Okay, everyone, I think we'll get started. So hello, everyone. Welcome to the 2023 NARS Workshop at AGI-23. My name is Christian Hahm, and I'll be running the tutorial session here in the morning. This session is going to run from, it's a bit of an echo. Test. Okay, it's okay. So I'm going to be running this tutorial session here in the morning, and we're going to basically discuss from the very beginning, from scratch, what is NARS, the theory behind it, how does it work, and then actually go into some hands-on examples, very simple hands-on examples, so everybody can get a, anybody who's not familiar can get a good understanding. Yeah, I know.
I think it's because this
and then in the afternoon we're going to have a workshop. We'll have open more. Hello? Yeah. What? Is it coming out of this screen?
you don't have to have your mic on, I think, because yes, no, it works. No, still okay.
Yes, that's it. So I think everybody who is connected need to close down the audio, the speakers.
I was just checking if the sound was through.
So is it working now? Sounds good. How it should work? Right? Cool. Okay, so just one more time. Again, we're going to have this tutorial session in the morning for people who are not familiar with NARS, going into some simple hands-on examples, and then in the afternoon, we're going to have a workshop for more advanced NARS topics. So here's the schedule for today. We're going to start off with an introduction to NARS non-axiomatic reasoning system, and more specifically, actually, the logic of the system. And then we'll go into the actual AI system itself and the real implementation, which is what Bowen will talk about. Then we'll take a short break, and Bowen will go through some reasoning examples using the real implementation, followed by a short example of a real-time application using NARS Palm. And Patrick will follow that up with hands-on examples, more advanced hands-on examples using NARS. And then we can have a more general discussion and question and answer. Sound good? Okay. On that note, I'll jump right into the intro to NARS. So first, what is NARS? Non-axiomatic reasoning system, or NARS, is an AGI project, which is why we're presenting here at the AGI conference. And what that means is that unlike modern mainstream AI, the field of AGI emphasizes more the holistic and general nature of cognition, which we see best in humans, which, as we've seen, are basically capable of accomplishing anything we set our minds to and conceiving of nearly anything, a very general capacity. And while many AI systems are usually oriented towards optimizing task accuracy in one domain, for example, like scoring the best image classification on certain benchmarks, NARS is open to solving any task which we assign to it, no matter which domain. So in this way, we can say that NARS has something like a basis for general intelligence, similarly to a human, because first, we can take any single NARS agent, at least theoretically, and have it work across any number of domains across its lifetime. And so in the design of NARS, we use a working definition of intelligence. We don't just use the word intelligence. We want to more concretely define it. And then we use this as a basis for the system design. And so we define intelligence to be the capacity of a system to adapt to its environment while operating with insufficient knowledge and resource. And by adapt to environment, it means to learn and accomplish goals in that sense. And so this definition of intelligence then gives us a design assumption, which is the assumption of insufficient knowledge and resources, or AIKR. And so when we say that we have this assumption, or when we say that the system has insufficient knowledge and resources, what we're meaning is that the system relies on constant finite processing capacity. It's not constantly needing more resources as it grows and learns. It always operates using a constant processing capacity, like a human brain. Works in real time, so you don't have to sit around waiting for to query the system or something. It works in real time, and it's also open to knowledge and tasks of any content, and that's the general part of the system. And that's to say that NARS is not restricted to any one domain. As long as you can say it to the system will process it and understand it to the extent that it can. And as a consequence of this assumption, the system itself has no overarching or objective benchmark, or like fitness function or loss function, which the system measures its learning or its correctness or optimality of its behavior. And so instead the system measures its correctness based on how well it's meeting its personal goals. The system itself has its own goals, its own set of goals. It can be very disparate. And so instead of using an objective function, the system processes its information and makes decisions based on the evidence that is available. And so this way, the system is more general, adaptive, flexible, and robust. So when we say non-axiomatic reasoning system, what is a reasoning system? It's a more traditional form of AI system. NARS is a more modern iteration. And there's 5 components to any reasoning system. So it'll have a grammar, or language, and this is how you represent knowledge in the system. It has a set of logical inference rules, and it uses these to reason over the knowledge. There's a semantic theory, and this is basically, the theory behind your system. What is your justification for why the system is expressing sentences with valid meaning? Why are those meaning valid? Basically, explanation of simple grounding problem. Finally, a memory structure. Because the system needs to store the knowledge in some sort of memory, and a control mechanism which it uses to select knowledge for using those inference rules. And so I've highlighted these first 3 components here because that's what we're going to focus on, at least in this presentation. And so in NARS, these are we kind of branch these all under the umbrella of non-axiomatic logic. These first 3 components all fall under the logic. And this is the logic by which NARS operates. And then components 4 and 5 are basically, how do you take the logic and put it into a real computer algorithm so that it works? And that will be in the next presentation. And so why use a reasoning system compared to other AI? Good question. There's the potential for domain independence, like we just said. If your language, if your knowledge representation is flexible, then it doesn't need to be restricted to any domain. And this allows for your, generality or general intelligence. A rule-based language, using like inference rules, things like this, it provides rich expressive power and also human understandability. Because when you're doing reasoning, this is sort of how humans think. We make justifications for the things that we do, even if they're not necessarily objectively good or, objectively good justifications. We all have justifications for our behavior. And so we can best understand reasoning systems compared to something like a neural network. Logic-based reasoning justifies the system's thoughts and actions past mere mathematical optimality. So the system can say, this is why I did what I did, not just because it optimizes this loss function, but because of these reasons, and which humans can then understand. And then finally, we have flexibility in combining these inference rules. So if you have a very small knowledge base, the system can take just this very small set of knowledge and derive many possible conclusions just using these different inference rules. So here's the layers of the logic, of non-axiomatic logic. And by layers, we just essentially mean that, we want to explain the logic in a way that makes sense, kind of simple, and then kind of build on the material. And so like now one is like the bare minimum of what you need for like a very, very simple version of the logic. Now two is like a more advanced version. And then we kind of build on the material up these different levels. And so in this presentation, we're going to cover all the way from now 1 to 8, but it's primarily going to be now 1, which is where the real meat of the logic is. So first, what you need to know is concept. So this is basically the ideas in NARS. So NARS memory, this is what is inside NARS memory. This is many, many concepts. And so on its own, a single concept doesn't mean anything. Instead, it gains its meaning through its relation to the other concepts. So this is the semantic theory of NARS. So when a concept doesn't refer to something in the outside world, it only means something in relation to the other concepts that the system has learned. So everything is relative to what the system has seen up to this point, and then it can compare different concepts. And so we use a word called a term to name each concept. And so a term can be anything, because like I said, a concept it's not necessarily representing something in the outside world. So it doesn't have to be like a cat, like the word cat or something like this. It can be complete gibberish, as long as the concepts are entering the system in a way that it can associate them properly. The term can be anything. It can be like ASDF 1, 2, 3. But the benefit of using a reasoning system is the fact that it's more human understandable, right? So you can use a human understandable word like cat or dog or apple, whatever it is. And so with these terms, you can build statements, and these are essentially the knowledge in the system. So a term names a concept, and then these statements describe relationships between terms or concepts. And so a statement has the form subject and copula, the predicate. So subject S, copula is this arrow, and then predicate is P. So S and P, the subject and the predicate, are terms, which are naming concepts. The copula is inherent to the logic, and it describes the relationship between the concepts. So here it's describing this arrow, this copula is describing a relationship between S and P. And the fundamental copula in NARS is this arrow. It's called the inheritance copula, and it describes a specialization generalization relationship. So something like water is a type of liquid is what that sentence means. So the water is a specialization of liquid, right? And the liquid is a generalization of water. And so the subject in an inheritance statement like this is like a more specific example of the predicate, and the predicate is more general. And the properties of inheritance copula is that it's reflexive, which means that a term inherits itself. So water is a type of water, technically true. And transitive, which means inheritance will hold across ordered terms. So if you have an ordering such as raven is a specialization of bird and bird is a specialization of animal, then using the transitive property, you can say, okay, well, a raven is clearly a type of animal. And so that's deduction. And so these statements represent relations, but by themselves are not terribly useful. So we add punctuation to them to make it a sentence. And basically what this means is that it can have a truth value. And so it could be true or false. So if we add a period to this cat as an animal, then we could say that this statement is true or false. And the period in this case, there's a period at the end of this is the punctuation that denotes the sentence as a judgment, which just means it's a piece of knowledge about the world. So there's three types of sentences. There's judgment, which is the period. It just means like a piece of knowledge or a fact. There's a goal, as this exclamation point as the punctuation. And it's a statement that NARS desires to make true. So for example, this is a goal saying NARS wants to put the coffee in the cup, which is good. And a question is the final type of sentence. This has a question mark. And when you put this into the system, NARS will try to find the answer if it doesn't already know it. So you could ask NARS, is a human an animal? And it could do some reasoning, some sort of backwards reasoning to try to say, oh, I don't know, is a human an animal? And compare like the properties of humans and animals. But a sentence is not only true or false, objectively true or false. Like we said, everything is relative to the system's experience. Nothing is declared entirely true or false by us beforehand, before the system operates. It's all decided at runtime based on the system's inputs. And so the system will receive a stream of information, and this is its experience. It's a stream of sentences, and it's input to the system constantly as it's living. And then, so this is K, this set here, if you want to consider it a set of the stream, a set of sentences. And then the system will then derive beliefs from this stream of experience. And this is essentially the way that the system can derive new knowledge that it's not directly been given. And it's a transitive closure of K, which we discuss a transitive property in which we can connect unconnected terms that were originally unconnected and then connect them using the transitive property. And so that's basically how NARS gets as many beliefs, is by doing this sort of connecting between different terms over and over. And so, like I said, in this way, the system's beliefs go beyond its experience, and it's actually reasoning about what it's experienced and producing new knowledge, even if the experiences seem quite different. And so that's why we call it systems beliefs instead of like facts or something, because this is just simply what the system believes. It's not something that we can take to be 100% necessarily true or necessarily false. It's just simply based on the system's experience and what it has been exposed to. So it could be completely wrong if it's been exposed to incorrect experience taught incorrectly, or it simply doesn't have enough knowledge about the current situation. Now, of course, it's kind of reductive to say that any statement is actually entirely true or false. You can't say that about many statements. And so often the truth is a matter of degree. So what do we do in NARS? So first I'm going to introduce a couple of concepts called extension and intention. So if you have some term T in the center here, it's going to have an extension, which consists of terms, and an intention, which also consists of terms. And the extension, and again, thinking in terms of the inheritance copula, which is the fundamental relation in NARS, the extension is all the terms that inherit T. So here, if you can read set notation, it says the extension is the set of all X such that X inherits T. And conversely, the intention is the other way. It's everything that T inherits. So the intention is the set of all X such that T inherits X. And you can see these dotted lines kind of show you what that means. And so in plainer terms, it means that examples of the subject are also examples of a predicate, and the properties of the predicate are also properties of the subject. And using these intension and extension, now we can begin to define evidence, which is what the system will use to justify its beliefs. So we have positive evidence, which is knowledge or evidence in support of a statement or a sentence. And then we have negative evidence, which is evidence against that. And so this is basically how we determine truth and false. So if there's lots of positive evidence, the statement is more true. There's lots of negative evidence, statement is more false. But it is a matter of degree. So to compute the amount of evidence, you take the intersection of their extensions. Well, this is the formula. These are the mathematics, which you can dig into after this if you like. I don't think we have the time. But essentially what's happening here is that if there is some term that inherits both S and P, imagine this green plus sign here is some term. You can see my cursor. This green plus sign is some term, and it's inheriting both S and P. So it is an instance of both S and P. So it's positive evidence that S inherits P, or P inherits S. But in this example, we're doing it in this order. And similarly, if both of the terms S and P inherit some other term, the same term, which is this green plus sign up here, that's also positive evidence. Because essentially, if the same thing inherits both terms, or they both inherit the same term, obviously those terms must be somewhat similar in themselves. So those are positive evidence. 4S inherits P. And then negative evidence is evidence against S inheriting P. So if something inherits S but not P, something is a type of S but not a type of P, again, using that transitive property, it should inherit P if they're similar. And since it's not, it's a piece of negative evidence. And similarly, if P inherits something that S does not, P has a property, S does not have that property, well, then again, it's evidence against S inheriting P, since S does not inherit that property. So this is negative evidence. And then you can sum up the positive evidence, sum up the negative evidence, bring them together, add them together, and you get your total evidence, which is the magnitude of the extension of S plus the magnitude of movement. So yeah, traditionally the truth value of a sentence represents how much does the sentence agree with reality as humans understand it, as human knowledge. How close is it to an objective fact as determined by the humans? But in NARS, it's not quite that way. The truth value is measured based on the evidential support. Now, the evidence is supplied by humans initially, or at least, if you hook a sensor up to it, you as the human designer or as the human operator of the NARS system are giving it certain sentences. But from there, NARS will take the evidence and put it together on its own. So a truth value in NARS is a pair of real numbers, FC, which are F is in 0, 1 inclusive, confidence is, or C is in 0, 1 exclusive. So F means frequency, and it's like the traditional understanding of truth. So if you have a frequency near 0, you might say, oh, this statement is pretty false. If you have a frequency near 1, it means, oh, this statement is pretty true. Confidence is the total amount of evidence that was taken into account when determining the truth value. So the way you calculate the frequency is the positive evidence over the total evidence. So this is like when you take everything into account, well, all the evidence for the statement, how much of it leans towards true, and that's the frequency. And then how much, since NARS will not take everything into consideration due to resource limitations, you also have this confidence value, which determines, okay, well, how much evidence do we have how much confidence and evidence do we have to support this frequency value? And so it really is the system's confidence in the statement. So the actual experience is the system receiving a stream of sentences from its sensors. You could have a human sit at the computer and type in sentences all day. Actually, probably will be better to just connect a sort of sensor to the system and have the sensor automatically produce those sentences for you. And each sentence will be input with a truth value, including frequency and confidence. And from there, the system uses truth value function, essentially a function over these truth values to determine the new truth value of the result. So every time it does reasoning, it's going to take two sentences. Each one has a truth value, put them together, determine the new truth value and the new result. And so we're all familiar with the traditional Boolean operators if you've ever programmed. So there's not, and, or. And from here you can say, oh, based on the true or false of the premises, we can determine the true or false of this operation here, of this operator. But in NARS, since we have this continuous valued logic between 0 and 1, continuous valued truth value, I should say, we extend the Boolean operators, but while still constraining them within 0, 1. So to negate a truth value, you simply take 1 minus the value. And is a multiplication of the values, and or similarly, it's a, well, if you know, or it's a not and. So that's what that is. So we're going to run through the basic types of inference. There's deduction, induction, and abduction. So if you have two premises, like S inherits M and M inherits P, as we discussed earlier by the transitive property, you can derive S inherits P. And we use a truth value here to determine, we use the function here to determine the truth value of the result. So you take the frequency of the premises, you multiply them, or you AND them. And you take the confidences and frequencies and you AND them to get the confidence of the result. So for an example, you could have a robin is a bird and a bird is an animal. You derive a robin, a robin is an animal using deduction. And those are the values. And this is what it looks like sort of visually. So those dotted lines are the premises and that solid line is the conclusion. Induction is essentially a generalization that one makes. So if you have here M inherits P and M inherits S, you can take the two more general terms and produce a new sentence by what we call induction that says S inherits P. And similarly, we have the truth value functions here to determine the frequency and confidence. And for an example, you could say a swan is a bird and a swan is a swimmer, say something that swims. And so you might say that to some degree, birds are swimmers, at least to some degree. Not all birds are swimmers, but some. The other way around, abduction, is comparing more specific examples with each other. So if you have P inherits M and S inherits M, then you can, again, derive S inherits P. You can see the visualization of this and the truth value functions. And as an example, we would say something like, okay, a seabird is a swimmer and a gull is a swimmer. And so we can derive that a gull is a type of seabird, just based on that knowledge. And so from here, we're taking two things which share a property, two concepts which are swimmers, and we say they must be similar in some way.
Questions, Jerry?
Sure, yeah, absolutely.
How do you determine the direction of that? Not that it's a gull is a seabird and not the other way around, a seabird is a gull.
You can do both directions.
Okay.
Here, this is just the one. But yes, it does go in both directions. And then finally, the revision rule, which is a special type of inference rule, which we use since we have this concept of evidence and the quantity of evidence, and like how much evidence are we using. And so when you have two sentences which have the same statement, We're not deriving any new knowledge here. It's the same piece of knowledge. They just have different truth values. Perhaps they were given from different sources, or they're based on different evidential base. So we combine them together. We combine their evidences together, and using this revision rule. And so we get a higher confidence since we're using more evidence in the calculation. So every time you do a revision, you will always get a higher confidence. Now your frequency might be different because again, frequency is something like truth. So here, if we have a bird as a swimmer is true and bird as a swimmer is false, two different people telling NARS different things, then NARS will have to put them together and say, oh, bird is kind of a swimmer. Taking them to be, and weighting them based on their confidences. The frequency is weighted based on confidence. So if it's more confident, the frequency will lean in the more confident direction. So in summary, there's three types of inference. We have the local inference, which is like that revision that we just showed, which is essentially just taking your beliefs and improving their confidence, improving their quality. Forward inference, which is the basic form of inference that we all know and love, deduction, induction. So given this, these two pieces of knowledge, how can I, thinking forward, how can I derive new knowledge? And then backward inference, which is based on this answer, doing inference backwards, based on the conclusion, what would be the premises? So basically doing the inference process in reverse. And that's useful for, like we mentioned, questions and goals. If the system has a question and it doesn't know the answer, it needs to do backward inference to say, okay, well, what do I need to answer to get this answer? So that was now one. That's the meat of the presentation. And now we're going to go into the higher levels of the logic, but only the very, very basics. So in certain cases, you can use special variations of this inheritance copula just for succinctness in writing or succinctness within your system of representation and like reasoning. So as mentioned before, sometimes the inheritance can go in one direction and also the other. And when this happens, it's not necessarily that S is a generalization of P or P is a generalization of S, it's sort of both. Or rather that neither is a generalization or instance of each other, they are just both very similar, rather than a true specialization generalization. So we can use the similarity copula to represent that. So something like Pepsi is similar to Coca-Cola. Pepsi is not a type of Coca-Cola, and nor is Coca-Cola a type of Pepsi. They're both types of cola, but they are not, they're similar to each other in that regard.
I have a question.
Yes.
Previously, when you looked at the values, like I'm thinking you can assign, like there is a thing object done, you assign a value that this is true. And does it matter how many times, like if like 10 people are saying this is true, like 100% doesn't matter, or is it just one like that line? Or it's good to have like many people who say the exact same thing and give the same value in a sense?
So it's based on the confidence. So you could have many people say something, like say as an input to the system, with very low confidence. And then you could have one person input something to the system with very, very high confidence. And that will, when it's combined, the higher confidence will take a higher weighting, a higher priority. Although the other 10 lower confidence will be taken into consideration as well and skew the truth value in a certain way. If the higher confidence one goes in a certain direction, it will skew much more strongly in that direction. So it's not necessarily the amount of sentences that are entered, but really how they're weighted with the confidence. Does that answer your question?
Yes, it does. Well, is there like an optimal how many frequencies you need, or like these are hundreds, thousands, or there is a limit?
No limit. Now, of course, you're going to get to some point where like you're increasing your confidence up to the point where it's like 0.9999999, and like you can't, like you add another 9 at that, it doesn't really matter. I don't know. Not really. But there are parameters that you can use to say, like we need much, much more evidence to get to that 0.99999. So you can configure your system in that way such that it will never really max out,
Maybe you'll
Yes.
cover it later, but will the system be able to track the source in the final output? This is where how the truth value came or what the reasoning.
Yes.
Will it be able to cite the source?
Yes. So while it's not technically in the logic, in the implementation of the system, we store what is actually technically in the logic. We keep track of all the sentences, like you said, that were used to derive the premises. We call this the evidential basis. So it's basically a list of all the sentences that were used up to this point to derive this final piece of knowledge. And we do this because if you take the same piece of evidence in consideration multiple times, you're going to you can't take the same sentence and revise them together to get a higher confidence because it's the same piece of knowledge. So you don't want to take the same evidence into consideration multiple times. It results in what's called circular reasoning. And so in that way, you need to make sure that when you have two premises, their evidential bases are distinct from each other. Good question. Thank you. So the other types of copulas are instance and property. So when the subject is an instance, which is the most extreme form of a specialization, then you can use this instance copula if you want, or you can put it in these curly braces. So for an example of an instance like Bob is a student, there is no further specialization of Bob. Bob is the furthest specialization you can get. And conversely, with the property, it's the other way around. So if the predicate is a terminal property or a terminal predicate, it's the most extreme form of a generalization, then you can use this property copula, or you can stick it in these square brackets. And so an example of that would be something like the sky is blue. Now you might say, oh, but blue is a color. Blue inherits it would inherit color. Well, the concept of blue is not exactly the same as the blue in the brackets. The concept blue is the concept of blue, and it wouldn't inherit color and things like this. Whereas the blue in the brackets means more like describing things which are blue. And so you can't get more general than that when you're describing simply the blueness of objects. So up to this point, we've only talked about atomic terms. So things like S and P, these are just single words. And this is, as we've seen, it can be pretty useful for describing knowledge, but it only results in very simple sentences and concepts. And we can introduce the principle of compositionality into the system by allowing the compounding of terms together into a new term. And we do this using term connectors. And the resulting term will have a different meaning that is related to the meaning of its constituent terms. So for example, you can take the extensional intersection of two atomic terms to create a new concept. And what this does is, as it suggests, it takes the intersection of S and P's extensions. What do I mean by that? You can have the compound like this, yellow, property yellow and bird. And this is a concept which represents yellow birds. So you can see how we're taking the two concepts and we're putting them together to create a new concept. We have yellow, we have bird, now we have yellow birds. And from this, the system can infer a statement like a canary is a yellow bird. If it has a canary, it's yellow. I saw a canary, it's yellow. I saw a canary, it's a bird. So I saw a canary, it's a yellow bird. So you can see how the system is producing new knowledge based on this very simplistic initial knowledge. So compound terms, that's now 3. Now 4 is about introducing arbitrary relationships between terms or concepts. So we've talked about inheritance. It's very useful, especially we're talking about like general intelligence. We're providing something which provides a specialization generalization relationship. Something is more general than the others, but we can't specify arbitrary relationships, which might be useful. So we introduced this product term connector. This is product. And if you use the product with the inheritance copula, we can represent any arbitrary relationship. So if we want to say water dissolves salt, that's how we would say it. Water product salt inherits dissolve. So you take sort of like the first term, water, then you move to the predicate, dissolves, then kind of back, salt. So that's how product works. And the dissolve is the relation. And you can deconstruct the product by moving the terms around to the other side using a different connector, which we call image. And then from there, you can say, you can derive new concepts such as water is something that dissolves salt. Yeah. And so this term itself has its own unique meaning, something which dissolves salt. So now the system has a concept when, if you say water dissolves salt, now the system can derive a concept of things which dissolve salt, which is not just water, it can be other substances, So we mentioned putting atomic terms and constructing statements or sentences out of them. And we call those the first order statements. But we also want to allow higher order reasoning, which means that we want the system to be able to form statements about statements. So we introduce a new copula called the implication. And what this allows is the truth of a statement to imply the truth of another. So it's not necessarily relating truthiness, but, semantic content, but relating to the truth of the two statements. And it's sort of like an if-then statement, if that helps you understand. So when S implies P, what it's saying is when S is true, P is true. If S is true, then P is true. For example, if the light is red, then the oven is hot. Don't touch it. Or if the light is red, it implies the oven is hot. It's implication. And so just like the atomic terms, you can take statements and connect them with each other, treat each statement like a term by itself, except you use a special set of connectors to connect statements with each other, but they're treated effectively the same. Up to this point, we've only discussed constant terms, which means that each term names a specific concept. So cat will, the term cat will always point to the concept of cat. One and only one concept. But there are certain cases where we want to represent knowledge, but the exact concept within that knowledge is not known, or it doesn't necessarily matter. And so in those cases, we use variable terms. And this is very useful for deriving generalized knowledge. So an example of a query variable, or a query variable is something which is a variable which is used to ask what term belongs in this sentence. So we could say, what is a red bird? And then NARS can try to figure out, using reasoning, what is an example of a red bird, and then we'll spit that out to the user. An independent variable, which is this hashtag X or pound X, represents any term under the given restriction of the knowledge in question. So for example, this X here, this sentence here says, if X is a type of dog, then X is a type of mammal. So whatever X is, the system can conceive of whatever is X. If it's whatever this X thing is, if it's a dog, then it's a mammal also. Now we're going to move into temporal reasoning. Up to this point, we've discussed how NARS can sort of take encyclopedic knowledge or book knowledge and put it together. But as we discussed the system, we want the system to work in real time, and especially in real-time applications, such as robotics. And so we need to have some sort of temporal reasoning so the system can figure out the consequences of its actions. Like it presses a button, does something happen? So what we do is we can allow judgments to have a timestamp associated with them. So in that case, we call the judgment an event. And this is usually what the system will receive from its sensors. So it might receive an event like at time t=1, the sky is gray. And then at time t=2, it might receive another event which says the weather is raining. So now when we do reasoning, we account for the time steps. And so in the simplest case, we just associate the two events using a predictive implication, which means this event preceded this event, or one event came after another. And this allows NARS to make predictions. So in this case, with our examples, taking these two sentences and using them temporal inference, we can derive an implication statement. If the sky is gray, then later the weather will be raining. And so this is how the system makes predictions. And finally, we're at NAL 8, which is operation and goals. And up to this point, we've only discussed the internal mechanisms of NARS and how inputting knowledge into NARS works, and then how the system reasons over it internally. But the system is an agent that we want to interact with the world. And so it needs an external mechanism to actually do that. Which actually, allows the agent to output information or, move some motor or something like this. Yes.
How do you update the knowledge? Like at some point, for example, temporal, initially the belief was Earth is flat. And after some time, new research. So how do you negate that? How do you say that the old knowledge is like invalid?
So the system might have a piece of knowledge that the Earth is flat.
Yeah.
This is what it thinks, and it has a frequency of 1, so it believes this to be true. Then you can come along and put into the system, the Earth is not flat, and give it a frequency of 0, which, saying it's false, and give it a very, very high confidence. And then it will revise those two beliefs with each other. And since you gave it the belief that the Earth is not flat with a very high confidence, then it will weight that statement or its belief in that direction more strongly. Does that make sense? So essentially, the system is constantly revising its beliefs and determining new truth values for them. So there's, yes, of course.
How do the model represent time? For example, it thinks it's about to rain. So is it represent a distribution of the raining probability, or just a specific time t to represent the t1? After t1, it's about you.
So the way, that's a good question, and it's sort of a tricky point. Like, how do you represent an event? Do you represent when the event starts, or in the middle of it, or towards the end? Like when it's raining, like how do you put that into the system, or when do you put that into the system? In the middle of the rainstorm, at the beginning? The way we do it is at the beginning of the event, or at least the system is receiving a stream of experience. And so it'll constantly be receiving information like it's raining. But basically we take it as, a single time step, like a t equals 1, t equals 2, t equals 3 with each sentence. So it will have, one number associated with it, which is the time. And so an earlier timestamp will come before a later timestamp.
When the new knowledge comes, when we first, for example, like when we inputted the Earth is flat, we will input at that point with a high confidence, because that's the knowledge at that point in time.
Sure.
And then the next one comes, that also has the high confidence, because now, so how does that replaces, and what would it take to replace the old knowledge? For example, like this new president got elected, so that president, that's the truth. Okay, got elected with a high confidence. Then the next one got elected. So how does it know, like, which is the current president?
Well, it depends on.
Both had high confidence at that point in time.
I agree. It depends on the design of your system, how it decides to treat old knowledge and new knowledge.
Okay.
You could, for example, flush out that old knowledge just by sort of putting that new information into the system many, many times, or with an even higher confidence than the old one. It depends on the actual NARS mechanism that you're using. How does it decide to treat prior knowledge with new knowledge? So returning to operations, there's a special type of term called the operation, and this is how NARS performs external actions. So you might have an operation like jump. And so NARS can, when it selects this concept or thinks about this, so to speak, then NARS can jump. So if you have set up your NARS with some sort of robot, it has some sort of motor actuator that allows it to execute a jumping motion, then when NARS executes jump, then the operation can trigger that motor, launch the robot up. But we don't want NARS to execute the operation every time it thinks of it. That doesn't make any sense. We only want it to execute the operation when it wants to execute that operation, when it makes sense to. So we introduce goals, which is the basically how the direction of the system. So we can input this goal like NARS wants the door to be closed. And it might have some knowledge, well, if I slam the door, then the door will be closed. And so using backward reasoning, it says, oh, I want the door to be closed, so I should slam the door. Hopefully it doesn't slam, hopefully it closes it nicely. But it could learn to slam the door based on its experience. So from here, the NARS would then derive a goal to execute that operation slam. And so it's important goals are important for operations so that it's not just executing random operations all the time, but it's also important to drive internal factors, the internal factor of motivation. And it can be used to steer the control process. And because there's many possible things that the system could be thinking about, reasoning about, motivation helps to sort of focus the system on specific pieces of knowledge to what is most relevant to it as a subjective entity. So that concludes the now portion. We're going to go into very, very basic memory and control because I know Bowen will be talking about this. But just to give everybody a sort of surface level understanding of the memory. The memory consists of tasks and beliefs, and a task is a question, a goal, or a judgment. It's something that that NARS needs to process. It's a task for NARS to complete, right? And then NARS also has the beliefs, which are the judgments that NARS already processed. So when you input something into NARS, say a judgment, a piece of knowledge, a NARS, that'll be a task. And then once it processes that task, it becomes a belief. And the tasks and beliefs are clustered into the concepts, which again are named by terms. And then the concepts themselves are prioritized using a number we call priority. And then NARS can select concepts based on which is the highest priority at the current moment. And that way it's only focusing on what is very important at this moment in time, as opposed to something irrelevant for the current situation. And if you like, you can visualize the memory as a network where every concept is a node with some term attached to it, some word. And then the relations between the concepts, you can represent them like links. Or like weighted links where they're weighted with the truth value here. And remember, this is frequency. This first number is frequency. And the second number is confidence. So if this helps you to visualize the NARS memory. Then finally is the actual algorithm. How does NARS operate? So this is called the control strategy. It's still an open problem. And different NARS systems can have different control strategies, and they might be better in certain domains. And so in each step, the task interacts with the belief according to the applicable rules. That's the same within basically any NARS system. But how those tasks and beliefs are selected is called the control strategy or the control mechanism. And Traditionally, they're selected probabilistically biased by their priority, which means that concepts have certain priorities. And so higher priority means higher chance to be processed by the system. And that's the control strategy. And various factors then influence that number priority. So like how useful was this concept? How relevant is this concept right now? And so on. And that's it. So if you want a full dive into non-axiomatic logic, this is very surface level, but there's a wonderful book called Non-Axiomatic Logic, a Model of Intelligent Reasoning by Dr. Pei Wang, who's here, the creator of NARS. It's a beautiful book, so I highly recommend you read it. And this will take you through the design and justification of now levels 1 through 9, along with the interesting discussions behind NARS and the relevant mathematical theorems to justify the logic. And this is a must read for anybody who wants to do research with NARS. Awesome. We're pretty much right on time. Thank you very much. And next up is Rowan.
Okay. Hello everyone. Glad to be here. And my name is Bowen Xu. I know my last name is hard to pronounce in English, so you can also call me Bowen Xu. I'm currently a PhD student at Temple University as a member of Temple AGI team. And so today, in my part, I will introduce the design and the implementation of NARS, as well as how to use open NARS to do some reasoning with some simple examples. I will firstly introduce some core ideas of the control mechanism of NARS, and then some ideas including the budget, memory, and working cycle. And then the newest version of OpenNARS, it's OpenNARS 4.0.0 that is implemented using Python. And after that, I will just show you how to install and get started with the newest version, and how to use it to do some reasoning. And okay, now let's get started. So generally speaking, the system consists of 3 parts. And the first one is the language of the representation. It's called narcis. And anything which can be represented as narcis can be recognized by the system and handled by the system. And the second part is the logic, non-axiomatic logic. And it is suitable for everyday reasoning. And it defines what the truth is, it defines the uncertainty calculus, and as well as some logical rules. And Christian has introduced this part, so I will focus on the third part, which is the control mechanism. And the third part is non-axiomatic reasoning system, and it organizes a bunch of inference steps all together and can work under the assumption of insufficient knowledge and resources. And today I'll focus on the third part, and that is the control mechanism. And though it's impossible to go through too much details, But I hope I can give you some basic intuitions, and you can roughly know what is going on inside NARS. And to understand why NARS is designed in such a way that is different from designing a special purpose system, we have to start from the working definition of intelligence. So by definition, intelligence is the capacity of an information processing system to adapt to its environment while operating with insufficient knowledge and resources. Here, with insufficient knowledge and resources has a special meaning. It means the system must be finite, open, and operate in real time. So being finite means the system's information processing capability is roughly a constant during any time, any period of time. And being open to new tasks means to make no restriction on the content of a task as long as it can be expressed in an acceptable form. And for the system to live and work in real time means that new tasks of various types may show up at any moment, rather than just come only when the system is idly waiting for them. So to be open to new tasks, as long as a task can be expressed as a narcissist sentence, then NARS can handle it. So it's easy to understand that NARS is open, right? And to be finite, the capacity of the memory is limited. That is to say, the numbers of concepts, of tasks, beliefs, etc., are finite, no greater than a certain maximum number. While to work in real time, a task is handled once a time within a working cycle, and multi-step reasoning is executed through multiple working cycles, and new tasks can be handled at any period of time. So how is the point 1 and point 2 realized in NARS? And what does the working cycle mean? So let's explain it step by step. So firstly, we must understand the fundamental element of the control mechanism, that is the budget. Every task is in NARS has a budget that is defined as a tuple composed of 3 members, priority, durability, and quality. And here, priority is what? It is the priority of a task to be processed. A task with high priority tends to be processed first, and the priority of the priority of a task is not constant. Instead, it's dynamic, and it may decrease or increase whenever a task has been processed. So durability determines how fast the priority change. For example, at here, the durability of the red curve on the left-hand side is less than that on the right-hand side. So it just decreases much faster. Right? And so more concretely, storage resources are allocated through budget during a short period. An item, which could be a task or concept and so on, with higher priority tends to be preserved, while that with lower priority tends to be forgotten. And during during a long period, an item with higher quality tends to be preserved, since priority ultimately decays to the quality, right? And during a medium term, an item with higher durability tends to be preserved. And since with a higher durability, the priority will just decay slower. And also, an item's processing time is determined by the budget. During a short term, an item with higher priority has a greater chance to be processed. And because it has a greater number of time to process, the more times an item is processed, the longer the total processing time the item is. And so as the other two cases. So in a nutshell, budget is all you need, although it's a kind of joke. And budget determines the amount of processing and storage resources allocated to an item. Here, an item could be a task concept or others. And exploiting the budget, there is a data structure which can make sure the memory is finite and new tasks can be handled at any time. So I will introduce this data structure. The data structure is called bag. A memory is a bag that stores a collection of concepts. And here, here's what a bag looks like. There's a bunch of buckets. Each bucket is a list that stores tasks corresponding to a certain level of priority. For example, a task with priority 0 is stored in the first bucket, and while a task with priority like a 0.021 is stored in the third bucket. So there's a pointer which points to the non-empty bucket with the lowest priority, and the default value is 0. And whenever an item is put into the bag, it is inserted into the corresponding bucket, and the item container simultaneously it is inserted to the item container, right? And here the item container is a kind of data structure of dictionary with a maximum capacity. So what does it mean? So when there's some room for storage, so the item is added into the item container directly, and after a period of time, the container is full. Then at this time, if a new item needs to be inserted into the container, into the bag, it will be overflowed. So an item in the bucket with the lowest priority will be removed, so that the new item could be inserted. And the bucket which is pointed to by a pointer, we might as well call it the current bucket. So whenever an item should be picked out from the bag, an item is picked out from the current bucket. And then the pointer has a certain probability to stay or move to the next bucket. And the probability is determined by the level of the bucket. For example, for the first bucket, the probability to stay is very low, but for the last bucket, the probability to stay is very high. So this is how the pointer is working. And okay, and an item is picked out for processing, and it is then put back afterwards. So the priority of the item should be changed towards the quality to some extent, and this extent is determined by the durability. And so now let's go back to this page. A memory in NARS is a kind of bag, and so that a concept compete with each other, and some concepts are eliminated according to budget and the bag data structure mentioned before. And in the meanwhile, you may understand that the concept in the bag with high priority has a greater chance to be processed. So given the data structure, the next issue is how to organize the multiple inference steps altogether. So this figure shows the architecture of NARS, and there are many channels as the so-called mind-body interface, and so that the system can interact with the environment, and all the external inputs and the internal conclusion derived from an inference engine are put into the so-called overall experience buffer. And the content in this experience is put into the memory. And tasks will be just like conceptualized. Some concepts will be constructed. And tasks in the internal experience buffer are competing with each other. And also tasks in the overall experience buffer are competing with each other. And within each working cycle, a task is picked out from the overall experience. And then it is conceptualized into the memory, meaning that the concepts corresponding to the task is constructed. So generally speaking, in each of the working cycle, one concept is picked out from the memory, and the related premises like a task and a belief are input into the inference engine, and you can get a conclusion, and then just do the next step inference. So in the following, I will show you concretely what's going on by using some animations. For example, how does the system handle the task of judgment? For example, we have a judgment, say bird is an animal. And firstly, it will be input into the overall experience. And then we take out the task and put it into the memory. Since the memory at the beginning is empty, so we just construct a concept, which is bird is an animal. This whole thing is a concept. And then we put the task into its beliefs table, because since the task is input to the memory, so but here the task becomes a belief. And this concept is linked to this task, and we call this link a task link. And also, since we have bird is an animal, and there's a bird here and there's an animal here, so we need to construct other two concepts, bird and animal. And some task links are also constructed. And also we just build some links between the concepts, and these links are called term links. So which represent the relations between the terms, the concepts. And then after the links are constructed and concepts are constructed, the task is put back to the overall experience. So after some time, we have constructed a network of concepts. And then, so how to do an inference step. So in each working cycle, we just pick out a concept, and through the term link and task link, we can get a task and a belief. For example, we get a task Robin as a bird, and we get a belief which corresponding to bird, but there's no belief corresponding to bird, the concept bird.
Oh, so there was a question over here.
Oh.
Yeah. Where does the task comes from? From the coding or from the?
It's from some channels. For example, you can see here. We have some channels like NARS channel, sensory motor channel, and so on. And the narcissist channel is what a developer can just input some narcissist sentences to the system.
All the tasks comes from the developer or
Theoretically, no. It can be from the developer, and also it can be from the sensory motor channel. Like it can just directly interact with the environment and get some data from the sensors. Yeah, it's possible.
So all the data from the sensors are not just evidence.
Derived tasks, I think he's asking about.
What?
Derived tasks he's asking.
Yeah. So you have some original tasks from developers or sensors, and also given these tasks or given these tasks and beliefs, you can derive some conclusions through some inference rules.
It's also back into the system as well.
Generate new tasks initial.
Yes. It can just get some derived conclusions, like some task can be derived from the system itself through reasoning. Okay. So in each step we get a concept, and we try to do a inference, but even this task and this beliefs table, we have nothing to get out, because we have nothing to derive. But if we just pick out this concept bird, and then through its task link we have Robin is a bird, and through its term link we get this concept, and a belief of this concept is bird is an animal. So we have a valid task and beliefs that I believe. So we put these two guys into the inference engine, and we can derive the conclusion Robin is an animal. And this task is put into the internal experience. Okay, so this is how generally is how a judgment is handled. So let's see another example, which is a little bit contrived example. For example, we have we have two balls, ball A and ball B, and we have a belief that if ball A is moving left, then ball B will be moving right, and then we have another belief, which is if the system push the ball A, then ball A will move left, and the goal is that we want the ball B to move right. So let's see what's going on inside this system. And firstly, suppose we have had this network, this concept network, and we take a task from the overall experience, which is this goal. Ball B should be move right. This is the goal. And we check if there's any concept here. So we take out the concept, and also we can find a task and a belief. We have this goal and the second sentence, this belief, the second sentence. Oh, sorry, the first sentence. Then we can derive that derive a new goal, which is we want the ball A to move left, and then okay. So, oh, and then we focus on this concept, which is if we push ball A, then ball A will move left. And then we can derive a new goal, which is we want to push ball A. So we can see that a goal is derived through a backward reasoning. Okay. So now let's go back again to this page. All the new tasks are competing with each other, and they are competing in the experience buffer, as we can see here, and all concepts are also competing with each other. A new task can show up at any period of time, even though they may be handled with a delay. So this is some basic ideas of how the system runs. And then let me show you some implementations of the OpenNARS system. And now we have done with the fundamental ideas, and then here are some implementations. Like we usually use this version, OpenNARS 3.0.4. It's the most stable version currently. And also we have another version, OpenNARS for application, or we call it ONA. And it is implemented mainly using C or C++, and it focuses on application. And we have a new version, which is OpenNARS 4.0.0, and it follows the design of 3.0.4, and it is implemented using Python. And this version puts more attention on maintainability of the code. And it will be uploaded to the OpenNARS website soon, although it can temporarily available in this GitHub page, the third page. The project is composed of 3 parts: the NARS parts, the logic NAL parts, and NARS parts. And the first part, NARS, implements the internal representation like term, statement, compound, truth, judgment, and so on. And also it implements a syntax parser. And the logic part implements some inference rules. And the control part, the third part, it implements some data structures like concept and back and so on of the control part, as well as there's a reasoner that executes the working cycle. Okay. Maybe we can have a break, and then I will show you how to use the newest version to do some reasoning.
Okay, we'll resume the session in 15 minutes. Yeah.
Well, the general. But you see, we shouldn't still be arguing.
And I think
20 years
Patrick
later.
was saying that when inference is.
We really shouldn't. Because to me, AGI is in my talk, I mean, if we can't even agree on what the goal is,
Well, it's a concept.
you know, then what's the point of talking about the architecture? You know,
1,000 concepts, but actually,
I
it's
recall
not
these are
like
correct. They already got
1.9 million.
No, forget about that. I'm talking about AGI. I'm talking about the community here.
Within a single concept.
They cannot. No, but we first need to be on the same page. And I mean, I don't spend a lot of time going to
Spirit. Yeah, it's very,
We have been, you saw some of the GPT work.
Of course we know, yes. AGI, but that's my whole point. What will it take to do AGI?
I've been involved.
So the first thing,
I'm trying to steer clear.
that's the problem, even though we. But why don't you? What are the? Because when you say we don't even agree on the definition, well, then let's. For example, then let's.
So the LLM, it seems to work good.
Yeah, but you know, if he doesn't want to be part of the discussion, I mean, Ben is. Everything is everything, you know, rocks are conscious and everything is intelligent. And, you know, okay, fine, if, you know, you're not going to be part of the discussion. If you don't want to pin down the discussion, the problem, goal of AGI.
And you're getting so amazing.
Well, that's fine. It doesn't matter. It's not the quantity of people, it's the quality of people.
Top of mind.
Who really wants to crack the problem? And if you're not going to define AGI, then
It's a nice merger of strengths and GPT.
but then
You
know, like, can we sit down and say, okay, what are the goals? What are the stepping stones? What are the benchmarks? What makes sense, what doesn't make sense, and go through it systematically and say, okay, where do we disagree?
So we have Patrick's aware that's kind of replacing the vector database with a symbolic graph database, right? And it looks like
Everybody has their.
It's like when people tell me.
Individually can. And then you can get them to agree or not, but like the professor said, it's hard for everyone to agree.
I don't care about everybody.
it's a combination of Patrick's work and.
You know, I mean, just say you and. Yeah, I think if the two of us could agree on whether what parts of your approach is.
Oh, we'll link you. And we'll probably integrate our plug. I mean, no one's really doing this symbolic. I think that's not pushing. There's a couple other companies.
Right, but we don't even, we haven't, I'd be very happy to.
Yes,
the next 4 days, I don't really care about the presentation.
Yeah.
What I, yeah, exactly. You know, I mean, how often do we get the chance here? How often do we get the chance to read? What are the strengths of, you know, your approach or strengths of one approach and weaknesses? Are we on the right track, you know? And to actually, it's hard, but to be honest and put the ego aside and say, well, maybe it's not right. But if we really want to get AGI going, if that's important, it's important to me.
I haven't seen
It's got to be more.
you hadn't turned up when I last came up here.
You know, if I have to walk away.
So they're doing their.
That probably should be in the session.
With ChatGPT.
Yeah.
It's a huge shock for
That's
all
what
of us.
Nils is.
Right on for you, I think. No, I mean, nobody would have expected, I mean, the people building it didn't expect that you could get that level.
Ben is here.
I
So
mean,
you leave on.
you know, it really, I mean, I had to really go back and say, is this a path? And I mean, that's obviously a discussion, I assume we're having here. Is there some way of using that transformer technology as some kind of a foundational stepping stone or something? I don't believe so, but or use it in some way, you know.
No, maybe compare, like you said, what is the goal? Something like ChatGPT.
No, that's again coming back. The first thing you have to do is agree on the definition of AGI. You know, and to me that's actually very simple. So I think we have you should have some rights. You know, not that you own it, obviously, it's society takes it over, you know. But we can actually say then within our community, let's use it. I mean,
That's what you're talking about?
yeah. But, you know, I mean, I started a Facebook group many years ago, and I couldn't call it AGI because by that time I called it real AGI. You know, I mean, that's how ridiculous it is. The reason we coined the term AGI because AI was no longer real AI, you know.
Now AGI is also taken.
But, you know, but we can put that aside and say, you know, we can have a new code language and say, all right, we're talking about real AGI, you know, or whatever. But as long as
Keep adding words.
yeah, but you know, let's agree on what that needs to look like, what it needs to be able to do, and I think that's actually not that hard to pin down at all.
Well, I'm interested to hear the talk.
Yeah, and then once you say yes, this is what the system needs to be able to do, you know.
Yeah, well, you need a goal before you can
Yeah,
move towards it.
then you can say, does your design meet those requirements?
Absolutely.
You know, and so yeah, that's. I mean, I'd love to spend 4 days talking about how can we actually get to AGI.
Now let's make some progress.
Yeah, yeah, and if we need to, and if we need to reboot, well, then we can say, all right, last 20 years, we learned what not to do. You know, that's also, you know, also progress.
Sure. Yeah.
I mean, I don't think I'm not suggesting that. I mean, I think NARS has a lot of, you know, really strong things. I really like the approach. And if I ever got really decent funding, I've always said I want to hire some engineers to see how far they can take NARS, you know, as a sort of competitive approach to.
Well, recently we're getting towards like real time like applications, whereas like with patterns, you know, like moving around and like actually like interacting with the world and using reason.
Yeah, that's really, yeah.
Which I think is a huge step forward.
I've actually had a few meetings over the last 2 months with up to speed recently. But he's now been sucked into the TPT integration. Which is interesting to see how far you can push it, but it's a side. It's a side job. But it's a side
I've
job.
got some ideas.
Yeah. Drink.
We should probably start up here. Huh?
Yeah, we'll have a lot of material cover.
You can go.
Yeah.
Not just one go. Break into.
Budget is all you need?
Yeah. Yeah, because for a component user, you could kind of, you know, the mechanism or modifying stuff.
But it's not.
There is a PowerPoint. PowerPoint? On the second. Oh, that's good. So we don't need to run the web.
Oh, yeah.
That would be fun.
Okay, welcome back. So next I will show you how to install and get started using NARS 4.0.0. And so since it's implemented using Python, so you can just install it through AGI, like PID install by now. So I can temporarily name it as Python, but maybe I will change it. So like you can install it in your control in this net. I will going to share this screen. Your presentation is not on the screen. Oh, sorry. Yeah, we can use this command to install the NARS 4.0.0, or you can just download the original code and use this command to install some packages. It's temporarily just located in this address, but it will be uploaded to the OpenNARS website, and then you can run this command to execute the control. Like I will show you here. To run the NARS Python and run the Python module. So you can start this listener, and then I will show you some examples of reasoning. Like this is the nail one rules. Like you have bird is an animal and Robin is bird. Then you can get Robin is an animal, and I can show you how to just use this in OpenNARS. Like you have Robin is an animal. A bird is an animal. Sorry. Bird is an animal, and then Robin is a bird. Okay, so now you just input two sentences or two tasks into the system, and then you can just input a number. It means how many numbers you want to run, how many working cycles you want to run. So I want to run 5 cycles. So it derives Robin is an animal according to this deduction rule. Also, it can derive animal is a Robin according to another rule, but it's much weaker than the previous one. It has a lower confidence. And also I can try this induction rule. Maybe we can restart it. It's Robin is an animal. And Robin is a bird. 5 cycles. You can see it derives bird is an animal, and animal is a bird according to the induction rule. Also, there are some other derivations, some other conclusions according to other rules. Okay, this is the first example. And for the second example, it's about the revision rule. For example, I saw four swans which are white before, but now I see a swan which is not white. And according to the revision rule, since we see the 4 positive evidence, so the confidence is higher than this one. So now I see a swan which is not white because we have only 1 evidence, so the confidence is 0.5. And that's inputted into the system. Its swan is white. If you want to input the truth value, you can use this % symbol. And for example, we have frequency is 1.0, and the confidence is 0.8. And then we input this sentence into the system, and we input swan is not white. Say it has a frequency of 0.0, and the frequency is lower, it's 0.5. And then you can see it outputs the conclusion that swan is a white with a frequency of 0.8 and with a higher confidence than the previous two. Okay, and for the third example, it's more complex. Robin is a type of bird or a type of swimmer, but robin is not a type of swimmer. The first sentence is like this: robin is a bird or swimmer, and we have some evidence to support this this belief. So let's input this sentence into the system. Robin is a bird or swimmer. It has a truth value of this. And then robin is a swimmer. It's not a swimmer. So it should have a 0.0 frequency and 0.9 confidence. And then we run some cycles. You can see here, robin is bird with this a very high confidence. It's them as this. So it's kind of we get this conclusion according to a certain rule in non-axiomatic logic, but I'm not going to go through too much details on these inference rules. And for the next example, it's NL4. So we have the belief that an acid and a base can have a reaction. So it can be expressed as this form. Let's try it. An acid and a base has a relation of reaction. The relation between acid and base is a kind of reaction. And the default truth value is 1 and 0.9. Okay, that's run like 15 cycles. Okay, you can see the outputs is this and this. It's the first sentence means acid can react with base, and the second sentence means a base is something that has a reaction with an acid. And for the last example, like it's about the goal realization. For example, we have I wish to feel good, and it's a goal. And we have a belief that if I'm not hungry, I will feel good. So we can just represent these two sentences into narcissist as just like this. Self is good. We have self is good. It's a goal. And we have if I'm not hungry, then I'm good. So we have a negation. Self is hungry. This symbol means negation. If self is not hungry, then self is good. Okay. Now we have these two beliefs, and then let's run 5 cycles, and then it will just get a new goal, which is self is not hungry. This is the goal which is derived. Okay. This 5 examples looks simple, but you can just see, yeah, it works in this new implementation. And then also there are some to-dos. You know, some of them are listed here. The first is to implement the event buffer proposed in the newest technical report, and the second is to implement some demos like Pong game or Fighter Plan, which is also implemented in other versions, but haven't been implemented in this Python version of NARS. And also, I would like to accelerate the program through C or C++. I just want to implement the NARSys and the logic parts using C or C++, but implement the control part in Python so that you can just modify the code more flexibly. And also, I need to refactor the code of rule table. It's kind of a messy. That's all. Maybe I hope I gave you some intuitions of the implementation and design of OpenNARS, and you can just do some simple experiments using this Python version. And later, maybe Patrick will just show you some demos using his implementation, namely ONA, OpenNARS for application. Okay, that's it.
Thank you, Bowen. So we've seen how NARS can handle encyclopedic knowledge, sentences, describing general facts about the world, things like dog is an animal, bird is an animal, a raven is a bird, things like this. But what about using NARS in a real-time application, especially these days with the other AI systems, especially very impressive AI systems, are doing tasks in real time, or things that require things like dexterity and speed, like playing soccer, playing virtual games that are like real-time video games, things that require thinking fast, things that, and this is the type of thing that traditional reasoning systems do very poorly, because usually they get stuck in long chains of reasoning. Now this is something NARS can handle. So we're going to discuss how to get your NARS to play Pong. So creating your first real-time application with NARS. So as we saw before, NARS can learn from the encyclopedic knowledge, and it can do lots of reasoning on that. And usually it's not a problem, because if we simply want NARS to derive new knowledge and we don't have any time limitation, time pressures, then we can just sit back and wait for the system to finish up its reasoning and then ask the question. But can NARS also learn to cope with fast-paced applications like a video game? Yes, because unlike the traditional systems, NARS doesn't get bogged down in these long chains of reasoning. An example of that would be Shaky the robot, one of the first computer vision systems and in a robot. That was one of its primary issues, was that it would be assigned to do a certain task, like move somewhere, and it would get stuck in a long chain of reasoning. It was one of the primary issues with Shaky. NARS doesn't get stuck in long chains of reasoning because it's constantly reasoning incrementally. So it only performs a single reasoning task at a single time step, and then it can move on to the next reasoning task. It doesn't follow a chain. It selects from all over its memory probabilistically. And also, it has a temporal component to the logic. We talked about events. So it can do temporal reasoning. So what we can do is in a real-time application, you attach sensors to your system because you won't be sitting there typing in real time. You could not type fast enough. So you need to have some sort of algorithm or sensor which will input into NARS certain events based on whatever the sensor is picking up. And so the sensors will input events into NARS regarding what's happening outside in the world. And then similarly, you attach motors to NARS so that NARS can interact with the world. And then using the temporal reasoning, NARS can associate its various sensations from its various sensors to form generalized knowledge about the world. And then it can use this knowledge in reasoning to inform its motor actions. So we're going to walk through how to use NARS in a real-time application. Pong. This is an example of NARS playing Pong. NARS is the one on the top, and that's me on the bottom. As you can see, the paddle actually follows the ball. It does a pretty good job of blocking it. And on the right, you'll see the it says ONA operation. At each moment, that's the operation that NARS is currently executing. And so for any real-time application with NARS, first you select the application. We selected Pong here. Then you want to identify the role of NARS. So in this case, we want NARS to play the Pong. So NARS is the Pong paddle. And the goal of NARS is to block the ball from passing it and getting into the goal. So according to the above, we give NARS the goal that we want, which in this case would be NARS wants to block or self inherits block. Then step 2 is to hook up the sensory motor interface. So first you determine what is the embodiment in the first place. In this case, it's a Pong paddle, and we have 3 sensors indicated by these lights that are on the paddle. And one of these will light up depending on the ball direction. So if the ball is this to the left light goes on. If it's the right light goes on. If it's right in the center of the paddle, the center light will go on. So in that sense, we have one sensor, like a position sensor for the ball, and it has 3 possible states, left, center, or right. So at any given moment, the sensor will be inputting left, the ball is left, the ball is center, the ball is right. On the other flip side is the motor. So this is the Pong paddle, and similarly, there's 3 operations. So the system can move the paddle to the left, it can stop, or it can move to the right. And so, like I mentioned, the sensory information is not going to be in NARCIS like natively. You're going to have to write some sort of conversion algorithm where whatever the sensor is picking up, it becomes a NARCIS sentence, and then input that into your NARS system. So for example, if the sensor picks up, we have an algorithm, where's the ball? And then, we detect the balls to the left. So the sensor is detecting the ball to the left, and it might enter this event, the system ball is left. So the system is now getting sensations, and then you also want to input your motivational signal, which would be that goal we talked about earlier. And so you want to be supplying enough, you want to be supplying this goal to make sure the system remains focused on solving that goal. And then finally, you run the application. So what's going to happen? First, NARS, as we mentioned, the memory is completely empty when it first starts out. It doesn't know anything about the world, so the system has to first explore, make mistakes, and then learn about the world based on its sensations and its motor actions and the associations it makes, the sensory motor associations that it makes. And the way it explores is through what we call motor babbling. So what this is sort of like a baby babbling. NARS automatically triggers its motor operations, despite the fact that it's not really certain what these operations do, but it will try them out. And based on the sensations it receives after trying these motor operations, it can then make certain associations and derive knowledge saying, okay, I triggered this motor and this sensation happens. So maybe whenever I do this action, this event happens. And if you're going to be running experiments like this, you can't just let NARS run and expect magic to happen. You need to observe the application and try to think about what is NARS receiving and what is it doing internally so that you can really gain an understanding. And that's the beautiful thing about NARS is that it is human understanding. So you think about what NARS is doing from a human perspective, and it's not a black box. If the system is acting up, there's a reason for that and you can determine the reason. So for example, sometimes like there are random factors in NARS and also randomness in your application, like physics for certain physics applications might have a random component. And it could result in a situation where NARS doesn't get the opportunity to learn the behaviors that we want it to learn. So like in this Pong game, you can see the ball sometimes will get stuck like on this wall, start just bouncing back and forth, and then it gets kind of stuck. And so in that case, NARS will just babble back and forth, and it will never receive any sensations about the ball hitting the paddle. So we can get we can watch a video about what this looks like. So right now, NARS's memory is completely empty. NARS is the paddle there at the bottom of the screen. You see that the paddle lights up depending on the position of the ball. Now, every once in a while, you'll notice the ball is going to hit the paddle, and that's what we want. That's the goal of the system. And on those coincidental moments, NARS is going to learn, it's going to be babbling. It's going to say, the ball was in the middle, I stopped moving, and the ball hit the paddle. And it's going to learn, okay, whenever the ball is in the middle of the paddle, I need to stop moving, and then I'll hit the ball. And over time, very, very quickly, NARS learns to master Pong. I mean, Pong is a pretty simple game, but based only on this motor babbling and these very simple sensors, that we're not inputting an image or anything, it has these simple sensors, it will learn to play Pong. So you watch, and the paddle will almost perfectly follow the ball after a couple of iterations.
Does NARS have the tendency to cheat the system, like trying to make sure that it gets like this angle that it never needs to move?
Can you repeat?
Like previously, I've been watching some AIs that will try to like cheat the game in a sense that like try to find the angle that makes the ball just go back and forth, so that it doesn't have to move. So make sure that it makes the least movements to have the maximum.
Well, that would be the optimum solution, right? So yeah, I suppose that would happen. In this specific case, the ball never really goes up and down like that. It only goes left and right. I've never seen it get stuck up and down like that, although you're right, it's technically possible. But in that case, yeah, the optimum solution would be to just stand still and let the ball just keep going. You're right. So let's analyze the clip. Through associating the sensory events, NARS learns that when the ball is in the middle and it stops moving, the paddle will block the ball. And it does this through conjunction and temporal induction. So the conjunction's happening here. The sensor is saying the ball's in the middle. The stop comes from the babbling, and we can put them in conjunction. These are both happening at the same time, so you can say and like these are both happening. Then suddenly an event is received later that the paddle was hit, and so we can use temporal induction to form this implication statement. So if the ball is in the middle and I stop, then I hit the ball. Very simple. And since that is the predicate here is the original goal. If you remember, that's what we're inputting. Then you can use inference to derive a goal for this subject, for this conjunction, and that becomes another goal, whose completion leads to that goal, according to the implication statement. And so because stop is an operation, it's controlled entirely by NARS. So if we desire stop, we can just stop. The only goal now is to get the ball in the middle. So NARS will derive, I want the ball in the middle. Then by further motor babbling and association, NARS learns the ball is left and I go left, then the ball becomes in the middle, which is what we want now. Or if the ball is to the right and I move right, the ball is now in the middle, which is what we want. Again, temporal induction and conjunction derives these goals. We can simplify with the motor ops out of there, which just gives us, when we receive a sensation that the ball is left, it will simplify this term out of the conjunction, leaving only a goal to execute the operation. And so in that way, when the ball is to the left, NARS derives, I want to go left, and it will do so. And this simple knowledge base will derive or covers all the possible sensations and is sufficient to play Pong. And that's all. Thanks for your attention. And if you are interested in this version of Pong, you can download it here, or I encourage you to download NARS and actually build your own application.
Question.
Yes.
Can it actually derive the prediction of if the current position and speed is like this, so and where should it be at the time of the intercept, so that it won't have to follow the ball every time,
Oh, you're saying it's coming at this angle,
and I need to move here.
Yeah. Because the sensor is so simple, it has no perception of angle or anything like that. All it knows is the ball this here, here, or here. So the sensors are too simple. Theoretically, you could set it up though that way. Yeah.
The frequency of sensor input that is controlled by the logic that you write, isn't it?
Yes. And normally you'll just give a frequency of 1 because it's an event that's happening in the world. So you say this is true, this is happening. But you might not give it a very, very high confidence because like we mentioned, once you saturate out the confidence at the maximum level, you might run into issues.
I meant to the frequency at which you will input the sensor input.
Sampling frequency.
Oh, yeah. It depends on the temporal resolution you want for your application. So in this case, I'm inputting every third of a second, which is sufficient because the ball, every third of a second, it won't move very far. But if the ball was moving, say, very, very quickly, I might want to do it 10 times a second or 20 times a second. So it really depends on your application.
Okay, thanks.
Any other questions?
Yeah. So is it possible, or well, probably it's not possible yet, but how would you pursue something like if you want to motivate additional? Oh, you're doing a really good job now. But from kind of third party feedback.
Sorry, can you rephrase?
Would it be possible to motivate NARS agents does a good job, not by observing the environment, but by kind of social.
Oh, like a reinforcement sort of, or a reward?
For instance, yeah.
The completion of the goal itself is sort of the reward. So when the goal is not satisfied, the system is going to be working really hard to figure out how can I satisfy this goal. And when the goal is happening, like if the ball hits the paddle, then the goal is now satisfied and NARS won't process it anymore. It says, okay, I'm done with it. This goal is complete. I'm done. And it can move on to the next one. And so you could have various motivations and then it will go focus on the next motivation.
But it's not possible to have two motivations at the same time?
Yes, it will. It will flip between them, or if one goal is very important in the current moment and the other one not so important at the current moment, then it will focus on the important one and then leave the other one. But if, let's say you have two goals, like if you want to do two different things at the same time, then it will alternate between perhaps Does that answer the question? Great. Yeah.
So I don't know if I've understood correctly, but it sounds like you would get because it's prioritizing things and it's not going to get stuck in all change routines based on the system you're basically. Well, you give it so many inputs, it's going to, process things so many times. So if you sort of, I suppose, can you increase the sort of frequency with which it sort of perceives and processes things, and does that affect the results meaningfully?
Like you're saying, can you speed up the NARS?
Yeah, basically.
It'll go as fast as your computer goes. So you get a faster CPU, you can speed it up. Yeah. You can also arbitrarily slow it down if you, for some reason, wanted your system to run a little bit slower.
Did you do any experiments with that? Did it change the outcomes a lot?
Let me think. Yeah, so I did put a couple of delays in between. I actually slowed down the system a little bit. I found it helped it work better, simply due to the event logic. So the events decay, the confidence decays over a certain amount of time. So like to have the events decay more quickly was better in this case.
Wow, that's cool.
So you do have to tinker a little bit. You can also set up like an automated system to change the parameters, perhaps like an evolutionary algorithm to optimize those hyperparameters. That way you don't have to tinker yourself.
Yeah.
Question?
Yeah.
In the previous slide, you had like these concepts like ball left, center. Which of these are like pre-programmed, and which does it learn by itself?
So this is pre-programmed.
Yep.
Because that's coming from the sensor. Okay. This conjunction here is learned by the system, and this whole implication is learned automatically by the system. And it does that simply because these two events occur at the same time. So we can do a conjunction. Yep. Because we're saying this and this, right? And this happens afterwards, so we can say if this, then this.
So on that point, roughly how many inference steps does it take to learn these things? Okay, do you have an idea? Like, is it like how much babbling and how many inference steps? I'm guessing thousands, 50,000, or?
In terms of inference steps or working cycles, I can't be sure.
How about time? How long does it take?
So based on the video, I sped up the video a little bit. I think it took like 3 or 4 minutes only. But that's in very optimal conditions. Like I said, sometimes the ball will, not do exactly what you want it to. Right. And sometimes the system will make incorrect associations like, oh, I babbled right. And then the ball was left, but it was coming at this angle, so it hit me. So maybe now the ball's left, I move right. It's going complete opposite direction, which is incorrect. We don't want that behavior. But, due to the perception of the system and its limited sensors, it might make those incorrect associations. And then it would take longer, like 10 minutes or so. But, eventually, with enough revisions, it will get to the right place.
It's probably more a factor of the physics of the game, right? Not the speed of the component.
Yeah, and also the like resolution or intricacy of your sensor.
Right.
Yeah, if you run the owner Pong demo, it runs so fast that you can't actually visibly watch it, and it will learn it in a few seconds. So this is highly constrained by the speed of the graphical UI.
Yeah, that makes sense.
And also, is if the ball is doing what you want it to or not.
Are you considering additional experiments where you add complexity, obstacles, you add, or are you kind of considering this a dead?
Well, I was considering adding different sensors. For example, this is only left, middle, right, but maybe something like top, middle, down. Or, like adding quadrants, like when it's in this quadrant, then light up that sensor or event. So you could have like 9 different sensors. And so kind of increase the resolution.
Right.
Doing something like inputting the entire visual image is still out of the question.
Yeah.
It requires further research, but
maybe the paddle could move not just in the line, but maybe a little bit of, you have some obstacles that the paddle require, learning to move around a little bit.
That'd be a different game.
Yeah,
maybe.
different game.
You have to design the game, but yeah, of course.
Well, they're minor changes, right? You want to just add some complexity, I think.
I agree completely. And that was my idea for the next step, would be to add something like quadrants for sensors. I just have not gone to it. Thank you.
Thank you.
Yeah. As for the assumption of limited knowledge and resource. The limited knowledge means at the beginning is know nothing, and does the limited resource just mean the limitation of the sensor and not the inside computational power?
So when we say insufficient knowledge and resources, it just means that the system will like continuously learn, and it like it won't assume that it has all the knowledge that it needs. It's going to be taking in various pieces of knowledge, like even things that are of lower priority, things that it might not normally consider for like optimality. It might like try different things that might not be considered optimal, that might later be found to be optimal. So when we say insufficient knowledge, it's more about the system continuously learning.
What about the resources? It's just the limitation of the sensor, or include the
resources? Insufficient resource?
Yeah.
In that sense, we're just saying like the system can't, we can't ever guarantee that the system will be able to have all the resources it needs to solve a problem. Sometimes it needs to think about a certain problem and then move on to the next one. Otherwise it will, like I mentioned about Shaky the robot, which was, had issues because it would get stuck in these long chains of reasoning. We can't assume like, oh, we'll eventually get to the end of this chain or anything like that. We have to say, okay, we'll do a single step of this, but we're not sure if the knowledge is sufficient to fully solve the problem. So we might go focus on other problems. So it's really about resource allocation, computing resource allocation.
Because in this demo, I cannot allocation of computing power resources.
It's not necessarily with the demo. It's more an assumption about NARS itself, more like a theoretical design assumption. If it helps you to just disregard that and just focus on the application, it might do that. But in terms of like design and theory, then that's important.
Yeah, did I understood it correctly that NARS can't deal with numerical values at all, like quantities, coordinates, all this stuff?
That is something we're experimenting with. Patrick, I know, has experimented with quantities using like numbers as terms. So like it might have a concept for a number, like concept 1, 2, 3. And then it can use those as terms of reasoning.
Yeah, with operations.
Yeah. And we've also experimented with using truth values to represent quantities, but that's still experimental. Good question. Oh, a lot of questions. I love it. Very good. All right, well, if that's it, then we will move on to the next part, which is Patrick's hands-on example.
So, I think before we dive into the hands-on example I wanted to give you, I just want to give you also an overview of what happened in the last years with this project, where it's heading. If we look back, I'm here at Stockholm University since September 2021, and I have actually this implementation which Christian just showed. Openness for applications has been developed since the first release was 2020, but it has really taken off from taking a lot of ideas from openness and trying to build a NARS system which can be effectively used for various application purposes. And a lot of these ideas which contributed to this system were actually back in my PhD. During my PhD with Dr. Bai Wang, and I had the honor to be his PhD student and to develop many ideas which made this this implementation possible. And I also have to say a huge thank you to Hugo Latterby, who funded us over many years and made this project possible in the way it currently is. And there's really, with every technology, it needs some time to develop, to get to really unroll its application potential. And I think the same is true with NARS. And during my PhD, it was especially a big focus on sensory motor, since personally, for me, I was always convinced that that to go to a human level is not a piece of cake. And even in animal kingdom, we see animals which can do very impressive feats and adapt to new situations and cope with various difficulties they face in their environment, learn to adapt to them in ways I wouldn't even have imagined that a bumblebee, for instance, could learn to put a bore into a hole simply from observation. It's not even reward-driven learning in this case. It watches another bumblebee, and from this learning from observation, it's able to do this behavior. And for me, as an AI researcher, I want to make sure that on the way we are trying to take, that we will actually be able to explain some of the capabilities which are demonstrated by various animal species. And that's actually not that trivial to make sure that we actually cover these abilities. And I think a major aspect in this regard is to look back. What do we really need? What does an AI system really need to have to be able to explain the capabilities which we can see in nature? And I think a large part of this is if, for instance, in machine learning, there's a lot of focus on reinforcement learning. It's really great work, but we also have to look at what do we actually need? Is there maybe more to it? Are there some phenomenon which we also need to explain? And for me, during my PhD, it was especially when I worked at sensory motor that I noticed the importance of causal relationships, that an agent can actually learn behaviors which not only lead to a certain reward value, but actually to an understanding about what would happen in the next situation. What happens if we do a certain thing in a certain situation? What's the consequence of that? And this is a major part of learning from observation, because if you learn from observation, there is no reward just yet, but there's already a lot of information you can take in and then utilize in the future to make certain outcomes happen. And for years, it was really just a struggle with sensory motor. How to even get the most basic learning abilities to happen in the machine, things which are started with insects and with mice. And I was really into this thing and trying to make this happen in the machine. And there was this kind of background assumption that, yes, maybe we want causal relationships, we want some way for it to learn behaviors where the system really learns to model what's the consequences of its actions in different contexts. And since then, the NARS project has really gone a long way with various robotics applications where we can actually demonstrate some of the reasoning abilities which are studied with animals. And that's, at least I can say that over the years, sensory motor is something which works really well in NARS in the meanwhile, even though it started as a model which is mostly concerned about the like conceptual reasoning. You have seen today the introduction of the non-axiomatic logic levels, and for many years we had implementations which could really reason very well on declarative knowledge, yet couldn't yet act in the real world because certain sensory motor capabilities were not yet present. And in this regard, the project has made really big breakthroughs in the recent years where we can really say, yes, the system can reliably learn sensory motor behaviors, even in situations like real-world situations where it needs to apply them. And that's a huge breakthrough, of course, from from the perspective that sensory motor is somewhere at the bottom of human level AI, it's of course still a small step, but it's a step that at least I always thought to be necessary to get to human level AI. Of course, there is some disagreement whether to what degree sensory motor capabilities need to be present in an AI system. But at least this part is working relatively well in the meanwhile, with various examples where we can actually demonstrate this. And more recently, we have focused more on the relational reasoning side of things. Like if we look back at this slide with the animals, like here, Alex the parrot, you might know this kind of parrot from Irene Pepperberg's lab, which is able to answer questions about objects. In English, it's not really mastering human language, but it has learned to some degree the meaning of certain words it gives. Like it can really count how many green objects are on the tray and give you an answer to that. So even though it doesn't have the human language capability, it's able to have some kind of correspondence between the words and the things it sees, so it can actually answer the question. And Irene Pepperberg really showed in her study that the parrot it's not simply parroting, but really understanding what it needs to answer, really the essence of the information that is asked about, that it can actually find the right answer to the questions. And from our perspective, okay, sensory motor, if this is there, then the question is, how can we reach the other capabilities? How can we get verbal abilities inside relational reasoning on a high level? And there's still a lot to be done, but also there we had progress. You will see today in the afternoon, where, for instance, we have combined our system with large language models, where we essentially try to combine the strengths of both approaches, so that essentially the large language models are used to translate English sentences into this formal language of the system, and then letting the reasoning system carry out the reasoning reliably, and so that question answering can then be performed on natural language input. So we also made some progress on the more human level end of this story, but also on perception and sensory motor. There's of course still work to do, but this is where we can really say we closed really a gap in the recent years, which was that like 2014 and earlier, you could not expect back then that NARS could, for instance, learn to play a computer game. But now you can do various things with the system, and I will give you some hands-on examples so that you can also see how you can actually utilize the system in various applications for yourself. And also, since it directly connects to what Christian has shown with the Bong application, there was this question, can it actually handle numeric input? Can it actually not just have this left, middle, right, but could we actually feed the position, for instance, into the system? Could it do something with that? And we have an example which we call the Band robot. The visualization is maybe a bit lacking, but what you can see here, this is a robotic arm. This is the object to pick. This is the position it has to drop it at. It's started from scratch, empty memory. It receives the location of the arm, the location of the target, and the target location, and the location of the object to pick. And we will see it does. It's actually also just a matter of seconds or sometimes minutes for it to learn this task. So you see now this learning process unfolding. Hopefully it will work. Built various of this hypothesis, which Christian has shown, which is like a precondition, action, consequence. And in this case, it's relational of a relational form, because it needs to compare what is the location of myself, what is the location of the object, what is the difference? Is it to the left? Is it to the right? So in this case, it's not information we feed it, but it's information it derives from this numeric input information. So we have also made progress in allowing this reasoning system to obtain numeric information, like from sensors, building comparative relationships on top, and then utilizing these comparative relationships for both learning and decision making. So here you see this process. It looks like it has already, maybe not yet mastered, but pretty close of sometimes exploring and doing water bubbling, but it got the essence of the task, that it needs to put this into the horror. So you can see this has learned this task and has now done this in a way that relational knowledge is utilized, and this relational knowledge was not given to it, but it has built this on its own. So this goes directly to this notion of extending sensory motor capabilities with higher level reasoning abilities, so that we can, for instance, explain things like this, where the bumblebee learns to put the boar into the hole. And this is, of course, a simplified version of this task. It has some parallels. It's, of course, simpler from a perceptual perspective, which is also the reason why we are also exploring our work in the context of robotics, to actually show and demonstrate that this is not just something which works for a simple simulation, but you can actually use this capability for real-world applications. Question?
Yeah, could you maybe go a bit more in depth how the sensory channel looks like in this example? Like what kind of data is being fed into NARS?
The good thing is there will be this afternoon in the workshop, we will go into all these advanced capabilities which we have developed in the recent years, like sensory channels and how to connect with sensors and actuators on real hardware, and also various topics like how to make the system scalable. Like it's one thing to have a reasoning system which works for a few toy examples. It's another thing to set it up in a way that it can continue operating, having persistent memory, potentially multiple reasoning instances operating on the same memory, on the same kind of graph knowledge database, so to speak, and essentially making a system which can run reliably over a long time period, which is really also the idea of NARS is that it will not just be restarted every time solving a simple problem and then getting deleted and re-instantiated for a new problem, but we really want to get to a stage where this system can run for years, essentially, learn new information and extend its knowledge for various applications, essentially. So we are getting closer to this goal. You will see in the afternoon that we have made big progress in terms of how to have persistency of memory, how to connect with robotic actuators and real-world sensors, and how we actually encode the sensor information. We will go into some of the details this afternoon. I just wanted to give you a good overview of what has happened in the recent years for this project, and also, of course, keeping the long-term objective in mind. This is actually meant as an AGI project, which at some point ideally would run for years and keep learning new knowledge and improving its capabilities. So that's this part. The other part of what I wanted to show you is how you can actually utilize this system for your own purposes. The first part here is how to download and install the system. You can simply get it from GitHub. So if you have like a new directory, you can.
The text a bit bigger, please, Patrick.
The text is a bit small, I have to admit. So we're in a new directory, so we can now. Is this better? Is it still a bit smart? So you can simply clone the project. And then you enter its directory. There's a build script, which you can run, build.sh. It's on a M1 MacBook, it will tell you there is no such thing as SSE, but like a processor extension for processors, Intel processor architecture. But here it will just proceed with compilation without the flag. So the warning should not concern you. It's just telling you that SSE is not present on your processor, but that's fine. You have a M1 MacBook or ARM processor. So if it has compiled it, and if you start the generated executable, then it will run tests, and it will ideally will tell you that all the tests run successfully. So at this point, you should be good to go. So it's really straightforward to get started with this system. You just need to clone it and execute the build script. You will need some C compiler, GCC or CLang, and then this will work. In terms of using the system, it depends. If you simply want to interact with the system, there's something called the shell. So you simply pass shell to the executable. You can also colorize it by piping it into the colorizer script so that you get nicer output. Like if you say cats are animals, still a bit small, right? A bit larger. So this is what we input, and it says it has accepted the input. And also ask it questions like what is an animal? And it will say cat, for instance, is an animal. So this is just how you can start up the system and interact with its shell. But maybe if you're interested in how to utilize the system in application, then it's also quite straightforward. You can create a new Python file and put it into the MISC Python folder of the project. And then you can just give your Python file some name, test1.py. And all you need to do is execute this line, and you will already have the system running, and you can already say what you want to input to it. And the way you provide input is via this add input function. So you can simply say now add input. So we can do the same thing we did here with the shell, but this time we use the Python interface. So if we do this, if we execute the script, so MISC. Run. Do the same thing you saw before in the shell. You will also get this printout. If you don't want the printout because you're maybe creating a shell application, so maybe you don't want it to print what you have input, then you simply put print equals false here, then it will not print it. And what you can do, for instance, same as there, we can, for instance, ask a question to the system using the same at input. And you will see the answer output here. But maybe we don't want that. We want to make use of the answer in the code for some application. So we again set print equals false. We don't want it to be printed in the shell. So how to get the answer to the question? which is we can simply get the return of this add input. So this will return you a Python object which contains the answer we have seen. So if we look at this, what did it actually return here? You see it's a dictionary which contains the input, which is the input question, and it also has a key in there which says answers. And here, the value of this contains the question, the answer to the question, which is that cat is an animal. So you simply have a Python object which you can use, it's just a dictionary. So we can do this, we can get the answers back. We want the first answer, and if we print this, we're already there. We have all the information, occurrence time, stamp information, punctuation, the term, and the truth value of the answer. Maybe we only want to see the term and the truth value, so we can say the term, so this is the answer, and the term of the answer is simply answer, the term of the answer, and the truth value is the truth of the answer. And maybe we want to print the term and the truth of the answer, so we do this. We wanted the first answer, it told us because it's a list. So we have now printed in our own way the answer to the question and its truth value. So you see it's very easy to utilize the system in a Python program and feed it information and get back answers to questions. And the second, there are essentially two major things you want to do in applications. You want to get answers to questions. And the second thing is you want to see when the system wants to do something, when it wants to invoke a certain operation or actuator. We can also create an example for this. We can input some procedural knowledge. Let's say something like in the robot case, if there's a bottle in the front of the robot and we want to pick it, we want the system to pick it up. So if there's a bottle in front and we pick it, then say the mission goal is achieved. And so if there really is a bottle in front, which for instance might come from some sensor, like if we have an object detection model, we will see the details in the afternoon. So you can have an event like this. And then let's say you want the system to get this mission objective achieved. So we have all the information here. Some window is a bit in the way. But we already see, okay, it executed the pick operation because we told it there's a bottle in front. So again, it's printed out. We don't want it to be printed. We can again say print equals false. Everywhere here. And we can again get the return of this car. And this one includes the pick operation. So if we look at print, if we print the return value, we will see there is derivations. We are not interested in derivations. We are interested in the
fourth to last line. Further down.
One window is in the way. Yes, we're interested in the
It's further down, Patrick.
executions. There it is. Okay, so here you see here you see what it did. It has returned the executions, the operator it has invoked, which is the pick operation. So if we want to get this, since it's simply a dictionary, we can again do executions. If we print this, we get this operator pick. So we're almost there. So you see, actually we are there. So we have what it executed. It executed pick, and there were no operation arguments. One can also have operator arguments, but you see, it's very easy to make the system do something in an application, feeding it information and getting back what the system wants to do, and then having this output operation, for instance, in the application might do then, it can then do various things dependent on what you wanted to invoke. For instance, in the robot case, in this case, you wanted to pick up the bottle, for instance, so invoking actually motor command. So it really depends on the application, what the operation will actually trigger, and it's very easy to interact with the system in the code and to develop application using this pattern interface. So that's a way how the system can be used. Maybe I also want to briefly mention, since it's really important from this roadmap perspective, Robert Johansson, for instance, my postdoc advisor, is using the system to carry out various experiments, psychological experiments, using the system. So essentially trying the system on experiments which are typically carried out with animals and with humans, just to see and to evaluate our progress on this roadmap of realizing more advanced cognitive abilities in the system, and whether we're evaluating essentially how well we are doing on this ladder or roadmap. So, and he's also using this pattern interface essentially in the experiments. That there are also some experiments programs like OpenSesame, which allows you to design psychological experiments and simply invoke the system via pattern. So also there you can simply invoke the system using this pattern interface, so that you can set up an experiment which can both be carried out by the human and also be compared with the system. Which might matter because, interestingly, for us, it was the most interesting cases is when the system's decisions and the system's hypothesis mismatch with that of the human, because this gives some indications either there's something missing, or we do something differently than the human mind potentially. And these experiments allow us to find out to what degree is this the case, in what kind of situations does the system behave differently or utilize information differently. And so that's the roadmap we have taken essentially. Are there any questions regarding the usage of this system? Okay. Then I guess this hands-on part is almost complete. I'm not sure how much time we have left. Another 10 minutes or? Then maybe I can show you some of the other examples which are also in this code base. What's really also a design goal of the system is to have a common set of parameters which we use across different examples essentially. Because often in machine learning it is a common practice. For instance, you take a Q-learner, you find some hyperparameters which work well for the domain, and for different domain, usually you use different hyperparameters. We force ourselves to find parameters which work well across a wide range of examples. So we don't want the human in the loop finding hyperparameters for the system. We want to come up with hyperparameters which work well in many situations. And maybe there's something I can show there because it's interesting from a theoretical perspective. It's working. So what we have, for instance, been doing, this was actually at the end of my PhD, was to see, is this model actually an alternative to reinforcement learning to some degree? Can it learn these causal relationships or this precondition action consequence relationships reliably enough so that it could, for instance, compete with reinforcement learning in typical reinforcement learning scenarios? And there are a few findings which we found which are quite interesting. And maybe here, for instance, here Bong-Tu, labeled it Bong-Tu. What's interesting about this particular example is it's an example which shows that even in very simple environments, you can break some of the assumptions which are often taken in reinforcement learning. For instance, Markov assumption of the environment and in this case, what we had is we added we have again the Bong scenario which Christian showed essentially, and there is a stop operation. And if the system does not call the stop operation, it will continue going into the direction which it has invoked like a few time steps earlier. So this setting is already non-Markovian because what the system will see next is not just dependent on this thing it has seen in the last step and action it has invoked in the last step. It also depends on what it has done earlier. So it's already non-Markovian, and you see for our system here it's labeled master. This is owner, openness for applications. It's no problem to be in this non-Markovian setting, but if you have a Q learner which takes this assumption, it will struggle in this domain. Of course, if you change the problem and make it Markovian, then you can get similar results with the reinforcement learner. But it's interesting to see from a generality perspective, if you give a problem to an AGI system, ideally, you don't want to find out if it's Markovian or not and then tweak around and somehow make it happen, that it can deal with it. Ideally, you don't want to fiddle with parameters. You don't want to fiddle with the input encoding much. You just wanted to learn the task, right? So it's always good if certain assumptions are not made in the first place. So this was interesting to see. But we will see more of this in the afternoon. I just wanted to give you some initial feeling about what we have done, about different things we tried to do essentially, and the progress we have made on this way. That's one thing. I think we have a few minutes left.
Question.
Uh-huh.
Can the system be trained to like predict the future scenarios, like in game of chess, for example? If you know the rules of the game, then playing the future scenarios, like if I do this, the opponent is going to likely to do this, or these are the options. And keep thinking forward rather than just referring to the prior knowledge.
Mm-hmm. Yes, and also here it's the key is that the system can learn these temporal relationships, which allows it to reason about the future essentially. So as you say, it's able to not only think about what it's currently seeing, but it can also take into account what it predicts about the future. And this is also important. This is important, for instance, in various examples where it needs to plan ahead, where it needs to come up with some strategy which involves future possibilities or even actions of other agents like in this game scenario where maybe there's another agent in the environment and not only itself. The system is prepared to do that because of this causal representations. From a control perspective, it was only about 2 years ago that we made some major progress in terms of inference control for planning purposes. So essentially, like actually we're in the red folder here, so I can at least show one example here. So in this example, it's essentially just planning what we see here. There's a grid, and all it has to do is to get to the target location. So that's not very impressive in principle, since it's only planning, right? But the great thing about it is this planning is done using NARS, using its ability to learn these temporal relationships and doing that on top of that. And that's powerful because it means if some of this procedural knowledge is wrong, it will adapt to it. It will see it doesn't work. So it gives you both. It gives you this learning abilities, which is really great about reinforcement learning. And it, on the other hand, it also gives you this ability to have a system which can plan into the future what to do and reach outcomes dependent on what it wants to do currently. So it's how to say, so it was to some degree a breakthrough, because also here we don't invoke the system in a certain way here just to make it plan. It's the same thing, the same input, the same hyperparameters, the same system which is invoked here, like it's invoked in all the other examples. So just giving it information, giving it course, and letting it figure it out. And it's the ability to plan ahead is simply part of its capabilities. So it's not something we as designer have to set up so that it will actually use it. So from that perspective, it's also different from cognitive architectures traditionally, like SOA and ACT-R, which was more like a programming language, essentially running on top of a cognitive structure. Like you have memory structure, different types of memory and so on, but you as a designer needed to encode how to solve needed to encode the problem and which cognitive machinery to use to solve it, essentially. Well, here we just feed it information and we leave it up to the system whether it will plan ahead or whether it will react, make actions more reactively. That's up to the task. Some tasks demand looking into the future further to make good decisions, while other tasks really demand a really quick response. And so it's really task dependent and leaving it to the resource allocation in the system to control what kind of reasoning it will carry out to be successful. That's about this. From a system development perspective, in case someone is interested in how the system is structured internally, we will see in the afternoon like how it's actually working inside. Because of course this all raises a lot of questions. How does it actually do this resource allocation in detail? How does it manage its memory and so on? We will have a more detailed picture in the afternoon with the workshop presentations. And if you're more interested in the code itself, there's also a code documentation available where you can at least see the overall structures and modules which are involved in the reasoner. This is a bit of a traditional implementation. OpenNARS Publications is written in the C language. It's not a very usual choice to write a reasoning system in. Of course, it gives you some portability and efficiency benefits, but it's of course not the first language choice everyone would take. But it's at least highly supported and run pretty much on any OS or even without OS if you want it to run on a microcontroller. So that's at least the case I think we are right in time. We are now out of time. 12:15. Right. So thank you. And we will.
So I'd like to thank you all for attending and for your attention and wonderful questions. One of the best workshops that NARS workshops that I've seen. So thank you very much. We'll see you in the afternoon for the workshop session.
What times are we at? We've got the sheet with the times on.
I have to look at the website. Sorry.
In the future.
It's very interesting. Yeah.
You're Chris, right? Yeah. I recognize you from your photos.
So you get the presentation.
Oh,
One second.
You need to turn this.
Right. Hi everyone. So we're starting the workshop. My name is Peter, and myself and Patrick will be running the workshop. So there will be quite a number of speakers today, about 6 to 7 speakers, and the workshop will be until like 5:30. So thanks for joining us, and I will give the first word to Peter Voss, and he will tell us his presentation about why we don't have AGI yet and what's necessary to do that. Right? Please.
All right, good morning, or good afternoon, I should say. So what I want to talk about really is what is AGI and why don't we have it yet? So I'll actually start by just, not all of you may know actually why we have the term AGI. So Ben Goetzel, Shane Legg, and myself coined the term in 2002 because we felt that AI had lost its way. When you go back 60 odd years, when the term AI was first coined, it was all about building thinking machines, machines that could think and learn and reason the way humans do. And the original founders thought they could solve this problem in a few years. Well, it turned out to be much, much harder than that. So over the decades, what happened is that the AI morphed into really narrow AI, where it was solving one particular problem at a time. But there's actually a very important problem with that, because what happened is that it was really the human intelligence that figured out how to use computers to solve that particular problem. So, for example, we had the breakthrough of IBM's Deep Blue becoming the world chess champion. But it's really the intelligence of the designers on how to use computer power to play a powerful game of chess. And that's been the story of AI really along the way. So in 2002, a group of us got together and we felt it was time to go back to the original dream of AI, to build thinking machines. So I'm particularly pleased to be talking here in the NARS Workshop, because I think NARS is one of the very, very few systems approaches that really tries to stay true to the idea of AGI. So about 15 years ago, Ben Goetzel, gave a presentation and said, we can, if we try really hard, we can have AGI, human level intelligence, in 7 years. I think I said something similar in a presentation. Well, that was something like 15 years ago. So why don't we have AGI yet? And I think to give you a quick answer, and obviously I'll go through the detail, the quick answer is I don't think we've had sufficient funding and focus on the right approach. I think it's as simple as that. So why do we want AGI? I think that helps to explain what an AGI should look like. So imagine having billions of PhD level researchers, whether it's cancer research or energy or whatever, that can chip away at these really, really difficult problems. You know, we are struggling with some of these things that are so complex. So if we can train one AI to be a cancer researcher and make, you know, 1 million copies of it and go off and work a different aspect of it, that I think is incredibly value to improve the quality of life of humanity. So cure diseases and aging, cheap, clean food, water, and energy, restore the environment. Now, the next two, I think, are, to me, as important, if not more important, to have smart, unbiased moral advisors. You know, this sort of brings to mind a little angel you could have on your shoulder that could help you make better decisions or avoid foolish decisions in your life, that could guide you away from the misinformation, bad decisions, so on, and vastly improved social systems. I mean, our political systems, I think most people would agree, are quite a mess. Certainly in America, yeah, okay. Well, I don't think I want to get too deep into that, but I think it could use a lot more intelligence. So in addition to it, you know, just a reminder, I think all of you will know these things, but what are some of the super desirable AGI characteristics, you know, that over and above humans? Well, they're much cheaper than humans once they are mass produced. AI can be incredibly cheap. They can communicate with each other much better than humans do. They don't have egos getting in the way, and they can communicate much better. I mean, they can basically share ideas by transferring a file or, you know, stuff like that. They can work 24/7 without getting tired. They don't have certain distractions that humans tend to have. And they have perfect memory, potentially. They have access to all of the information in the world instantaneously, and they are much better at reasoning than humans are. So what do we mean by AGI? And there's a lot of confusion. I mean, I read a lot of articles that say, oh, nobody really knows what AGI is, or the term is too fuzzy or whatever. Well, I don't think so, you know, and, you know, we can drill down on what it should mean. So you quite often read that there's sort of godlike, unlimited AGI, that AGI can solve any problem. And this would be the kind of roughly in the school of the mathematical logic one. So I think of AI-XI, for example, Shane Legg's approach. We have a purely theoretical approach and say, if we had unlimited computing power, we could solve any problem. Now, that's nonsense. A, you cannot have unlimited computing power. And B, even, I mean, you can't have it full stop. So secondly, there are many problems. In fact, I would say most problems in the real world are intractable. It's impossible. It is practically, theoretically, totally impossible to predict exactly what the weather will be 3 days from now. You know, and I mean, this is all over the place. In the real world, you cannot perfectly predict the future. So that already, you know, and medical systems, all that. Anyway, there are many intractable problems inherently in the world. So no, you cannot have omniscience in that. That's not possible. The second idea is collective intelligence. And there are some people who believe that if we have enough narrow AIs that have all these different skills, and we somehow put them in a swarm or together in a society or something, that will give us AGI. Now, it's a more subtle argument to debunk that, but no, you cannot achieve AGI by just having a bunch of narrow AIs, and I'm certainly happy to debate that, but I don't have the time now. So it's human-like cognitive abilities. And, you know, simple test would basically be, you've achieved AGI if you have an AGI that, if you have a system that can learn any cognitive skill that, you know, an intelligent, average intelligent human can have, or maybe above an average. So that means, you know, it could learn any secretarial job, it could learn any management task, and, you know, really any task that a human. That would be kind of a benchmark. Again, going back to a PhD level researcher, it should be able to learn that with roughly the same kind of interaction or less than a human has in learning it. So they could hit the books, they could ask questions, and so on. That to me is AGI, basically human level cognitive abilities. So ability to learn wide range of new knowledge and skills autonomously, any cognitive skills that an intelligent human can learn. So it will, of course, be superhuman in many ways. I mean, they already are. So, but that's in certain areas where computers will be stronger at. It can certainly specialize and be part of a collective. You know, if you have these cancer researchers, you train one with basic skills, they will go off in different directions and specialize, because it would make sense. They would then be able to focus their energy on particular sub areas. Now, the third bullet point is, of course, NARS assumes limited knowledge and resources. So the input you get is never going to be complete, it's never going to be totally accurate. You'll always have limits in resources, in time, how much time you have to solve, to work on a problem, how much computational power you have. So your system has to be inherently capable of working with bad information, fuzzy information, with limited time, under pressure, so to speak, and still be able to make progress. So it has to work in real time. It can't take 3 weeks to train some kind of a model or to get a new skill. Now, I like to describe it as a Helen Hawking model of AGI. Some of you may recognize Helen Keller, and we have Stephen Hawking. So you can be perfectly intelligent with very limited sense acuity and very little dexterity. So our AGI does not need to have human level dexterity or sense acuity. Again, I don't want to spend too much time with these points because there's quite a bit to go through. It will inherently be a tool user. So your particular copy of an AGI may not be that good at chess because it hasn't spent the time or whatever, but it knows how to use a chess computer. So tool use is an extremely important point. I mean, that's what makes us humans, one of the things that makes our human intelligence so important. But it needs to go beyond language. So, you know, ChatGPT by itself is not going to cut it, because you do need to interact with the environment. You definitely need vision. I mean, if you're going to hit the books and read graphs and diagrams and things like that. So roughly, I think one of the good compromises there in terms of sense acuity would be a computer I/O. If it could totally make sense of what is on your screen, you know, obviously including video and stuff, anything that can come up on your screen, and it can manipulate mouse and keyboard perfectly well. You could do a lot with that. You could really do a lot. You could control other robots, and, you know, you could basically have a window into the real world through that. So now my starting point in AGI has always been, you have to understand intelligence first before you can build an intelligent system. Now, of course, I have people say, nobody knows what intelligence is, you know. But quite frankly, I say, speak for yourself. You know, you need to understand intelligence well enough, at least, to be able to build it. You need to have some version of intelligence, or some, you know, definition of intelligence to be able to build such a system. I think that's one of the problems with AI research, is we have very, very few people, especially since we've had the success of deep learning, machine learning. We have very few cognitive scientists in the field, very few people who are philosophers and understand epistemology. We basically have statisticians, logicians, mathematicians, who really aren't interested and don't have the background, they don't have the framing of cognitive science, which I think is really necessary to understand intelligence. So practical human cognition, intelligence, what does that entail? How does it differ from animal intelligence, for example? So you need to be able to learn and integrate new skills and knowledge. So knowledge, more static things, but skills as well. And then you need to be able to do that in real time. Whether you're reading a paper, a book, you're talking to somebody, whether you come across a news scenario in running a business or whatever, you need to be able to learn interactively. You need to be able to integrate that in real time. No offline learning, or if the offline learning would be supplemental. It requires context, short-term memory, long-term memory. So whatever you hear and see, you need to interpret within the context of who you're talking to, what else they know, what you know, what was said before. Context is extremely important. A system that doesn't utilize context cannot learn effectively. You obviously also need long-term memory, because you need to be able to learn things and permanently use them. So again, something like large language models only have sort of short-term memory, but it doesn't get integrated into the existing knowledge, and they don't have long-term memory. The ability to form new concepts. So in fact, what makes human intelligence unique and separates us from animal intelligence is our ability to form abstract concepts. Animals can only form concrete bound concepts that are directly tied to perception or very closely tied to perception. Whereas humans can form concept of concept of concept to come up with very, very high-level concepts such as honor, and marriage and things of that nature. So that's generalization, concept formation is absolutely crucial to intelligence. Reasoning and metacognition. Metacognition is the ability to think about your thinking, to have the right approach in your thinking and have control of your thinking. That would also include, metacognition also includes things like cognitive emotions, or what I call cognitive emotions. Those would be things like uncertainty or confusion, which are emotions that an AI needs to have. Let's say whether you want to call them emotions or metacognition. So it needs to have that. Kahneman talks about system 1, system 2. I think large language models are largely working at the level of system 1. You need that metacognition, the ability to think about your thinking, to reason about your reasoning, and to control it. And you need various learning modes. I think I have a list of about 12 different learning modes, but things like transfer learning, aping, zero, one-shot learning, and so on. So that's the starting point, is what does intelligence require? Now, if you are serious about building an intelligent system, you really have to ask yourself, is the approach that I'm pursuing consistent with what intelligence requires? Does it meet these requirements? Can it meet these requirements? If it can't, you're not going to be able to build an intelligent system. As simple as that. Now, one of the things I wanted to mention earlier, I'll say it now, is why, what are the reasons? I gave you sort of a quick summary of why don't we have AGI yet. And, the other reasons that I'm coming to here is that basically it's not taking intelligence serious in that. It's basically the motivations of people and the approaches that people in the AI field are taking are often distracted by, what do I need to do to get a grant? What do I need to do to get funding? Or what am I good at? Deep learning, machine learning is a perfect example. It's Google and, the big companies have a lot of data. They have a lot of computing power. So that's the hammer they've got. So everything looks like a nail. And, it's been super, super successful in many areas, but it's not AGI. And, that's why you have Dennis Hasabi saying, deep learning is amazing, but it's not AGI, not by a long shot. Those are his words. So these people realize, you're doing something. It's like looking for your keys under the lamp. It's kind of what you feel comfortable is, or what you need to do to get your next grant or your next investment, rather than doing what is required to get AGI. So here's another comparison: external intelligence. Even for things like deep learning, it's the external intelligence that makes things happen. It's what model do I use? What training data do I give it? What parameters do I tune? It's a human in the loop who makes the system work. How do I tune the meta parameters, or what problems do I give it? What training data do I give it? They're largely domain-specific, relatively fixed, rule-based or statistical, externally initiated improvements. Whereas on AGI, it's not having or coding knowledge and skills. It's not having the knowledge or skills that's important, but it's the ability to acquire and learn. Now, there's a huge problem with that, because any benchmark that you have is on the top left. So if you're building something that's good at acquiring and learning, none of the benchmarks that we have will really reward you for that. You're not going to get published, you're not going to get funding, you're not going to impress anybody. Oh, the system can learn, okay. But can it beat the benchmarks? Can it play ping pong or, whatever? So that's a huge problem, but you have to have that vision that it's not having the knowledge in the system that's the real important thing. That's a benchmark. It should be, does it have the ability to acquire, to generalize, to learn on the fly? Ongoing cumulative, general, contextual, adaptive learning, all key words. Autonomy and experience-based improvements. So DARPA talked about 3 waves a few years ago. They came out with this presentation where they speak about 3 waves of AI. I think it's a pretty good model. That's why I put it in here. So the first wave was what we now call good old-fashioned AI. So, for the first couple of decades, 3-4 decades in AI, that's really what it was. Expert systems, logic-based systems, psych, Deep Blue would be examples of that. So good old-fashioned AI. My graphic here is really for conversational AI. In conversational AI, you basically end up doing flowcharts. We all know what the problems are with that, combinatorial explosions and so on. Now, the second wave hit us like a tsunami about 12 years ago, when people finally figured out how to get neural networks to work, and spectacularly so. So that's the second wave, and we're still very much in the second wave. And this is the other problem. This has been so incredibly successful that it sucked all the oxygen out of the air. I had an intern working on our project about 8 years ago, a brilliant guy from Germany. He really got our approach, he loved it, and he was very good. He went back to Germany to do his PhD, couldn't find a sponsor. So he ended up doing deep learning, machine learning. So, we've lost him. Obviously, he's now going to be lecturing or working in industry on deep learning, machine learning. So, it sucks all the oxygen out of it. Try and get funding. You talk to VCs in VCs in Silicon Valley and in the Bay Area, and what, you mean you're not doing deep learning? Well, not interested. So the third wave, what is the third wave? The third wave is this adaptive thing. Now, whether you want to call it, I like to call it cognitive architectures. One can, debate whether that's the right term, but the hypothesis about fixed structures that provide a mind. So, basically what I've been talking about is, what does intelligence require? And does your approach, does your architecture have the components, the inherent ability? Is a design inherently geared towards meeting those requirements of what a mind needs? So first and second wave, frozen external intelligence. Third wave, cognitive adaptive internal intelligence. Now, this is a problem, one of the problems, and, my own company keeps falling into this because we go into a development stage and we spend a few years developing, and then, you know, we run out of money, and then we better commercialize something, and we dumb the system down. So instead of being able to pursue generality and competence at the same time, or even generality more than competence, you basically then say, okay, we'll just hard code a bunch of stuff here to get a more impressive product together and make it less adaptive. And we're using our external intelligence to basically achieve some more narrow objectives. It's a huge problem, you know, whether it's in academia or whether it's, you know, commercial on any project. You know, it even, I think DeepMind fell into that trap as well, because, you know, for a couple of years, I mean, they were absolutely smashing it with all of the new, really impressive demos that they put together. But, you know, I think they got swept up in, okay, what's the next big thing we can do, rather than saying, what do we need to do to get to AGI? So I think that's about as much time I have for it. There are many other considerations. I'd love to maybe have another session of people who are interested in exploring this. Maybe you can carve out some time and get together. I don't know who wants to organize it. But I mentioned already benchmarks and expectations. Huge problem. If you have a proto-AGI, a baby AGI, or even before baby AGI, proto-AGI, how are you going to impress anybody with it? You know, it's not going to be able to do anything very impressive. It's not going to meet any of the benchmarks, the traditional benchmarks. So we really need very different benchmarks to say, are we on the right track to AGI? And it's not going to be the existing benchmarks, because then you are going narrow again. Grounding, what kind of grounding does a system should have? Robotics is very nice. You can see it interacting with the real world, but obviously big problems with robotics. They're sexy, you can get funding for them and so on, but it's really not a very good way to go about it, because it's just like you spend 90% of your time struggling with hardware, and it's just very slow to do anything. So virtual worlds, virtual robotics makes a lot more sense to do that. And then there's sort of the pseudo grounding, you know, which large language models in a way have. They have, through their high level thing, they somehow infer grounded information. You can ask them about that. How much pseudo grounding can you get away with, or how little grounding interaction do you need with the real world? And so my suggestion was, if it can interact with a PC screen and keyboard and mouse, that might be a very good compromise. Representation, how do you represent the knowledge and skills that the system has? Is that some kind of a knowledge graph? Is it a black box? Is it a white box? Is it a gray box? You know, and, you know, I think NARS is sort of a gray box, or by the time it scales up, it would be, and maybe by the time any system scales up, it's not going to be totally scrutable, but it's also not going to be a total black box like large language models are. What is understanding? I've got quite a few articles published on medium.com. I mean, these links are horrendous. I didn't have time to give better links there, but, you know, what is it? Struggling with these things of what is intelligence, what is understanding. It really pays to spend time on drilling down on these things so that you know whether you're achieving something or you're not achieving it. That people just say large language models have no understanding. Well, really, by common sense definitions of understanding. So I think it's good to have a handle on these terms, you know, not to get confused. And the same with consciousness, you know, what does it entail? So I think that's all I have. I don't know if we have, I don't think we have any time for questions, but maybe we do, I don't know. Time for questions or not?
Yeah.
Yeah.
Two comments. One, you said something about animals where they only perceive their environment and they don't typically develop a higher level concept.
Right.
They have this thing out now with dogs and touchpads for words, and they're finding out the dogs are kind of gaining some intelligence and starting to ask questions. Have you heard about that? Or
No, I'm not familiar with that, but I've read a lot about different animal studies. And one of the problems you really need to watch out for is, you know, a lot of these sort of ape studies and you know, even parrots and so on, that humans often ascribe more intelligence, read more intelligence into behavior than is really evident. And it's especially the researchers that work with the animals. And there was one account that I read of somebody who was a researcher, and then he left the field and he wrote about how much they overinterpreted intelligence. You know, that a lot of these things like self-awareness and so on, that they really could be explained at a more lower perceptual level. But you know, I think that there's very easy. I mean, even the Alex the parrot that we have, you know, for us saying that he could count. No, he couldn't count. He could respond correctly only for a limited number of things he could perceive. So he could tell you whether he perceived 3 green things or 4 green things or 2 green things, but that's not counting as such. So it was, you know, direct perception.
And then the last comment was, I forgot who said it, but the person said, knowledge representation is the problem. It's probably the only problem.
Sorry, what is that?
Yeah, knowledge representation is the problem. You had a list of things.
Yes, you
said that.
It's too, well, if you're designing an AI, you need to ask yourself, how is the knowledge going to be represented? You know, on the one extreme, you could say, we have a separate knowledge graph engine or something, you know, where all the knowledge is stored. Or, I mean, large language models, you know, have a knowledge representation that you can think of it as a neural network, even though it's implemented differently. So it's a difficult problem. I spent several years agonizing over that, and we went through several iterations of how to represent knowledge, and certainly don't have all of the answers yet, but it's a really hard problem, I think, to decide how to be able to encode the uncertainty of information, the fuzziness of information, and so on. You know, they're not formal logic. I mean, formal logic won't get you there. But pure statistical systems, how do you work with them as an engineer if you can't pinpoint where stuff is, you know? And there are problems with the way large language models create that knowledge representation because, you know, I mean, if you go back to the word-to-vector representation, dog and cat is closer in proximity than dog and puppy. And, you know, you really don't have the representation of what's a relationship between a puppy and a dog and dog animal and so on. You don't have the hierarchy, you don't have the attributes. They may kind of just emerge out of the statistics, but there's no guarantee.
Yeah. You said about benchmarks.
Yes.
What do you think about abstraction and reasoning corpus? That's basically attempts to measure generality. It's not very famous because, again, neural networks.
Which corpus is that?
Abstraction and reasoning from Strashalet.
I don't think I'm familiar with it. But the more general comment is, as soon as you start focusing on the benchmark, then you're narrowing in to, you know, to be good at that benchmark. But yeah, I mean, it sounds, I'll look it up and.
Yeah, it's basically, it looks somewhat similar to IQ tests, but more diverse and more variable, and measures the ability to find complex abstract, combination of complex abstract rules from very few examples.
Right. Yeah, I think, in fact, I was involved in implementing a very novel IQ test. I spent about a year on that project in South Africa, which was actually an IQ test that doesn't have cultural bias. It has very little cultural bias because it was a huge problem in South Africa. And one of the unique features, in fact, that test would be good for an AGI test The only problem with that test is you can really only take it once because the novelty of it is really important. So it's you learn a new language and you learn to play a game. So we had highly educated people, like people running the Reserve Bank in South Africa, looking to fill that position. They did really, really poorly on that, you know. And then you had, you know, basically a cleaning lady in the office who did really well on it, you know. So it's the ability to measure the ability to learn new concepts, to form new concepts quickly. So if the test can do that rather than just logical reasoning, then I think that would be good. It would be great if we had more of these AGI tests, you know. But as I say, it's really hard because a baby AGI or proto AGI is really not going to be very impressive. So, all right, well, I think let me not take up more time, but I'll be here for the whole conference, so I'll be happy to talk to everybody. As you might have noticed, I'm still very passionate about this 20 years into it. So be very happy to talk about it. Thank you.
Okay. All right. So now we will start the setup presentation dedicated to NARS in particular. So we will start with the introduction of NARS as its implementations covering the control and technical detail or aspects. Of course, we cannot go into much detail because time does not allow us to go there. Then later we will go into the presentation regarding the application of NARS, in particularly application to the robotics and to the interactive answer questioning with the ChatGPT system. So let me start then. So we actually always ask a question to ourselves on the weekly basis: why don't we have an AGI yet? Maybe the simplest answer is that it's very difficult to create an AGI, especially the human level, general intelligence, at that level. And we don't know how much time or we will reach it at all, if it will be reachable at all. But what we know is that during that development, the NARS, with this extraordinary null logic, will be actually a keystone on a path toward the AGI. We're sure about that. So I will start with the ladder of intelligence, and let us show us what we mean by to be intelligence. So all the coffee machines or appliances that have that AI base to it, are they really intelligent, or they are pre-programmed, or they just do whatever predefined by the designer? So clearly they are not intelligent at all to what we're looking here. So then the self-driving cars, for example, one of the most advanced technology pieces, are they intelligent? They use deep learning, all of the stuff, all of state-of-the-art technologies. And they also will argue, so they are pre-trained, they are pre-programmed automation that would not allow to learn during the real time. So then they go a bit further to the biological agents. So insects, are they intelligent? And now we can see already, as Patrick was explaining earlier today, they already can adopt or mimic the behavior they can see from other species. So we're getting closer. So then the mammal or bird, and then we can find that they can reason about the behavior. And then finally, we have that human level AI that can reason and can communicate into the natural languages. So this is the human level AI. Is that basically the goal all of us we want to achieve, right? But we don't know when we're going to achieve. I will tell what we think about intelligence as we, as a NARS AGI team, think about. And also, before that, I have to explain what's a little bit explained for what's AIGR, Assumption of Sufficient Knowledge and Resources, is. I'm sorry if I'm repeating something from the tutorial, just very, very few slides, but some people be not here on the tutorial, and I cannot really go without a short explanation of that. So assumption of sufficient knowledge and resources implies that basically with sufficient knowledge, we can solve any problem if we can spend an unlimited number of time amount of time on the problem and unlimited resources, so everything is solvable. However, it's not the case in the real world. In the real world, we always deal with how much resources we have and how much time we have to solve that certain problem. It doesn't mean that we have to solve the problem to extremely advanced level, but we're forced to provide a solution given given the resources and time we have. And that brings us to the definition of intelligence, which is basically that we define the intelligence as the ability to adopt under that IECR. Because the adaptation is the really key here. How we can learn new behavior, how we can adopt. And this is we always see in the species. In nature, for example, they adapt very quickly, learning from one or maybe two errors, because mistakes is often fatal or survival relevant. So that brings us to the non-axiomatic reasoning system concepts, or NARS. How NARS can actually view all of the aspects we just described. And we see that NARS has conceptually three parts. It has a language, formal language, we call it NARSIS. It's internal language. It's very expressive language and can express pretty much everything the system can deal with. So it has to have some logic, null logic in particular, which we think it is believed that the logic to go to achieve the AGI goals. And it has to have the control, actual implementation of the system. So if the NARSIS and null logic can really exist on the paper or on the whiteboard or in the books, so the control is something that allows or gives that NARS ability to function and to be implemented into the real world. Now, of course, NARS is fully based on IECR, and that means that it's actually developed to deal with the finite resources. So it has to be always open to any new task or any new input, and it always the real-time learning has to be part of it. Otherwise, we cannot reach that goals in the AGIs. And it gives us lots of advantages, actually. One of the biggest advantages is a domain independence. And later we will see that how the same code base of NARS, only in particular, will be applicable to the robotics, and the same code base also will be involved in the interaction between the user asking questions and getting the answers. It's exactly no prior different knowledge was given to NARS in starting those completely different domain applications. So another advantage is we will have the rich expressive power. We will have basically complete inferential power if we implement the NARS as conceptually as we can, which is, of course, we still have the limitations, but we'll discuss them later. And the main importance in the artificial intelligence that we have the justification of the rules and explainability of the derivation process. So whatever the NARS derives, we have the learning vector to explain and to trace what causes what, to the extent, of course, but more or less it is explainable. Now, a few words about the logic which NARS uses. You can see on the left, on the right, I'm sorry, on the right, there are multiple levels of the logic from 1 to 9, and these are the levels that build on top of each other. So it starts with null 1, which is very basic, very simple, saying that uncertainty is not yet there. Basically, it says that something which is true, it has to be reside in the knowledge of the system. If it's not there, it's false. And now building on top of that, we get now 2, 3, 4, 5, 6, which we call a declarative knowledge. Then we introduce like uncertainty, truth value. We introduce property instance property relations, ordinary relations, variables, and composite statements, compound statements. Now later on the null 7, we introduce the temporal reasoning, which is very different, have some unique features because null 1 to 6 requires the term to be shared, and that gives us lots of advantages in terms of implementation and in terms of efficiency. But with the temporal reasoning, we no longer have that requirement. So that two events, for example, can be temporally distant from each other, but they're not sharing the same term. Now, null 8 is the procedural learning, and whenever we have to really achieve the goal by executing an operation. And this is also a different conversation we'll have at the end of this, how it's implemented at the end of this presentation. So on the left, we can see that in null, so we have atomic and compound terms. Atomic terms are like cat or animal or anything like, you know, raven, black. Statements can have, like, for example, inheritance, like cat is an animal, Garfield animal, this is null 2 instance property, cat mule. Implications, like already like null 5, a little bit higher level, so lighting is standard, and also we can compound and nested statements like that. Switch is on and lights is on, right? And of course, the null includes the rich set of rules which are predefined, which are not learned, these are predefined. Inference rules like deduction, induction, abduction, revision, choice rule. Also, we have some compositional rules, technical other rules, but we will try to explain them later if time allows. One of the key features of null logic is the truth value and expectation. Basically, the truth value. It brings us the uncertainty. So with the truth value, we can say how certain whatever derivation is, how certain is the NARS to what the derivation is, or in other words, how true the certain derivation or statement to the system experience, not to the absolute world, but to the system's experience so far. And this has two components in there, frequency and confidence. Previously, Christian discussed about the evidence, so I will not duplicate it here. So frequency basically means how much positive evidence we have divided by the total evidence we get. So we get, for example, so we have a raven is black, so, and we have like nine ravens are black we encounter, and one raven is white. So basically, the total evidence will be 10, and the positive evidence will be the raven is black, which is 9 there. So this is the frequency. For the confidence, it's a bit like coming from the data science and has some shared some similarities, yet similarities not exactly from the theory of probability theory, and that actually tells us to what extent we can believe to the certain statement. So, for example, if we just encounter, or we can have an example with the toss of a coin, how fair is the coin? If we toss the coin once and it gives us, for example, a tail, and then we have evidence on the total evidence as 1, and then we have a confidence there, basically basically just a half, 0.5, which is by definition uncertain. However, if we basically start to tossing the coins thousands of times, and then the evidence, and then the confidence will have like evidence, total evidence will be basically to the distribution of this coin toss, and that constant of 1 would not make any difference. So that confidence will stay, the confidence will see the distribution of the process. And this here basically is what the S&P, this is modeled as a statement with the frequency and confidence. Now, for the implementation reasons and for other reasons, for efficiency reasons, we sometimes need to see the truth expectations. Is we need to combine the confidence and frequency together in one measurement. And for multiple reasons, we will show it later, because we will have multiple data structures which we will prioritize based on the expectation. So it will show us exactly how to combine those two measurements into one. And here is the very abstract diagram of NARS, which all of the implementations share. So we have multiple implementation already, but all of them share basically this diagram. Is that given that we're using the null logic, so we have the concept, we have the memory like a concept-centric memory as a semantic long-term memory. So we have the inference engine, which has the components to derive declarative knowledge, episodic, procedural, inference. But we should have some priority of buffers, data structure that can limit input and output from the system. And of course, the sensory channels which we get. So this is very basic high-level diagram of NARS et al. Now we are going to show OpenNARS, in particular the latest version of OpenNARS. And OpenNARS is a general purpose reasoning system and proposed by Dr. Wang and was initially developed by Dr. Wang. And it operates, of course, under IACR, Assumption of Insufficient Knowledge and Resources. and it has the finite process demands. It's always open to new information at runtime, and it's the real-time operation. And of course, it uses the null logic to deal with uncertainty. This is in particular the architecture of it, and we can see on the right is that we have a memory. We can really see. We can think of it as a total overall experience of the system during in the real time, working in real time. Then we have the inference engine implementation null 1 to 8. So we don't have yet implementation of the self-control, which is the null 9. Over here we have two buffers, global buffer and the local buffer. Global buffer has the cross-model information, so the input can come from multiple channels, multiple models. And also it has some temporal compositions into the global buffer to allow temporal compounding and be effective into the temporal region on a later stage in the cycle. Now the local buffer is only gets the derivations from the inference, and it also has some degree of temporal compounding in the local buffer, which are then being from local buffer, they're being inserted to the global buffer, and from the global buffer, they're going to the memory. So the flow is basically from input to the global buffer, then there is some prioritization in the global buffer, and of course the competition for the resources so happens here. Then we go to the memory. Memory, there is another prioritization. Then after that, we select something from the memory, making an inference on. Derivation go to the local buffer, to the temporal composition, if any, and then the actually cycle continues always. So this is the main idea of cycle actually present in all NARS implementation. Of course, there might be different number of buffers, or your buffer can move out of this picture, going to the channel class, or in the priority queues in the case of ONA, Patrick's version. But in general, this idea is present in all of the NARS implementations. And now the power of task. So all activities in NARS are task-driven. Tasks are basically handled using beliefs, which are statement with truth value, and the desires, which are statement with a desire value. I think desire value was explained into the tutorial session, so I probably would not duplicate it over here. Now, the task is processed in sequence of inference steps, and it's always achieved not to the fully, but partially. And at any cycle, whenever it tries to process, it generates other derived tasks, which again going to all of the data structures, all of the components I explained on this slide. So NARS repeatedly select tasks and beliefs as premises, then apply some certain number of inference rules, which is a constant number of inference rule, and then decides, and then the decision is made to what extent the task is achieved. So the overall objective then, as we see, is not actually to achieve a single task to its fullest, but to achieve all of the tasks, as many tasks as possible, as like not to spend all the resources in a single task. And this brings us to the multitasking that once we started achieving one task, after we stop processing it for after a few inference steps, we can go to the different tasks. It doesn't mean that we finished the achieving or processing the previous task, task 1, for example, and when we switched our context to the task 2. But when the time comes, or when the priority of those tasks arises, or when we selected from the memory using the prioritized selection as a task 1, then we probably switch the context back to task 1. And this is how we have a multitasking here. So it's not like multi-threading is into the understanding of the multi-processing system, but the sequentially we process one task, then we leave it for some time, then we basically pick out another task, processing it, and then return to the task if it's still in the memory. Because there is certain resource allocation mechanism that allows the task to be kicked out from memory or forgotten, or maybe it's losing its importance. And there was there is no competition for the resources for that tasks. And as I said, only very few tasks can be processed completely because cycles never stops. It always keeps processing until there is some derivation is going on. Now I will repeat the task types because it's really important. So we have 4 types of tasks. It's a judgment, the most common type of sentence, and this is the statement as a declarative knowledge, as a declarative belief with the truth value. Now we have a type of question, and this is a sentence without the truth value. However, it can contain variables, and it asks the system to find or derive a judgment that can answer that question. Now we have a goal as another type of task, and goal is basically a sentence with a desired value, and to realize the goal, the system has to execute some operations. And we have also the query, which is similar to the question. However, the question asks about the truth value, but the query asks about the desired value of a goal. So these are the 4 tasks, and that's, I think, also was discussed in the tutorial. Now the inference engine. So the process is the following. So once we have an RC statement as an input, we create a task by decomposing it. The task also can be created by the derivation through the cycle. So once we select the task, we select the belief also or desire as premises. And once we have those 2 premises as a task and belief, we then trigger inference rules, also some other structural compositional rules to produce a number of derivation tasks. And we argue that a number of inference structural and compositional rules are always constant. Yes, it's maybe a large number, but it's a constant. And therefore, we argue that the cycle happens at the constant time. And this is very important because the cycle, the learning has to happen into the real time. So, yes, so that's this slide. The further set of slides is basically will be focused on the memory and the data entities of the NARS. So we have the concept of NARS. Concept is the fundamental data entity, which is conceptual and architectural. So it's very key to the NARS implementation. So concepts are created during the task processing. So as you see, the task comes as an input. We start to process the process input to create a task. After we creating a task, so we decomposing the task into the concepts. And concepts are made by a term. So for example, the raven is black, so we will get the raven as a concept, the black as a concept. Also, we will get the raven is black as a concept. And within this concept, there are multiple data structures. Now, particular data structures are implementation specific. However, all of them share like links to tasks and links to the other concepts, because it's impossible to do without it. It also have some proprietary data structures to somehow navigate within the declarative knowledge, episodic and procedural knowledge. In OpenNARS, for the declarative knowledge, there is the belief table, which is sorted by the confidence, and there's already telling the prioritization. So sorted by the highest confidence. And also there is the desire table, which is sorted by the confidence of the desire value. As far as episodic and procedural knowledge is concerned, so in OpenNARS there is implication tables and the procedural hypothesis table, if we can call that. We will cover this into the later slides, how the procedural knowledge works. However, it's important to mention right here, so concept is the entity. Whenever we pick it from the memory, it has all the related information in all of the aspects in terms of declarative, episodic, and procedural knowledge right there. So that's kind of efficiency we achieve only because of the structure, because we don't have to scan all the memory for all of the entries there. We select the concept, and we can trace the links from the concept for all the related items. Have a question?
Quick question, is the storage RAM-based, persisted, or distributed persisted?
No, it's just in basic tables. Inside the concept series.
But is that in RAM?
Oh, RAM, yes.
Is it RAM
yes.
or persisted in files?
It's in the RAM.
Okay.
It's in the real time, yes. We had, for example, we can have the memory snapshot on the file, so we can run the system using this memory, but we always start systems usually without it, or sometimes very small file. But again, the importance is that once we select the concept from the memory, so we have access to all the related items in the memory, and that gives us efficiency right there. So this brings us conversation to the main memory, and memory, as I already discussed, follows the concept-centric semantic memory structures, and this can view as a long-term memory at the semantic memory of the system. So this is the entire experience of the system at the runtime is in that memory. And concept of content of memory is always changing in non-repetitive manner. So whenever we have the derivation, you may have a different number of concepts. You can add the concept. Concepts also can be forgotten because of their prioritization, or they really can lose the grounds for the computation for the resources. Now, how in OpenNARS, particularly in OpenNARS, the data structure for memory is the back data structure. Back data structure is the non-deterministic priority queue where item prioritized by the priority value. I will cover the resource allocation and attention mechanism a little bit later, but the priority value gives us the short-term importance of the item. In this case, short-term importance of the concept. Whenever we pick up, we try to pick up the highest priority, but there's still some small chance that we can pick up the lower priority items, and this gives us the balance between the exploration and exploitation. That's kind of this. And whenever we, as we just discussed, whenever we pick up the concept from the main memory, so we also apply and trigger constant time of inference rules, constant time of operations, and we argue that it's the constant time operation to pick and put the constant back, and therefore it's a real-time operation as a whole. This is the old picture, and I still want to show it. So this is a fragment of memory of the very short fragment, very simple fragment of the memory. So we can see the concept here for the raven bird, and for the bird. So the raven is bird. The sentence raven is bird. The statement raven is bird creates this many concepts. And for example, bird is an animal. So then the bird concepts already exist. So that the information merged together. Then they create the concept of bird as animal and an animal. Right. So we are talking about the main memory. We're talking about main memory, right? And these links are nothing but the links within the concept. So whenever you see the two types of links here, and that's proprietary to OpenNARS because ONA has a little bit different types of links. Whenever we see those links, so these are over the particular data structure for the links to which links other concepts. In particularly for OpenNARS, we also use the bag here, and there are two types of links: task link and term links. Both we using the bag, we utilize the bag for the task links and to the term links, and this gives us even greater prioritization because first we have to sample the task link because, for example, as you can see, concept bird might have two, or even, of course, in real time, it's have way more task links. So we prioritize basically sample the task link from the concept bird, then we sample the term link from the concept bird again, and then going to the belief whenever the term link is pointing to. Over here, you can see that the belief links or the term links, like are blue, are belief links or the term links. We can use this word interchangeably, and the red are the task links. So we can see that they're in two directions. That means that whenever we have the belief link from the bird or term link from the bird to the concept raven is bird, right? We also will have the priority value into the back of the term links in concept bird different than the priority value into the back inside the raven is bird. So the two different concepts, they have two different priority backs. So depending on the processing into the current time frame, because it may change always. The priorities distribution within the term links backs within different concepts are different. So therefore, the links here are different. Now I want to switch the conversation to the buffer and the role of buffer. So if you remember, I'll go back. So we have the two buffers in OpenNARS design. We have a global buffer and a local buffer. And the buffer are basically priority queues in this implementation. So overall experience buffer is the main buffer where everything comes to it, including from internal system buffer, including from different channels, from vision, from NLP, from anything. And this cross-model information is basically competing for the resources. In the internal, however, buffer, we only have information which are processed by the reasoner, derived by the reasoner. Both buffers actually extend class in terms of program language, extend class of the event buffer and create the two types of temporal composition, which are forward implication and the sequence. And of course, they have a hyperparameter, for example, how long the sequence can be. Or we have like a sliding window approach. How many events, what's the temporal difference between the events we can follow, such that we will not overload the system. So buffer is the priority queue, and based on the priority value, selection is based on the priority value. So there is not like a bag whenever there is probability to select the priority value. Another thing, so buffer has another parameter such that items in buffer will be forgotten at a different pace. So, for example, in an internal experience buffer, the parameter will be to the highest and to the higher value, meaning that the number of items will be forgotten, for example, after after certain amount of cycles. While in the overall experience buffer, they will stay for a bit longer because they have a different size and they have a different decay factors. Now it brings us to the inference.
One quick question.
I didn't say sorry.
Is there any locking on the buffer elements?
What do you mean locking?
Locking, L-O-C-K-I-N-G. So if an element in a buffer is modified, does that prevent other things from modifying it, or is it a free-for-all? Like
it's a sequential operation. So we don't have multi-threaded design inside of the buffer.
Okay.
So in this case, we don't really need that. I think you're worried about the temporal composition because elements in buffer are probably not modified until they arrive like that, and they're not modified there. So there is no revision inside the buffer. There's only they can be forgotten from the buffer. The good question, because the revision can happen whenever we do the inferences. So we have the inferences. That's actually the next slide. Or I can go over there. So whenever we have the inferences from the main memory, so we select two premises, we do some derivation, and what if that derivation that we have already exists in the memory, right? Then we have to do the revision or choice or choose. In this case, we just do it because it's serial. It's just serial. It's not just multi-threaded. It's that in that implementation actually. But I see what you mean. So you have to basically look and do it like.
But the serialization prevents all of that.
Right. So once we started the inference, so we probably don't select anything from memory. We don't modify the memory at that stage until we finish the inference and until we finish the reasoning on the concept and until we put the concepts back to the memory. And that design we pursue across, if I am aware of all implementation of NARS, if maybe something Python version used differently. And that brings us to the cycle. So as I said, so the system constantly runs in the cycle. Why is like moving? Okay. So adding the results to the buffer first, then taking it from the buffer and loading to the memory, using the composition of tasks and then the composition of the concepts, and of course, as you said, triggering the revision and revising with already existing concepts within the memory. Then we select the concepts from the memory. When we select the task link, as I showed in the diagram, then select the term link. Then in the term link, where it points to, we're going to the belief table and select the highest confidence belief from there. And then we do the inference on the task link. So I go back, it will be easier to understand. So I do the inference on the task link. In particular case, here is like a raven is bird, for example, and do the belief is that bird is an animal. Do on those two things and do the inference, and I can create many different types of inference. Of course, that's a very primitive example. In the real world, the statement will be compound very longly. Can be very many derivations, like thousands of derivations. So and whenever I complete the inferences, I then adjusted that importance of each items of the concept and put the concepts back to the memory, and also put all of those corresponding data items like task links back to the task link, that term link back to the term link back, and I adjust priority of every item I was making the inference on. That's very important, and this is the serial operation. So until it's completed, nothing is being modified. And then that conclusion or derivation is put into the internal buffer, and it may be output as an answer to the question, it may be output as an operation, if it's procedural learning is involved, etc. So that's it from the inference cycle. Now I want to briefly go into that important thing, which we call the resource allocation for attentional control. So for each of the item I just was describing, we have the budget value, and budget value is the set of 3 parameters. And in OpenNARS, it's a way different budget system than in the ONA, for example. And it's more, I wouldn't say it's more advanced, and more complex in OpenNARS because it covers more conceptual cases. Sometimes they might not even happen, but it's still supposed to cover them all. So we have the 3 parameters they call priority, durability, and quality. So priority measures the short-term importance, STI, for example, of the items. Quality shows us the long-term importance of the item, right? And durability is the factor. Basically, I would multiply priority, and priority will decay to the quality parameter this time. And how fast the decay is basically based on the durability. Because once I took out the concept from the memory, for example, did a derivation, then I don't want the priority to be the same. I want it to be decreased such that some other concept and some other data item would participate in the computation for the resources, and I would select that instead of the same. So and this takes care of the durability will you basically decays the priority. I also have to mention that from the very start, even before the implementation, that resource allocation exists on multiple levels. On the logical levels, for example, implicitly, because whenever we do the null, the inference, the premises share the same term. And whenever we select, as I said already the concept, so the shared term can be accessed from there, and all the relevant knowledge can be accessed from there. So the data structures also, all of the data structures basically are prioritized, and it becomes the selection problem. So we have that long-term memory, which we just seen that concept-centric memory has a priorities. We've seen that priorities into the bags of task links, term links. We see the prioritization in terms of belief tables, desire tables. We also see the prioritization in terms of temporal knowledge, temporal inference and procedural inference. Whenever the implication table, for example, are sorted by the expectation. Same with the procedural hypothesis. We sort them in operations. We sort by expectation and then select the ones which have the higher truth expectation. And of course, to take care of all of those modifications is the job of the budget inference. That's an extensive attention control mechanism which evaluates budget in the real time based on what was there. Like, for example, based on which task was processed. Was it the belief? Was it the task link? Was it a temporal event? So it's a very complex system which we're still working on and fine-tuning it. Now I will tell you a few words about forgetting. Whenever we have such a expressive power of system, so the forgetting is a necessity to have, such that it helps to have the balance in loading all the data structure we have. And in NARS, a very brief mention, we have 2 things of forgetting. And hard forgetting is everywhere. For example, the memory is overloaded. There is no more place. So information is forgotten. And the source forgetting. So it can be, like I said before, the priority decay. So priority decays to the quality. And when priority decays to the quality, so basically it tries no longer to be selected by the control mechanism. And this time is basically forgotten because whenever the data structure is full, the certain number of low priority data items are basically forgotten. We also have the idea of evidential base that, for example, each of the derivation has its evidential base. It's the set as basically the linked list of information where it comes from, and it has a certain size. So we also allow revision between the 2, as I said, 2 concepts, for example, or two knowledge, information, 2 pieces of knowledge, whenever there is no overlapping evidence, because it's very difficult to subtract the common evidence, almost impossible. So in this case, we have, for example, I don't remember, but the constant of how long the evidential base is. So even so, after whenever the length of the linked list is reached, so we will no longer track if the evidential base have any overlapping evidence, and that's very similar to the how human remember stuff. For example, they can forget from where it comes from, and they can combine the knowledge, not even thinking that it comes from the same source. This is what I explained how the priority decays with the time.
5 minutes.
Okay. I will then cover the openers for application. So this is a programmatic design following the NARS theory. This is the general purpose reasoning system which we're utilizing now. That's written in C, very efficient and very practical in compared to OpenRs. At least tries to be practical. It designs for reaching goals, establishing sub-goals, and proceed with planning. Very importantly, it's capable of controlling on intelligent agents because of its efficiency, and it has a very, it's very good in terms of memory consumption. It is really bounded. It doesn't have real allocation of memory during the runtime, so it allows us to use it on the smaller robots like you can see tomorrow, which does not require lots of resources. It basically can run on the laptops. And it can also be interfaced with any of the channels, including the state-of-the-art deep learning novel technologies. Now, this is, you can see here, the structure or architecture, well, very high-level architecture of OpenRs for application, and it may look like a cognitive architecture. It is not. It's very, it is not just depicted the way such easy to understand. So as OpenRs, it also has the conceptual memory. It has the temporal inference connected to the memory directly, procedural inference. It has the prioritization in the conceptual memory by the priority. It has the priority queues and declarative inference mechanism over there. This is the more of the, it's a better picture, I would say, for the explaining the owner. So we can see here that we have again the concept memory. We have the temporal reasoning over here. Over there we have the FIFO, which utilizes the temporal reasoning, which have the sliding window approach, as I said maybe earlier, right? So when we create the temporal compositions, also temporal reasoning creates that implication table that puts into the consequence of the statement over there. So here we have the procedural reasoning. Procedural reasoning, the job of procedural reasoning is to basically to choose the most desirable operation to execute such to reach the goal. If we have such operation, we basically have one backward step to choose it based on desired value. If we reach if we above some threshold, if not, we derive the sub goals, and then when we derive the sub goals, we insert them back to the priority queue goal event. So the main key data structure for the owner is the attentional buffer, which is items are ranked by priority, and it's its capacity, so it's over there. So the first half, but then we have the concept memory. There items are ranked by the use counts and last use time. So now it's different than the OpenRs, which also uses by the priority. And as in OpenRs, so content of memory is always changing and in not in a repetitive manner. So another important thing is the implication table, as I said. So in each concept, there is an implication table, and temporal implication is stored there into the consequent of the statement and ranked by truth expectation, similar to OpenRs. And we have the different depth of the goal priority queue over there, such that we can trace and have the predefined the number of sub-goaling we can trace. Few minutes, right? Now, can Patrick follow his example on the temporal and procedural? Very fast.
We're due a break now, so we should stop now because it's 5:02, and then carry this on afterwards.
Maybe we just have a couple of minutes.
Oh, is that all it is? I mean, you're not going to do it in 2 minutes, are you? You need a bit of time.
Depends on how many slides.
Basically, your favorite example.
Maybe a break.
How much time did it take, the talk?
Did you take?
How much time did the talk take, my talk?
When did you start? You was due to start at 1:30, but you might have been a bit late. So hour and a half, hour 30, 45.
Okay. Then let's have a break. And then we will have less questions, right?
Thank you.
Yes.
About the reception.
Where we will continue with the workshop.
So everyone is
I hope the Zoom audience can also hear us. Is there someone connected to Zoom who can quickly check whether the audio works? Oh, thank you. Okay. Then let's continue. I just want to give you, before we continue, since there was a break in between. So the overall picture of this implementation of NARS, this open NARS for applications, you see here there are pretty much 3 inference paths in this system. There's one inference path here, which is responsible for declarative reasoning. There's one inference path which is particularly concerned about building temporal relationships between events. And there's one inference path which is concerned about decision and subcoding. And we will now, you have in the morning and now you have seen the logic regarding declarative inference. You have seen a lot of that. You have seen now some of the temporal inference for forming temporal implication statements, which describe, like, if this happens and I do that, what is the consequence of this operation in that context? And you know, that's this inference path here. And now we go to the procedural execution part. Like when do we decide to create a subcore and when do we decide to invoke a decision? Like turning on a motor. And so the idea is there's a certain goal we select in the inference process, a certain goal we want to realize. The system wants to make this goal happen. It wants to achieve it. So next thing is there are multiple hypotheses which speak about how this goal can be achieved. And they are competing for each other, the multiple ways to achieve the same outcome. So which one to pick? And now it's a matter of how fulfilled are the preconditions of these contingencies, as we call them. So it's always precondition, operation, and consequence. And in this case, we particularly,
Operation identical to task, or is it something different?
Operation is like a special case of task or event the system can invoke by itself. So it's different from the other events which just happen, like from sensory input. The operations are events that can invoke, like turning on a motor, moving forward one step in a simulation. So it's really about the actions the agents can take, so to speak. And in this case, if the agent has built multiple such hypotheses of how a certain outcome can be achieved, the question is which ones to pick, which operations to invoke. And the idea is we pick the operation which, according to the system's truth evaluation, most likely leads to this desired goal to be achieved. So among these options, it's always trying to pick the best option. We will see this, I go through an example now, and only if there is no such condition currently met, only then it will generate subcores. But we will see this now in a more intuitive way. In an example, let's say there are three different contingencies or procedural hypotheses. If the system sees A and it invokes operation 1, then it expects event B to be seen. If it has seen event B and operation 2 is executed, it expects G to happen. And if C is the case and operation 3 is invoked, then it expects G to happen. Just as an example, let's say we start with this knowledge and let's say we have observed A already and we want G to happen. So now there are two procedural links for this concept. Two of them speak about how G can be achieved. Both of these implication links, both the preconditions are not yet met. It has only seen A, it wants G to be achieved. So what it can now do, according to this, what we have just seen, it will derive B and C as a subcore. So that's next step. And now, so it has now two subcores. For C, there is nothing it can do. There is no incoming link. There's no procedure it can invoke to make C happen. So it will select the score, but it cannot do anything with it, so it will be thrown away. And for B, when it selects B, it can now invoke operation 1. Since it has previously seen A, it's now executing operation 1, anticipating that B will happen. Now, two cases. System was right, B happens as predicted, or system was wrong, B does not happen as predicted. Let's say, for the purpose of this example, it observes B. B indeed happened as the system anticipated. So in this case, this procedural hypothesis gets positive evidence. Invoking operation 1 in context of A indeed led to B to happen. So positive evidence for this piece of procedural knowledge. And still it wants G to happen. So what it will now do, again, compare both options, the incoming links to G, when it selects it from the priority queue. Two options. And this one doesn't even have the precondition fulfilled, so this one is now the most likely to lead to G. So it invokes operation 2 and anticipates G to happen. So it would be done if it's right, but of course it can happen. Maybe it was unlucky, differently than it believed. G did not happen, so this second procedural hypothesis gets negative evidence. So even though, so we have a very interesting situation from the credit assignment perspective, because even though the system wanted G to be achieved, only even though it did not manage to achieve this outcome, it found positive evidence for intermediate hypothesis that invoking operation 1 in context of A leads to B. That's valuable. So even though the final goal has not been reached, this hypothesis got positive evidence. It's only the second piece which got negative evidence. It's a very, very interesting aspect of how the credit assignment, so to speak, works in this system. It is positive and negative evidence assignment based on whether the temporal hypothesis predicts successfully or not. So that gives a good picture of how the learning process actually happens for the system in the various situations you have seen, like learning to play Pong and other scenarios where it needs to learn procedural knowledge and update the truth value of this procedural knowledge. But this was one important step, which is probably good to see. We can probably give a very brief conclusion.
Just out of curiosity, would it create a concept which says if I instantiated B through operation 1, operation 2 will fail? Because it has the knowledge that from B with operation 2 I get to G, right? And this time, it first used operation 1 to get to B.
This you mean like modeling under what, when the operation itself succeeds or not, right?
Yeah, like if operation 1 blocks operation 2 from, being successful, would it create such a concept?
Oh, yes, it can also create new additional temporal links through this temporal induction process. But in this example, I particularly focused at how the
just out of curiosity, yeah.
Oh, yes. So here it was more about how the hypotheses are updated once they are there. But I fully agree. It will also build new temporal links with the events it observes. So it will also cover that aspect of structure learning, so to speak. So it's not just updating the truth value of existing hypotheses. It's also constantly creating new hypotheses using the temporal induction or there's some Unicode mistake here. This one should be a temporal implication here. So we have like event sequence ABC. It will form this multiple hypothesis. This we have already seen. So we can conclude regarding NARS. This slide is actually not just honor related, but so we have this conceptual representations. We have this kind of cause and effect relations. Was there a question? Okay. And of course, effect representations, which the system can learn and utilize in its decision making, which itself is very good to have. And the system, I mean, you have already seen that has like uncertainty estimates, and most of this we already talked about. So we will now go into one of the more advanced capabilities. Why is it not clicking? If I click. So we will now see the system in a robotics case. And maybe can't guarantee that it will work.
Someone is whispering.
It's a long way over there, but there's a robot behind you. Which I'm trying to guide into our direction. This is more the right side, so it should actually move over here. But I want to show you some of the capabilities we have developed on the robot.
What are some of the facts and what are some of the facts and operations that you're using for the robot?
This we will shortly see. I just want to get it here first. Oh, yes, that's true. And you see here on the map, actually, the map it has built. Not sure how I can move the camera around here. Maybe if I just to give you some impressions of what we have built on this hardware before diving into the more dry presentation of the capabilities.
Is this the part that's funded by the Swedish Army?
It looks dangerous, right? So we are essentially running this reasoning system on this robot. And we will see certain capabilities which we have developed. So the idea it's also part of the philosophy of the system that we actually also make use of the state-of-the-art technology as well as we could. So that we actually make use of technologies such as what you see here. This is the result of simultaneous localization and mapping. It's something which has become quite mature in the last 10 years, I would say, but maybe even a bit less, that a robot could reliably build a map of the environment, which it can use to get back to a certain location. That's maybe from a human level AI perspective pretty basic, but it's also very important that we can get back to certain locations where we have been in order to do certain tasks, which some of them we might do every day, like to get to the kitchen or to get to the bathroom. So it's, even though from a human level AI perspective, okay, that's pretty basic, from engineering perspective, it was a challenge for a long time. And from an AGI perspective, it's still very important to have the space capability so that more interesting stuff can happen on top of it. And so the idea is we utilize this so the robot knows where it is in its environment. It can get back to certain locations it wants to get to, and it can also see objects. This, we can actually get a view on what the robot currently is seeing. This is what it currently says. And you see, for instance, it says multiple objects. This is machine learning model which we utilize for ONO, which is object detection model, YOLO version 4. It can detect objects and can identify certain types of objects. Like it says there's a laptop there in the back, there's a person there, there's a chair there, there's a bottle. And that's useful because it means it has some semantic understanding of what's going on around it. It sees at least certain object categories which allow it to distinguish certain objects of interest from other objects which it might not be able to do anything with.
The objects that are not with the bounding box, does it not see them, or is it just that it doesn't have a label for them?
That's a good question. There are, of course, feature representations which also map to these areas. So one could certainly build something which makes use of the learned features in a more unsupervised way. That's also part of a lot of research. It's our own focus was not this so far. Actually, there's Robert Venture here is developing an unsupervised vision model, which you will see tomorrow in the demo session. Actually, it's a system which can really learn new object categories while it's operating. But for this robot, we have mostly relied on relatively established components. And this really means a lot because 20 years ago, you couldn't do very much with a robot. And now you can let it move around reliably and really use it as a good demonstration for AI capabilities. And for instance, here, what you see here in the background, it has really encoded what it sees in a way that NARS can reason on it. You can see it encodes that there's a bottle, that the location of the bottle on the left, it knows where it is based on LiDAR location, based on simultaneous localization and mapping. It can see the distance to obstacles and so on. And if I instruct the system to do something, there's, for instance, a mission goal where we say the robot should just look for bottles and pick them up. And so essentially it should search for bottles and then pick them up and then find a human or remember where a human is sitting and then bring the bottle to the human. So a bit like fetch, but for robots essentially. And you can do such experiments with this hardware. You can do these experiments, and I think previously it was mostly a distraction to work with robots, but the technology has progressed in such a way that it becomes very tractable to use actually robots for AI demonstration and to let them perform various tasks in the environment. And of course, from our perspective, we want a system which keeps learning and operating. So we really want to build an adaptive system which can drive the autonomous robots of the future, which can continue to adapt, learn information from the environment, adjust their behaviors, remember where certain things are so that it can get back to the loading station, and so on. And of course, live demos are always risky. There's always something which could go wrong. But it's, how to say, I would say that a lot of robotics technology which is required to do such AI demos in the real world has really significantly progressed, especially in the last 10 years. Of course, deep learning is also part of it. Also, very clever algorithms are part of it, like simultaneous localization and mapping. And our idea is then to have a reasoning system on top of that, so that it can carry out missions like that, and that it can essentially perform various tasks in complex environments, ideally, right? So in this case, it has seen the bottle and it has picked it up. Maybe it's not too impressive, but it's an integration of all these different components. Object detection model, simultaneous localization and mapping, running NARS on top for procedural execution and real-time learning. And I think it's a good demo which shows that we can actually combine these technologies in a reasonable way. How to say, from a reasoning perspective, there's also, of course, always the question, at which level does reasoning actually kick in? If you build a cognitive system, is all of it reasoning? Is reasoning only happening at the top of the iceberg? Or is it more tightly also in perception? We think it also has a big role to play in perception. But of course, there's always the question, where to draw the line between sub-symbolic and symbolic. We try to make use of both, so to speak, to integrate both in the way that is most fruitful and to utilize the technologies. And so that there will be some synergy in using these components together. So, for instance, currently, if it can see me, it should be able to identify me, give me the bottle. It's given me a warning signal, which is because it has seen that I'm a human, which is pretty close to it. And it might just seeing me. So maybe we can also look at what it's currently saying. The background window. I somehow lost track of the window of what it's currently saying. I think this.
Don't work with animals and children. I think you need to add rodents.
I was just thinking of treating my nephew and see something on the floor and pick it up.
But so it should see me and give me the bottle, ideally. Okay, now it did it. Give me. Take it. Yeah, so just as a demo of what you can do with this box.
I think you made it mad.
That's not good. Good. Like an insect. So, and now we will. And now we will dive in some of the and how this was actually achieved, this integration of different capabilities. But we can, for instance, also ask it, what does it currently see? Like, what is on the left? It allows one to interact with it while it's operating and answering questions about what it's seeing, what it's doing, and so on. So we could, for instance, ask, we could, for instance, ask if it sees a person somewhere and where. In this case, maybe there. So this is the NARS to ask. So this is essentially a question variable here. So it can instantiate it with specific location. And it should be able to answer. Okay, it says in this case there's a person on the left. Yes, there. In this case, maybe it's not the best example, but you see it. It sees the things, and so it can also answer questions then using this reasoning system, like where it sees certain things and what it sees and so on. So just one example where we can also ask where it is. from using a reasoning system, what you really get is you have a system which you can essentially ask questions while it's operating. This is by itself very valuable, and for NARS even more valuable because the system can learn new things while it's operating. So it's always good if we can ask it questions about this. You will also see on one of the next presentations where we combine with GPD, and here you see why, because it's not always easy to communicate with NASIS. It's easier to communicate using natural language. So it has answered with this location, because it's also aware of the coordinates from its location estimations. We can also ask them more interesting questions like, what would it say about itself? What is self? We can, for instance, check what is its own categorization of self. Self is something which appears in the system when it invokes operations. It knows itself is doing that. And so it can build categories using this self term, essentially. So if it picks up bottles, it knows itself is something which picks up bottles. And over time, this concept gets richer because sometimes it says, okay, I also see you have this green arm. Okay, I'm something which has a green arm and picks up bottles. And so this self-concept, self-categorization is something which is also very interesting from a cognitive perspective, because we really like the constructivist approach which is also Christian Dorison is pursuing, which is if you have a system which can perceive certain things about itself, then why not use this knowledge to build concepts around it? So let's see what it currently would answer. Of course, it might also be that it answers nothing. So we can, in this case, we want to ask a generic question. Okay. In this case, it really answered, self is something which picks bottles. Okay, it just has only picked one bottle now, but it's reasonable categorization it made about the self term.
I will ask it if it wants to have a bottle back.
Yes, we can actually also ask it. Fix the bottle. Bottle. And ask if it has. If this is desirable. Oh no, it doesn't want it back. That's yes. And now we will dive into some of the more technical aspects of all this. So we will shut down the machine. Into the presentation. And tomorrow in the demo session, we will also show the robot and some other capabilities. So you can also, maybe you have some ideas about questions you could ask the robot or tasks you want it to do, because it's really generic in a sense that you can give it different tasks and make it, let it try to achieve them. How can I get back to the slideshow mode here? Maybe it can go up there. So it has a better view. So how did we all do this, and what was the motivation behind this integration? It's often considered to be a bit of a distraction to work with robots, which I actually also agree to, but it's a funny distraction. It's really fun to work with robots. And it's also great to see that the technology has progressed in ways that make this effective now to work with them. And you can do certain things which generally with AGI systems, we want them to be good real-time learners. And So this is our things, capabilities, which we can actually, which we also want robots to have to some degree. Of course, there's the question how autonomous we want them to be and how task-driven. But generally, we want them to be quite adaptive so that they can deal with challenging circumstances they face. And this is also one of the key drivers which made me personally dive into robotics. That is, I really thought, isn't NARS a great fit to build autonomous machines? An adaptive system can learn procedural knowledge and update it at runtime. Isn't this a great fit? And I think the answer is yes. Just a few years ago, it wasn't yet there yet that the implementation was ready for this kind of task. Because you need all the lower levels of non-axiomatic logic to be ready for this. It needs to be able to revise hypotheses. It needs to build them. It needs the attentional control mechanism. It needs to focus on the right inference steps. If it doesn't do that, it will not even make any decision because it will go off track with its reasoning. So there are many things which need to be there and need to be in place in the right way to make it function. And this is also where I'm really grateful for Hugo Lutterby, who really sponsored this research now for many years, which allowed this research to get to a certain maturity, especially the implementations to get to a certain maturity where we can show the potential of the non-axiomatic reasoning system. And so this was the motivation. This you have already seen. I will not repeat any of this. So the current picture is like this. It has the multiple modalities integrated in a single system. You have a RGB camera. Here you have there's also infrared cameras. It also knows how far things are away. You have localization through the LiDAR, and you have actuators. So pretty much a lot of modalities which you need to integrate into a single AI system. And this makes it interesting because our reasoning system doesn't really care where it gets the information from. Is it visual information? Is it auditory information? Where the events come from and what information they carry? It's really flexible. It doesn't have a constraint which says, the events only have to be about vision. It's really good in this kind of multi-modal integration because it allows different events from different modalities to enter the system at any moment in time and building these temporal relationships and learning from this experience, so to speak. So that's the current picture here. I think this motivation is already done. Let's see how much time. So I will try to keep this short. So encoding-wise, you have already seen some of the encodings like representations which are used by the reasoning system, like how to encode location information, how to encode that it has seen a certain thing at a certain location. You have already seen some of this. I will not get too much into the details here because I think it's not too relevant. But there was the question before, which was, which knowledge do we actually represent on the robot? Which knowledge do we give the robot? And which knowledge do we expect to be learned? And that's actually by itself a tricky issue. The good thing is with NARS, you can combine it. You can give it certain knowledge, like what we typically do. At least we give it some mission. We give it something we want it to do. And then it's a matter of either it has to figure out how to do it completely by itself, which can take time, of course. It's not cheap. It needs to do learning. It needs to try things and to make mistakes on the way. So here it's in a matter of either you let it learn, which might or might not always succeed. It's in no means a silver bullet. Or you can give it the knowledge. And for instance, certain knowledge is easier to learn, while other knowledge is more difficult to learn. For instance, if it's just about avoiding obstacles on the way, that's relatively easy for the system to learn. Because if it has this, if it can sense obstacles, if it receives events for obstacles, seeing them at different locations around it and the distance, then it's relatively easy for it to learn behaviors like that, where it notices, okay, there's an obstacle in front. I received this event. What happens if I turn to the right? What happens? Okay, now this obstacle is to the left and not in the front anymore. So if the obstacle is in front and I execute left, then there is no obstacle in front anymore. That's very simple contingency, which it can learn in a matter of minutes while it's operating the robot. But of course, to speed up, we can also give it this procedural knowledge about how to get around obstacles, how not to bump into them as a first start. So the good thing is with NARS, you can combine learning and giving it knowledge. Traditionally, it has always been a strength of reasoning systems that you can give them knowledge. And the issue was always how to make them learn the knowledge, right? And on one hand, they are very powerful. You can give them knowledge, they can work with it, they can plan ahead and make decisions to achieve the mission goal. But in terms of adaptation, traditionally, we have had to rely on something like reinforcement learning. And it's like two different worlds which are hard to combine. And I'm not saying that we have the final story of how to combine it, but here we at least have one system which can cover aspects of both worlds, so to speak. We can cover some of the real-time learning capabilities, adapting behaviors, in this case, causal representations. And on the other hand, being able to give it valuable high-level knowledge to work with. So this is really, how to say, the core of the multiple possibilities, so to speak, to work with the system and can combine both learning and giving it background knowledge.
Question. If you go back to the last slide, like the word obstacle, I guess that's a concept. Can that also be learned, or do you have to specify like these, say, primitives?
That's a good question. It's essentially, there's also, I fully agree, there's one more decision which has to be made when working with such a reasoning system. It's not only about which information you give it and which information it should like build by itself. There's also this question, what are the perceptual primitives in the first place? What does it see? What can it actually observe? And what are the representations for this observed information? And here it's, in this case, this concept, as you pointed out, is essentially given, encoded by the sensor in this way. But there are also possibilities to have smaller primitives, and then to let the compound term formation, which Christian showed today, like combine different attributes. So for instance, in this perceptual case, here we actually have a case where it already needs to be a bit more granular than you have just seen before, where I simply told it should pick up the bottle and it went for it and it picked it up. Here, for instance, it needs to make a choice between two bottles. So it already needs to go a bit below just seeing this bounding box and knowing this is a bottle. But what we have, for instance, here what we have is essentially the idea that we not only have a single label for the thing it says, but also to extract additional information. So it's maybe not at the pixel level, that's too much for us, but additional semantic attributes, like what is the color of the things you are seeing, what is the size of the things you are seeing, like you can use the bounding box dimensions to fit to the reasoner as a size measurement. And here, for instance, this is also what we do. We give it color information for each of the detected objects, automatically extracted from the bounding box, and also the bounding box size. So it has color and size at least to distinguish objects or to see commonalities between objects. And in this task, we explicitly give it the task to pick the smaller among both. And you see it's really able to carry out this task by doing this, building this comparative relation and then acting on it essentially. And we will see some of this in my talk, comparative reasoning talk tomorrow or Sunday, I think. Yes, and this is actually something which is really a capability which I really have to thank Robert Johansen for this, my postdoc advisor, because he has always stressed that this ability to see differences and commonalities between objects is so, for us, it's common sense that we can do that. But for AI systems, it's actually, there's still, how to say, if we build special purpose perceptual systems, then usually we don't equip them with the capability to compare arbitrary attributes and find all the commonalities on the fly. But here we really aim for this ability for it to quickly see what are the commonalities and differences between objects it sees, and so that it can make decisions based on this. And in the psychological literature, this is studied under the name of transposition, that animals, for instance, can not only pick a certain thing because it has a certain size, but can also take another stimulus into account and make a comparison. This one is larger than the other. And always when I pick the larger thing, then I get cocky. So it's essentially, to some degree, an abstraction to build a comparative relationship among stimuli, instead of just acting on the specific stimuli to say, okay, I compare two of them, I derive a comparative relation, this one is larger than the other one, and then to act on this derived information. And this is something which we have recently achieved. And I think it's something which is relatively fundamental. There's also, I don't have it here, but you have seen this case with like Alex de Barrett, and I actually agree with Peter Voss that the language capability, it's certainly very likely missing something fundamental. So it's definitely not generic language understanding, but I think that at least this ability is to compare things, like to notice one thing is larger than the other, that this is relatively innate in the perceptual machinery of the animal. I think this at least is very likely covered, and so we also try to capture this aspect when designing general purpose visual system for NARS essentially, so that can compare perceived objects and see commonalities and differences. Yes, I think this is actually this is it about this presentation. I think I'm out of time anyway, right? Yes, so I will go for the next thing, which happened recently. So this is quite advanced capability to have this different.
Maybe we could just ask if there's any question about the previous.
That's a good point.
Right now.
Then the next thing, so we're really exploring multiple things to make our system more capable. Of course, making the reasoning system itself more capable, how to integrate with certain technologies to make it more workable for practical applications and various purposes. And there is, of course, we also cannot ignore the huge progress which happened with large language models. And I would say it's also, how to say it, I like them very much because the public is now taking the idea of AGI more serious. I think this we can at least say. It's these large language models have demonstrated a lot of capabilities which I personally at least did not expect them to obtain from simply being trained on huge masses of text. And for me personally, there was always the question, they must be doing something right. There must be some, if they are so good in capturing the structure of language, there must be something right about them. And the next question is, okay, how can we utilize this? How is it relevant to NARS, for instance? To my own research, is there a way to combine these technologies? Are they even competing, or is it more like I can utilize the GPT model for NARS so that we can have a natural language interaction capability? And I have, especially with Hugo here, have especially also explored this idea of using GPT to provide natural language capability to NARS. So instead of always having to interact with the reasoning system with this NARS language, to essentially use GPT to translate natural language into NARS. And what's really interesting to me, over the years we tried various semantic parsing approaches, and I have to say GPT is way better in translating English to NARS than everything I have ever tried to manually build with semantic parsing. And of course, the question is the idea of semantic parsing in the traditional sense flawed by itself, or is it just that I didn't pursue it hard enough? But one thing is for certain. The GPT model is really capable in translating English to NARS. So for me, it was a few months ago, it was clear we should at least use it for this purpose, because it's really, really good at it, and better than what we had before in this aspect. So what we will now talk about is how to do this, how to combine a large language model with NARS, so that you can get both ability to communicate with the system in natural language, while at the same time having the reasoning capabilities you have seen, or the sensory motor learning abilities, without losing any of that, essentially. So here I just have to point out some acknowledgement. So Cisco has largely sponsored this research, and also Fraunhofer. We together with Fraunhofer the Springy Computing Challenge. We participated in the challenge, which we were able to get. And this was both very good to make this project possible. And I also have to say thank you to Peter Voss for providing us a very useful question answering data set, which I also used for internal purposes to test the chatbot, right? And personal assistant. So that's that, and of course also why is it not switching? Oh, okay. So there are a few drivers of this work, a few base observations which made it clear that, or made it clearer of how these systems could be combined. In addition to simply letting GPT translate to NARS, it was the following observation. Ideally, we would like AI systems to remember information for a long time. Like if I communicate with my AI system, it would be good if hours, days, weeks later, it could remember certain things it ordered, right? And that's something you cannot get from ChatGPT at current. They have really limited contextual window, even GPT-4, like 50 or 60K tokens. And once you're out of that, everything it generated is gone, essentially. So without any additional backpropagation being applied, everything the model generates or the token generates, when they fall out of the contextual window, it will not know anymore what information we gave it. So there's this challenge of how to have long-term memory, essentially. That's one part. How to keep information for long term, but that's not the only part. The second part is how to form a belief base of the information that was taught to you. Not just remembering sentences one by one the way they were taught, the way they were presented to you, but being able to have a notion of truth, so to speak. How does the input information you get textually change your internal beliefs about a certain relationship, like if ravens are black, or if the earth is round, or different kinds of relationships which we consider common sense knowledge. And there's the question how to update this, how to evaluate the truth of this in a way that new textual information we get from other people can influence these beliefs in a long-term way, in a way that we can learn from these interactions. So that so that you will 2 weeks later remember what I talked about here. And that's essentially what we try to do by bringing NARS into the picture. NARS already has this memory capability. So if we can use NARS as a long-term memory system for GPT, then we have some of these questions addressed. And for this particular project, of course, there can be many ways of how to achieve this, but somehow it needs to be addressed. It needs to have long-term memory. It needs to be able to update its beliefs. And also for our system, it's also a sensory motor system. So the things it believes are not just somewhere in a database. They're actually affecting the decisions of the system. The beliefs are not there for nothing or just to answer the questions of a user. They're also there to drive the decisions of the robot. Like, what does it believe? Where is this particular object? When I tell it this bottle is in the kitchen and you should get it, it will act differently than when I say the bottle is over there. Dependent on what it believes, it should act differently, essentially. So that's just conceptually. I will not repeat anything we have already presented. I think you are also very familiar with GPT models, so this we can also skip. We will go right away to 2 key pictures of how to do this. So if we look at GPT, normal GPT, you just input English to it, and it gives you tokens, predicted tokens back. That's it. If we want long-term memory, the situation becomes a bit more complex. Let's say we simply wanted to remember the sentences we gave it. This we can do. We enter a sentence, we calculate an embedding, and we store the vector and the English sentence into a database. And later, when you ask a question, you can calculate the embedding of the question. You can pour out items of sentences which have a similar embedding and pour it into the prompt so that you can answer questions about sentences in long-term memory, essentially. It's very simple architecture. So sentence, calculate embedding, put embedding and sentence into the database, and then when question comes, pour out the relevant information so that you can answer a question using long-term memory contents. If you don't have a notion of truth, you cannot really update knowledge. If one piece of knowledge says the earth is flat and one piece of knowledge says the earth is round, then the answers will, sometimes you will get it's round, sometimes you will get it's flat. Not really trying, it will not form a consistent view. With NARS, this is addressed. We take in a sentence, it's a bit more complex now. The overall picture is still similar. but now we have NARS in the picture. We take an English sentence, but this time we don't just simply calculate embeddings and store it. Instead, we take it apart. We let GPT extract relations from sentences in such a way that the relations cannot be further divided without losing information in the sentence. So if I have something like Patrick drinks coffee in the kitchen, then you can, for instance, say Patrick drinks coffee. You can say Patrick is in the kitchen and extract these two relations. But if I take them apart further, I will lose information. I cannot further divide this that I'm in the kitchen or that I'm drinking coffee. If I try to divide this further, I cannot do so. So these are like the minimal relations which I can extract from the sentence Patrick drinks a coffee in the kitchen. The idea is we extract this more atomic relational basis, which is not always perfect. Sometimes it will lose some information. Some relations will not be encoded. This can happen, of course, but it's relatively good in taking complex sentences and putting them into pieces. And GPT is really good in that if you prompt it for that. Take a complex sentence, translate it into very simple subject-verb-object relations. And really do this well. So if we have this, it's very simple from the subject-verb-object pieces to translate into the NARS and to feed it into NARS. So NARS receives this relational pieces and does reasoning on it. And now comes the good thing. Now a similar thing as before, but this time we don't only have the relations from the input, we also have derived relations. So we take the statements now as derives, we calculate embeddings of it, and we put it into this embedding database. So we have now a hybrid database, actually. We have the vector embedding of the relations, and we have the symbolic information, the NARS statement attached to it. It's really a hybrid representation now. So we store both input and derived information here. So when user now asks a question, it will consider both things users have said and things NARS has derived from it. So we essentially, at this stage, we have a consistent, relatively consistent belief base where certain evidence will have been revised. So it's not like before where it will either answer the Earth is flat or round, but dependent on the evidence, it will believe one thing more than the other. So if you ask a question about whether the Earth is round or flat, dependent on the evidence it had, you will get a consistent answer. Some of the details of how this is all achieved. So some of this I already mentioned. We take sentences apart into subject-verb-object triplets. So this is like the prompt looks like. So this is the prompt for GPT to take apart sentences and put them into smaller triplets. So I just described to it, this is a relation claim, certain noun, verb, noun, or a negation thereof. So it can cover both negation and non-negated case. So I just instructed that it should encode all the relations in the sentence so that it will take it apart. And this it can really do. So you can really prompt it to carry out this. And then the interesting thing, when we ask questions in English, it's actually because we are pulling the information from this memory here. So it's actually answering questions about NARS beliefs, which I kind of already implied, but that's really the key here. And you can ask it not only that, you can ask it when it gives an answer. Which memory item in NAS memory actually supports the answer to this question? So you know, is the answer made up? Or is it based on actual evidence the reasoning system has for this statement? So, how much time do I have left?
Nothing.
Okay, then I will.
You have a WhatsApp on the wall, but I go. You have watch. In front of you can left or you can cover the last slide with the results only, and that's it.
Oh yes, that's fun. So you will see more tomorrow in the demo session. You will have a live way to interact with NARS GPT. So you can interact with NARS in natural language. You can tell it information. You can ask it questions about things you would expect it to derive it. You can see if it actually does that or not. You can tomorrow you will be able to try the system in action.
On Monday there will be extended presentation of that.
And maybe one thing, the only thing I want to end with, we actually tried this system in reasoning experiments, and there's Facebook Barbie tasks for reasoning and question answering, and there are like 20 different kinds of reasoning tasks in natural language. So different subtasks which require some form of reasoning or might require, both for deductive and non-deductive inference. And there are some of the subtasks we can already show with NARS GPT that we can actually have a better, better question answering performance than using a GPT model itself. Interestingly, in this Barbie tasks, it's not even a matter of long-term memory because it's just like 4 or 5 sentences plus 1 or 2 questions associated with it. Then you throw it all away, then the next sentences, then the questions about it. So it's not an issue of long-term memory in this example, but just a matter of being able to reason appropriately. So what we can show here is that we, especially in inductive reasoning, that we get significantly more questions read than relying on like vanilla GPT 3.5. Additionally, there's this data set which Peter was kind to provide us, which is also interesting because that one shows another strength, which is simply, in this case, long-term memory, which to some degree, in this data set, it's expected. Okay, there are over 1,000 input sentences. Of course, that's far outside of the contextual window. So it's not too surprising that vanilla GPT 3.5 only get 11% questions right here because most of the information is already outside of its contextual window. Well, with this NARS GPT, we currently get 65% of the questions answered correctly. So you can really, there's really a lot of synergy in combining GPT models with reasoning systems like NARS. This, I think, is safe to conclude. There's also one funny example I want to give because it's a good example of how easy it is to correct or to inspect the beliefs of NARS and provide it new evidence to correct its knowledge. Let's say you're a restaurant owner, you want a Q&A system guests can interact with via touch panel to make orders or to ask questions about different meals. And you want the AI system to be factual about the meals you provide for the customers. If you take vanilla GPT, it will often make up stuff like here it claims Käferbohnen salad is a German salad made with green beans and potatoes. That's totally made up. It's not the case. Käferbohnen salad is an Austrian salad made with runner beans, onion, and pumpkin seed oil. So I corrected its belief by simply telling it my own knowledge about this, so that it's actually so that NARS GPT gets evidence that it's actually this kind of salad. So next time when you ask about it, like where is it made, then it will already answer correctly. It's made in Austria, not in Germany. And it's made of these ingredients and not the other. So it's also a lot of potential here to have customized models, not in the fine-tuning sense, very adjusted via backpropagation, but to have a reasoning system attached, where you can more easily adjust the belief base, essentially. There's also some potential here. Yes, what was really good to see for me is that NARS is actually the current inference control strategy, because for many years this was like the biggest issue to us, to make the inference control strategy do something meaningful, to really be effective for question answering and decision making and so on. And it's good to see actually it can, in terms of question answering results, it's really clear that the attention mechanism works reasonably well to answer questions which are about natural language knowledge, which we feed into this. So that's good to see. That was good for us to see, because at first we were worried that maybe it's not up to this task, even when we give it all the relations extracted, but seems to do pretty well. Yes, so overall, that's just one of the many promising directions we try to explore with our relatively small team. Thank you very much.
Right. Let me make some announcement. So the workshop will continue after the 4:40. So the Robert Vinci will come next, and then I will want the Hugo to start because we'll have to go, right? At 4:40, there will be the reception here, they will bring the food, but we will have two more speakers, is Robert Johansson and Chris Thorson. So you're welcome to grab the food, and the workshop will continue until 5:30 or so, 5:30 to 6. Okay? Okay, thank you. So, Robert, start. No, Vinci. Why not?
Scheduled for tomorrow, isn't it?
No, for today. Okay.
It is for tomorrow, Peter.
Very nice. Then who do you start? Yeah.
Don't scare him like that. He's having a heart attack over here.
It's just there. Look at the schedule and see.
No, you're
So Peter, how long time do I have now?
You can have like
25 to 30 minutes. Are you still able to listen for 25 to 30 minutes?
Is there much math?
No. Okay, so thank you very much for the talks this far, and I will explain a bit on the kind of research we do at the Department of Psychology, where we use NARS as our study object. NARS is our research subject. So I will try to use these 25 to 30 minutes to explain the general idea of how to look at psychology in a way that is very compatible with NARS. And I would like to show some very simple experiments from the perspective of learning psychology and how we do this with NARS. I will argue why learning psychology and NARS fits very well together. And I also will argue why this approach fits very well to other AGI systems as well, that this kind of study approach fits to other systems. And also discuss the larger implications of this work. And I hope this relates a bit to your ideas on how AGI could be beneficial for society. So everybody knows that psychologists like to study rats in rat chambers, right? And so I want you to imagine a rat that is in a chamber here. And we would like to train that rat to turn anti-clockwise when a light is on and clockwise when the light is off. And the chamber also contains a food dispenser that we will use to deliver food to the rat. And we just assume that the rat can't do this at first, but we would in some way expect the rat to learn from experience. So here is the rat, and the rat is in the chamber here. So it turns anti-clockwise, clockwise when the light is off, and it gets food for every turn it does like this. So it keeps turning like this, and the experimenter turned the light. So the rat now can't rely on the old strategy. There it turned, it got food. It's a bit hesitant in the clockwise turning here. So it starts motor babbling and explores the cage. There it turned. Okay, the light turned off again. So now it's correct again from the perspective of the experimenter to its correct behavior that it turns anti-clockwise now. So every time now that the rat turns anti-clockwise, it will get food. So as you see, the rat has learned quickly that. Now we try the other way around. There it did it. A bit motor babbling again. There it did it again. There it did it. It got some food. And still not really stable, but you can see that the clockwise thing, the anti-clockwise thing goes up in frequency regarding how correct it was there. Correct, whenever I say correct, I hope you understand correct from the perspective of the experimental design. It's me who are outside the chamber who defines what's correct from the perspective of the experiment. So we have used this excellent system. I don't know if you've heard about it. It's called Open NARS for applications. This is the old flowchart that was in the original paper. And the reason why I like to show this rather than the new one is because there was a branch on GitHub called MSC2 where the flowchart was like this. The declarative semantic inference part up there was removed. So basically this is, you get something similar to this when you compile ONA with a parameter semantic level 0. So what this means basically is that it, at that base level, it implements temporal reasoning, reasoning on events as statements, and reasoning on procedural operations and goals. So all experiments I will speak about today the explanations will only rely on these layers from NARS, so to speak. So let's say that we were to look at this rat example, but with our NARS friend instead. This is how you can set up a NARS system. Just type this into the into the shell. So we can have one operator named CW as clockwise and another operator called ACW as anti-clockwise. And this would just be one way of encoding. I'm perfectly aware of all ways to talk about properties. This is just illustrating how simple it can be to study this thing. So let's say that we have an event that the light is on and we have G exclamation mark, meaning for NARS that G is now a goal for the system. This is a goal event. The system, we trigger the system to trying to achieve G. But at this stage, if this is the start of the experiment, the NARS rat have no clue on how to do it. Will it do the clockwise thing or the anti-clockwise? It would have to rely on motor babbling. Anyway, we just try this and see what happens. And the system actually babbled with anti-clockwise, which was, as we decided, correct. So we provide the G event here. And thanks to having the G event there, this continuousy is derived. With high frequency, it hasn't seen negative evidence, but with low confidence, since this was basically the first time it saw this, so it derives it, but with low confidence. It also derives a direct prediction between, maybe when the light is on, the G happens, without reasoning on its own operations. Then moving from light is on to light is off. And with G exclamation mark, we trigger the system again, and it does anti-clockwise. But we, as experimental designers, are saying, no, we have said that, no, that's not correct. So this is the way how we show to owner that that wasn't correct. This statement functions as a punisher. Basically saying that in this context, G happened with 0 frequency. So owner derives this continuously. If the light is off and I do anti-clockwise, that leads to G with 0 frequency. There's a way about talking about what it has learned this far. We try it again, and it once again babbles what we would consider the wrong thing. So it gets more confident in that this has very low frequency. It goes from this confidence to this confidence. So it revises its previous statement. And now we try the thing again, and now it goes back to motor babbling, tries what we consider the correct thing, and derives that statement. So then when we show the light is on, owner will do the correct thing and report what kind of learned knowledge it bases its decision on. In what context, with what precondition there. And the same if we try the light is off, owner can also solve that task, so to speak.
The question here.
Yeah.
Just a matter of terminology, what do you call all of the premises and inferences? Is that called like a theory, domain theory, or what do you call it in
So I'm not sure that I'm answering your question, but this is what is called temporal statements. So we basically...
The combination of all the temporal statements. So G, light on, light off, and ACW operation, everything. What do you call that? Do you call that a theory? What do you call that?
So it's a good question because it ties into what this talk is about. It depends on if we talk about it from a NARS perspective or a psychology perspective.
What do you call it in each?
So here, this is an event in time.
Okay.
This is a goal event. Okay. This is a precondition that is used together with this temporal statement to make a decision to execute this procedural operation leading to a consequence. And I will soon talk about it from the perspective of psychology. Anyway, this is what we learned this far about what the system has learned. And we can think about a bit harder example. For example, we have been talking about previously in this workshop when the system starts to relate to several things at the same time. Once again, we have found a rat. This is a rat paper published in 1938. And in this rat experiment, the rat had been trained with what they call the jumping technique. So the rats could either jump or do something they call avoid. So the rat was trained initially to jump when it saw this kind of triangle and avoid when it saw this triangle. And of course, the rat had to, rely on motor babbling at first to train this. But then after a while, they changed the background and the rules were different, so to speak. The rat was supposed to avoid this and jump when it saw this. So basically it had to take the background into account. At first, of course, maybe the rat kept, jumping when it saw this and avoiding when it saw this. So, but with repeated trials, the rat understood that, I can not make my decision only on how the triangle look, but I also need to take the background into account. So basically, this is one step more complexity from the other experiments. So this is something that also can be studied with ONA like this, and after a while, it can basically come up with something like this. If we encode the, let's call it domain in this way, but since it's an AGI system, it can operate with any encoding. And so this is an example of when some behavior is executed dependent on multiple events, so to speak. But this example then is equivalent to what we would call the matching to sample experiment, equivalent from the perspective of complexity. So what is a matching to sample experiment? This is actually the kind of experimental setup that we have used for very many of our much more complex experiments. So what I show now is the simplest way to look at that experiment. So let's say that we have some nonsense symbol, never seen before, shown at the top of the screen, the sample. And the system is expected to make a choice between two other nonsense symbols. And without any further information, it would need to guess. And in all experiments that come after here, I will only use these symbols instead. But also these symbols means nothing to NARS. So we would, in the simplest case, train the system to, when A1 is the sample and B1 is to the left, we want the system to pick left with the help of giving it feedback. And when A1 is on the top and B1 is to the right, we would like the system to do the right operation with the help of feedback. But if A2 is on the top, we want it to pick B2, both on the right-hand side and on the left-hand side. So let's look at this in NARS then. So we can set up the system in this way, very similar to before. And once again, encode this with temporal statements like this. So if this would be the first time for the system, it would have to make a guess when we provide G exclamation mark. The system would need to guess between left and right. And the experiment then contains 3 experimental phases. So now we're moving into the domain of really studying this very rigid with a clear experimental setup. So during the baseline, we will provide no feedback. So we would expect the system not to learn anything. During the training, we provide feedback and expect the system to learn. And during testing, we expect the system to demonstrate that. And we have this thing of when I show the setup one time, it's called a trial. And each phase has 3 blocks of 12 trials in each. So we have used this Python experimental framework that is called Open Sesame. So this is a software that can be used for psychological experiments with people. And we have used it with NARS. And since Patrick has created a very nice Python interface for ONA, it's extremely simple to just arrange an experiment. So here I have the baseline, the training, and the testing. And within this, it's some like Python setup, but where needed, we simply call for ONA. So this is what it looks like when it's run. This is an illustration of ONA operating here. So this is the baseline. We provide no feedback. So the system has to babble or maybe do nothing. Sometimes it's correct, sometimes, but it doesn't get any feedback. Now we start to give feedback during the training. We can also see here that the confidence in the target hypothesis go up. And we also start to notice that the system gets more and more correct over time here, but still sometimes incorrect. And we see that we train the system in the 4 versions of the setup. Now we are in the testing, so there's no feedback given here, and the system is correct in most of the cases. And like that, yeah. And it's very easy to look at this is the log from the experiment, and it can be used to plot whatever happened there. This is the plot from the experiment. You see that the system did not perform better than chance. Just babbling between left and right would be 50% of chance. But during training, when we provided feedback, the system was more and more correct. Probably if we had continued, the system would have been even more certain. And then without feedback, it performed better than chance. And we also have plotted the confidence value of these hypotheses. And the hypothesis that was derived was these. The confidence in these increase over time. So I want to use this as an opportunity, the last 7 minutes of my talk, to ask then what learning is, or how can we define learning in a way that might be meaningful to talk about, both from a perspective of psychology and from NARS and other AGI systems. So, Belgian professor Jan de Houwer, he has defined learning as ontogenetic adaptation, adaptation throughout the lifetime. Or more specifically, he defines it as changes in behavior due to regularities in the environment. So let's look at this. And this is very thoroughly described in this book, The Psychology of Learning, that is freely available online from MIT Press. It's an open source book, extremely well written. They have also recently published a paper where they generalize this definition to many types of systems: genes, machines, groups, and organisms. And here we are in Belgium a few weeks ago, visiting Jan de Houwer, talking about our system. His students said, "I have never seen Jan as excited as today," when they looked at NARS. So they was really interested in our work. Okay, so one, how to say it, premise for the whole book that Jan has written is that it's meaningful to distinguish observations from functional knowledge from mental processes. And I will try to explain what that means and how it applies to NARS. So let's say that we observe some events. For example, light is on, light is off, there are some operations happening. That is something that is only observed. But to define learning as changes in behavior due to regularities in the environment, that's a functional definition, because if the change in behavior is seen as a dependent variable that depends on environmental factors, then it's what's called a functional definition. And it's basically a way to clear up what behavioral psychology has been talking about since the 30s. But if functional explanations is about changes in behavior, so learning is about changes in behavior, then mental processes can explain how that learning takes place. So learning is then defined as an effect of regularities. And functional theories can explain these effects in terms of moderators. For example, when these and these and these factors are present, that affects the behavior change. And a cognitive theory can then explain how these learning effects work in terms of mental mechanisms like associative networks or propositional networks or something. So if learning is described as ontogenetic adaptation, it's possible to further classify that into habituation, classical conditioning, operant conditioning, and more advanced types of conditionings. So the examples we looked at this far with the rats were examples of operant conditioning. Like this, for example. So to use the psychology language that you asked about, we can say that if we look at each block of trials and had the rate of correct responding as our dependent variable, that increased over time. So then the functional psychology question becomes how to explain that change in behavior with the help of regularities in the environment. So we know that thanks to the baseline, that G had an effect on the change in behavior. So G functioned as a reinforcer. And this is important. Reinforcer in this framework is not a reward as a mental event. A reinforcer is anything that increases the probability of this going up, so to speak. If it affects the change in behavior, so it increases in probability, then it's defined as a reinforcer. B1 being to the left functions as what's called a discriminative function. Discriminative stimulus for indicating that the left response could result in G. And A1 example also moderates this relationship further. So to end this talk, I hope you can see how this functional definition of learning as ontogenetic adaptation is very similar to Pay's definition of intelligence as adaptation with insufficient knowledge and resources. And this work that we do, we take a functional learning approach to studying these psychological events. So we study under what conditions does NARS learn? When does NARS learn? When we manipulate these factors, so to speak. And NARS in itself, the NARS theory, explains how the learning takes place. It's with these mechanisms in NARS defined as the logic rule and the control mechanism. So what we do at the Stockholm AGI lab is that we combine functional learning psychology with NARS. And we use this, let's call it a bottom-up way to study complex learning within these experiments, what I call idealized situations. Even if it's an experiment with left-right, you can study complex tasks. For example, last year we studied identity matching, and this year we have a paper on stimulus equivalence. And transposition that Patrick mentioned is also a complex task that can be studied within this setup. Our research is guided by relational frame theory, which is a functional theory about language and cognition. A theory that studies language and cognition from the same perspective as this. And my paper to the AGI conference in 2019 was about that approach. And also the workshop paper to the NARS workshop. I recommend those papers for anyone who wants to learn more about this approach. But I would say that the roadmap that RFT has provided for us has been extremely helpful in guiding research from the bottom up with NARS. So final slide here. The implications, and I really struggled with this slide when I heard your talk, Peter, because I wanted to add something that really matched to it. And I was working on it when Peter said, oh, can you go up? So there is a gap here because the final statement is not there. But let's take that as a metaphor. So anyway, when we define terms like learning from a functional perspective, I think it leads to an abstract way of talking about things that is not dependent on brain structures or anything like that, or other implementations. So when your team, Chris, for example, demonstrated the arm picking thing, that would be a typical, how to say it, other scenario where you can study operant conditioning using the framework of functional learning psychology. And what I really would like to say is this last thing, that this is not about simple rat experiments. This is really about studying extremely complex cognitive phenomena like consciousness and theory of mind and that kind of stuff from this perspective. But our roadmap provides a clear path that is well defined from the bottom on what steps we need to take for that to happen, which includes what experience does the system need, and it could provide ideas on what's needed from the process perspective in NARS. So with that, I say thank you. Yes?
Have you done, what kind of work have you done in terms of language learning? How do you learn language from the ground up?
That's a good question. So the very simplest, I can do like this. The question was, what kind of experiments have we worked on from the bottom up, so to speak?
Yeah, for language learning.
For language learning. And I would say a prerequisite for, let's see. A prerequisite for it was this thing that was published last year at the conference. And we demonstrate how the system can learn the identity concept through examples, so to speak. And we explain how it's done with the help of abstraction in PACE model.
Okay, great. Yeah.
And otherwise, we have done like preliminary explorations on how the system can do something that is called symmetry. That is a capability that is available very unreliably for like pigeons and sea lions. And it's from the perspective of relational frame theory, this is the building block for symbolic reasoning and language. And it's basically the ability that if I learn an A to B relationship, I derive the B to A relationship. So within the match to sample situation, it can be studied as if A is the sample and B is to the left, and I am trained in that, then I could derive in a new situation. So we have done some experiments on that, and this was a part of an experimental branch we had, but the paper that we have for this year's conference is more conceptual, that we argue that reasoning on statements as terms might be beneficial for this, to introduce higher order statements like this. So this could be the matching to sample situation. One situation implies another one. We prefer a more compressed representation than this, but it's along those lines, so to speak. And this year's paper that I will present on Sunday also talks about how it can use acquired relations from NARS layer 4 to even generalize it more further. But yeah, you had a question?
Yeah. So question slash, well, not a question, more of a comment. So each one of these that you just have up on the board, there's statements with the implication.
Yeah.
Is it a prediction, or is it a reflection of the regularity that is found in the environment?
So it is a reflection, but since it has introduced variables, it can be used as a prediction. So if if, for example, in a new situation that the system would see X1 is the sample, and if it has seen both ways, if it has been trained in both ways, like A1 was the sample, B1 was to the left, and B1 was the sample and A1 on to the left, the generalized pattern could then be used to predict. So if X1 is the sample and Y1 is to the left, then I predict that Y1 could be the sample and X1 being to the left.
You call each one of these a hypothesis or no? What do you call each one of these?
A hypothesis. Yes.
Okay.
So about contingencies as well, another word we would use.
Okay. So there's a great book by a guy named Gary Drescher called Made Up Minds. Have you read him?
Drescher schema.
Yeah. So the Drescher schema, right? Yeah. So each schema is the Drescher schema, kind of similar to what you have. He had context, action, result, or prediction, right? So you can throw away the action, or you can keep the action. But essentially what you have is that A, B1, B2, this event stream that's coming in, and the labels are irrelevant. You know, you could have all E1, E2, E3, E4 to E infinity, just these events coming in. And what you really want is just a subset of events and a prediction, you know, what is going to be predicted. You know, that is basically your statement, your hypothesis, right? And then you just play with these. As the events come in, you have the context, you know, the subset of events and the prediction. And then you can manipulate those. And that is the learning. That, you know, each one of those hypotheses represent a regularity in the world. And then over time, these regularities will fail because, you know, as in the case where A1 to the left and B to the right, and then that changes around. And so eventually over time, you will acquire these hypotheses that are consistent with the world. And the ones that are less consistent will fall out over time. That's, I think, the most valuable part of this, because now you have a learning system, general learning system. It doesn't require you to create a domain in the beginning. The domain is irrelevant. All you need is a stream of events. And so I think that is the most powerful aspect of this. And then in addition, Drescher talks about reification. So it is the embedding of these patterns. So instead of having just the raw events come in, you can synthesize new symbols, you know, like R1, R2, R3, which represent subpatterns. And, you know, like if E1, E2, E3 comes in, then that can be represented by R1, you know, the reified event. And so now you can look for the reifications in addition to the lower level events, or even higher level reifications, R1, R7, R8. Those are coming in because the patterns below matched and so on. So I think this is a really good direction. I think, you know, getting rid of the domain definition entirely, just working with the event streams would be a really good direction for this. And I think you'll have a very general learning system that's very, very powerful over time.
Yeah, and Jan de Hauer, when we met him, he basically said that learning psychology is defined on the domain of spatio-temporal regularities. Yeah. So it's only that, so to speak.
We wrote a paper a few years ago on this, which was called Goal-Directed Procedure Learning, where we contrasted our work with Gary Drescher. So, you know, he was an inspiration for sure, but there are some fairly strong differences as well.
Mm-hmm.
In our approach.
Yeah.
That's good. Love?
Yeah, so I have a question about the first rat experiment.
Yes.
So like the background for this is that you basically want to replicate somehow the experiments in the machine.
Not necessarily.
Yeah, but so I think what happens in like real environment, it's a bit. So we do some assumptions about how this environment is represented. So in the first experiment, what I noticed is that actually it's much easier for the rat was to turn clockwise than anti-clockwise because of the position, because there was a wall on that side. So it was like, so would it be possible at some point to include this kind of affordances of the environment?
Well, it's a very, so Vlad's comment is, I think, very, how to say it, you point to that there's a lot of stuff that explains the variability in changes in behavior. So if it's true what you said, that it was physically harder for the rat to turn in one way or the other, of course it affects the situation. But what I take, do you want to say something?
Yeah, no, it's fine.
There is no symmetry in the box. I agree. It was easily to around clockwise.
And I just want to say to you, Vlad, that it is a simplification to talk about precondition operation consequence, because in reality there's so many operations going on, like seeing the wall, smelling maybe something and so on, and all these events highly likely influence the change in behavior, so to speak. So I agree, it is a simplification. Yeah.
But I would suggest that the point is to abstract away and ignore those differences and only go for the events that are really of interest. You know, the whole point would be to get rid of it.
Yeah, but it's not possible to get rid of it, of these things in experimental settings.
No, so for example, you have a visual system. The visual system pulls in a lot of information that you have to reduce down to symbols or whatever.
Yeah, but we don't know how it's produced. We don't know.
So can I ask you to carry this on? We're already way over time. We've got to let's go yet. So thank you for your interest, mate.
Yeah. Thank you very much.
Hello, everybody. So a lot of synergies with the work that I've been doing with many of you here at Cisco over the last few years. And Peter, you know, actually, it's interesting. I started a few decades ago with Korsivsky's, ideas about knowledge representation and what differentiates humans from animals. I would think that I would characterize his view on knowledge as not that animals don't have abstraction, but that humans have infinite levels of abstraction. And we have this time binding property, right? The time binding property meaning that one generation of human can pick up where the last one left off from a knowledge perspective. And you don't really see that so much with animals. The other thing that I would characterize the work that I'm about to show you, some of the demos. But by the way, my name is Hugo. I'm with Cisco. And I've been working with a lot of the teams here. So my approach to trying to get more budget and get more emphasis on AGI is to get elements from the research community, add some of my own. We do have patents, a lot of patents, but we have a lot of open source. And actually, most of the work that I'll be talking about is open source. I have like over 90 patents on a lot of this stuff. But focusing on scalable, self-supervised learning, and how do we create a hybrid architecture that you can plug and play a lot of the research that you're all working on. So the idea that I had is to actually show this working. I'm going to go really quickly here because I know that we're out of time and everybody wants to take a break. So hybrid AI, in essence, is an open source framework that I'll show you in a second here, which allows you to plug in different reasoners. We have different symbolic, knowledge models. Oftentimes, if you have a great open source, graph database like Redis or Neo4j, we'll use that. We have, we do one of the core things that we've added is explainable perception, which is something that at Chris's last self-supervised learning conference, we were talking about with Pei, a bunch of us saying that, explainable perception, this idea that you can observe the world and then explain it without any human intervention. How would that work? It seems kind of oxymoronic, right? Because in the sense that how can you explain something if you don't have words or someone's not telling you what the language is? And the answer to that is going back to when you're 2 or 3 years old, and you remember when you started to learn, the concept of a train or a car, you actually created your own label, onomatopoeia. right? So you would say a train is a choo-choo train, right? So you would use the sound associated with that, or similarly with other things. Of course, doing onomatopoeia with machines is a lot easier because the sensory data can be converted, pretty precisely into an average image, average sound, or representative sound, even in a privacy-preserving way. So yeah, a lot of the work will be that we've been doing does center around this idea of explainable perception. So these are some of the elements here. We're bringing, you can think of it as bringing a lot of different things together. I'll show you the open source project that's doing this. And there's a lot of great challenges out there. So rather than try to come up with another, and by the way, we are part of Cisco Research, which has roughly $13 to $15 million, I think, per year that we invest in a lot of different universities. This is a small sampling of some of the projects that we're funding. Some of these may be, familiar. You see OpenNARS, ONA era, but things, hyperdimensional computing is going to be playing a big role in what we're doing. The self-sustaining vibration, we're multimodal, as a primary concept, and the vibration is a fantastic way to get really good analytics inside the home. Nobody wants to have cameras inside the house, but with vibration, I could actually, if I had a sensor here, a very inexpensive geophone, I could actually measure people's heart rates and breathing rates while you're sitting in the chair just by the vibrations in the foundation. Of course, there's it does vary by different sorts of materials of the foundations and whatnot, but so there's a lot of signal processing there. But let me just kind of skip along here. Okay, so this is the open source project. The GitHub is out there. A lot of changes happening out there right now. There's a lot of very active development because the idea that we have right now is that we want to address a few things. We want to try to see if we can get into the mainstream ICLR, NeurIPS. I do have a lot of papers in these conferences, but I haven't been able to get into the major conferences, CVPR, et cetera, with hybrid AI or with AGI, right? You just haven't been able to get in there. So the concept is to take a look at the current state of the art of machine learning and deep learning on really well-recognized, well-understood things. So you can go on papers with code, look at the dashboard. Here's a dashboard showing the current state of the art for object detection. Shockingly low, right, 65%, and here we are doing self-driving vehicles. And I would say that right now with Pei's team and with Patrick and Tori, we're already showing, I'll show you a demo, how this AGI, more AGI-ish approach takes this up, to me, I think we'll get within a month, I'm going to focus on this myself and a few others. I think we'll get into the 90s, high 90%. So you can see that it's been pretty much flatlined for 10 years, hasn't been progressing really, it's kind of reaching an asymptotic state here. We'll see, we'll hopefully be able to say that with OpenNARS and maybe Deep Vision together, that we're able to get, not a 1% or a 0.1% sort of a gain, but you're looking at 10, 20, 30% or above, improvements on that. So the hope was that would be a good way to get into these conferences, get more budget, et cetera. And if you look at a lot of the deep learning leaderboards, hype aside, and you actually just say, what are the actual numbers? You can always, you will notice, of course, that what happens quite a bit is that people will compare their technology to kind of trivial problems, right? The MNIST is still being used a lot with machine learning, deep learning, which is recognizing handwritten digits. You have CFAR, which is very simple little images, or recognize, even just the task of recognizing an image. It works really well with convolutional neural nets because they're affine transformation invariant, which means that they can recognize, but they can't localize, right? And so in the real world, you don't have animals that recognize and don't localize. I mean, so localization, recognizing what the object is and where it is, it's a very different problem that has also been stagnating. The current state of the art for tracking is another one that we're going to be beating here, which is, again, below 65%. So kind of surprising, right, when you think about where we are with robotics and self-driving vehicles. Some of the work that Patrick is showing when you take this AGI-ish approach to large language models, you could see that as great as these models are, the bottom one here was the biggest, right? Sometimes the bigger models aren't necessarily doing a lot better. GPT-4 is doing better. This is I didn't get a recent update on this one, but so here's a quick overview of the approach. This pyramid triangle is kind of my representation of how I'm adapting some of Korsivsky's ideas. I think he's thought most deeply about the nature of knowledge, which interestingly has really been overlooked to a large extent. So in my formulation, L0 is where you have the raw data coming in. L2 is where you have infinite levels of abstraction. If you take any, say you have a level of abstraction 1 million at that point, you can always have 1 million plus one talking about that prior label, right? So it's infinite in the L2. L1 is where you match the symbolic. So this is where you get into the neurosymbolic. You can see arrows going up and down on the symbolic, the spatial temporal self-supervised learning. We've done a ton of work there at scale. We have fantastic algorithms that I applied on Cisco data sets in pretty small computers, like on a laptop. You could run 1 million time series in real time and get and learn from that. And so we have some principled approaches, on that based on matrix profile, which is an evolution if you're into time series analysis of Fourier transforms and wavelets and all that good stuff. And then on the self-supervised learning on the reasoning side, there's something that's how I really use a lot of the open NARS. It's not just for reasoning, but the learning by reasoning is a very interesting thing. And you come up with a lot of, 10,000 or 20,000, or now with open NARS, I was testing it, I think it runs 200,000 inferences per second. So you get 200,000, chains of reasoning that can be quite long, and they're plausible, right? It's quite an intelligent thing. And here shows kind of the bottom there is a timeline showing the various projects I've had with Pei and with Ben Gertzel and a bunch of other people here. We started out with, I think it was the first deployed neurosymbolic system in the smart city, where you would just point a camera and it would learn, by the motion and tracking behavior, integrated a tracker with a reasoner. And we were able to use that to determine the semantics of the scene, right? Tony was involved with that quite a bit. So that would learn where the road, sidewalks, crosswalks, all that sort of thing is, and what the normal speeds are. And then it had a very basic ontology. I would characterize it as a few laws, speeding, obviously, maybe, illegal jaywalking, but the other one would be if any two moving objects, whether it's a bicycle, a car, or a person, look like they might make contact, we want to know about it, right? And so it worked really well, and we deployed it, and the customers, they really wanted to buy it, but Cisco wasn't ready to sell. That one did not have any sort of a meta model, interestingly. It was a very crude gluing together of a tracker with computer vision tracker and the reasoning. And what I learned when I tried to bring that into the retail domain, people said, hey, if you can point a camera, in a retail environment, automatically do what you just did for Smart City and say, here's where the shelves are, here's where the refrigerators are, here are the products inside there, and do that automatically, because the current products even today require a lot of training. We tried to do that, and we found that there was a scalability issue. So we needed the initial demand for the meta model was to be able to do a sort of a semantic partitioning of the problem. So with what we did in retail is we used this meta model, and it partitioned the space cleanly into multiple segments that could be processed with individual NARS in parallel. So it made it it kind of addressed the combinatorial explosion issues there. And then we have some networking things that we've done, which are very cool. I'll show you a quick demo of that if we have time. How much time do we have? I mean, I know we're over time already, but the HBA is very interesting as well. The time series analysis that I did started out with video. No, actually started out with the networking, but then I applied it to video, converting the tracklets into time series. And we found that the algorithms were so sensitive, they had to be adapted, but they were able to use people as a sensor. So, when people start fidgeting, or when people get nervous, or they have they hear someone screaming and the audience reacts to that screaming, it's so sensitive that it would pick up this collective behavior immediately. So we call it HBA, Human Behavior Analytics. Again, a lot of patents, but since we're open sourcing, with Apache 2, that you don't have to worry about that. Yeah, okay, so let's see if I can just kind of move along here. It seems like it's stuck. You don't care about the details of those things. A bunch of publications. You could look me up on Google Scholar with Patrick and a lot of you, the team here. Okay. Yeah, so by the way, just a word on what's happening with AGI. So I think part of the problem is that deep learning was so successful with convolutional neural nets. Of course, when you think about the problem of recognizing digits to having a deep semantic understanding of the world that's moving in spatial temporal, it's a big gap. So that success was kind of a double-edged sword. And so there's an illusion, there's this idea that you have to do it with deep learning, you have to do it with convolutional neural nets. We're finding, we're showing that that's not the case. So expect Pei and Patrick and a lot of us to get on the leaderboards with some of this the reasoning plus this other technology. Yeah, so we don't have time to get into this.
MOT, what was MOT on the previous slide?
It's multi-object tracking.
Okay.
Yeah. And so actually we already have, I'll show you a demo of what we have there. I know everybody wants to take off real quick. We have some good networking stuff. This is an interesting project. I would like to talk to anyone that's interested about where what we're doing is another way that we can use AGI is to help accelerate the use of deep learning. Since everybody already is using deep learning, they're using TensorFlow, PyTorch, Onyx, whatever you're doing with deep learning. What we spend some time thinking about is, well, what we have with this is not AGI, but in the direction of AGI with this hybrid AI, is we can actually automate a lot of the work necessary to create the deep learning models. So deep learning model, one of the most painstaking parts of that is generating the ground truth, right? So if you want to create any kind of model, you have to hand label. It's a very difficult process. AGI or hybrid AI can help you to generate your own ground truth in a much more efficient, automated way. So we do have this, this project ongoing. We have an initial prototype. So this is Tori's work on Patrick's team. So here's the state of the art for tracking. You'll probably won't notice, it's very subtle, but this shows some of the problems with trackers, because when the people get occluded with the people walking in front, the boxes on the back change color, which means that it lost the tracking, right, for that period of time. So and it's quite easy to fix with a hybrid approach that has an internal model of the world and says just because someone walked in front of an object doesn't mean the person behind necessarily changed their ID. So and so here Tori annotated this one, and you'll see some of the annotations coming up. And this is using, right now, I think we're moving, right, Patrick, to Open NARS, ONA right now. We're in the process of doing that. But there's a few other, we've analyzed the errors that the current deep learning trackers are making to keep them at 65%. Every single one of them is very fixable. I've also looked at the object detection. Combined with the reasoning and the multimodal models that we have now, I think we'll be able to fix all of that. So you can go to these sites. You can look up Cisco Deep Vision. There's a GitHub. There's also a research page on it. And so all the sources out there, it's all containerized, scalable, it's serverless. So the idea is that this is kind of using planetary scale sort of technologies. If you ended up deploying something like this and you want to go to say 10 million, or 10 billion subscribers, users, the entire planet, it's very doable with this, right? This is the kind of framework that just extends out. You can add servers, you can add data centers, the whole thing. So it's a very scalable. Being Cisco, that was an important part of what we did there. And then this integrates the reasoning and the time series analysis, self-supervised learning. All of that's coming together right now. I don't think we have to get into this too much. Oh, one thing I should mention. For this deep vision, the other piece beside that scalability and bringing these elements in that we added was this OpenMM Lab. If you haven't heard of it, it's a huge project that's run out of China. And what they do is they take the latest state-of-the-art algorithms in every area of deep learning, mostly vision related, but they go beyond that, everything from pose estimation, semantic segmentation, whatever it is, whatever the leaderboards are, they're designed, they try to put a shim layer that makes it easy for you to use OpenMM Lab with, whatever your favorite, platform is, PyTorch or TensorFlow or Onyx. And I think they support others as well. And so, but they don't run in real time. The whole purpose of their intention is to make it so that they can easily just create these leaderboards. So when a new algorithm comes out, you can compare them. Well, so we integrated this into Deep Vision. So now in the past, it took a lot of effort, right? To change any one of these algorithms was a lot of work, but now you just kind of change a configuration file and you're using, completely different algorithms. Yeah, this is kind of, when you first, run this, it takes a few minutes to build the containers, and then you get this initial thing. It's using, the continuous integration and deployment frameworks, which I don't think matters here too much. I already mentioned VisionWorks. It's this idea of automatically generating the ground truth. So if there's, and we've talked to a lot of customers. It looks like that's an interesting area where you can take a more advanced AI that could help generate, that could help you generate deep learning, current state-of-the-art deep learning models. There's a big need for that right now. So, it's kind of a intermediate step there. Yeah, briefly, I don't know if you want to see some of the networks. So the project was called Kronos, and it still lives. But the idea was you take hundreds of thousands of time series coming in, and we do this the self-supervised learning, to do the core idea, the core thing that we're building on is something called matrix profile semantic segmentation. We kind of had to adjust that algorithm, but what it lets you do is if you have a single time series, it lets you determine when the structure of the time series is not statistical, it's semantic. So when the structure of the time series, has changed from one mode to another. So for example, if you're looking at accelerometer data, it would tell you here's one behavior, which could be walking, here's another one sitting, et cetera. Those would automatically be partitioned out. And it tends to be semantically meaningful, like I said. So for people, it means that, hey, they're having a normal behavior, but now the rate of change of these things is increasing. So that tells you that maybe people are nervous or there's something else happening, so when you apply it at scale, the idea was, okay, so any system that has interrelated time series, networking, security, biometrics for people, whatever it is, if you have a lot of time series, you're going to, whenever you have a lot of these time series have a simultaneous regime change, semantic change, then it might mean something. That's what those Ks mean. It turned out that it's true. And then if you map that information onto what the time series are, then you can, in the symbolic domain, then you can begin to understand something about the network, map it onto here, we're mapping the insights from these time series that are having simultaneous regime changes. We're mapping it into what the time series were, what does it mean on the network topology, and then we're mapping it onto the data center. So here's just because it's a very simple display that says, hey, here's what's happening. It's this unit, it's rack V3, and this is the, what's that? So you already know about the LLM. One of the projects in UCLA that is also doing intent-based, querying with kind of a SQL-like language that we're incorporating as well. So I think that was really quick, but just a quick word on Cisco Research. This is a small sampling of over 100 universities, 25 countries, a lot of different areas that we focus in on. I think we're going to see a lot more in the AI area. Yeah, this is the team. So I do encourage you, if you have a chance, take a look at the GitHub. It is evolving a lot this month. Our focus is going to be, because we're refactoring, we're trying to make things a lot easier to use, and we're adding code that will be associated with these new results for tracking and object detection. Probably just do the tracking. I think that would be the main one. But it would be good to have you on that one, Patrick, for the tracking. So I don't know if you have any questions or thoughts, but I just wanted to get through it quickly because I know it's the end of the day and everybody's a little bit. And for me as well. I took a 20-hour travel to get here, and I just came straight here. So good. Any thoughts, questions?
Where are you based?
So I'm in Temecula, wine country.
Okay.
Yes.
Oh,
Yeah.
I just moved from Austin.
Oh, I think you're gonna go. Oh, to Austin. Okay. Yeah, it would be great to follow up. Oh, thank you. I'll send you an email.
Thanks, Hugo. And thank you, everyone who did the prior presentations. I will compress my talk in the interest of time. And I get the
My name is Chris Thorson. I'm a professor at Reykjavik University. I guess it's my job now to try to connect some dots. I think it's nice and appropriate that this talk happens right at the end, because it's a kind of a sandwich that we make with Peter Voss and I. He sort of talked about this from a fairly high level perspective, and I go into a little bit more detail, throw some ideas out at you for how to do AGI. Yeah, and the title is it's a word salad, so, but bear with me, I will connect the dots. So just to remind us, what is the goal here? This is the goal, this is our shared goal, to create general machine intelligence. Like most people here, I think I really agree with this view on intelligence, its adaptation with insufficient knowledge and resources. These are really key things to keep in mind when developing AI. Or how I like to say it, figuring how to get new stuff done. Because everything else that humans do could potentially be done in some other way, but this is the one where you absolutely have to have intelligence. So that's at the heart of the matter. And as has been discussed already, which was nice in Robert's talk, it's impossible to figure out how to get new stuff done unless there's some regularity. If there's just noise, well, by definition, nothing leads to anything else, and so you can't really get anything done. And this is where explanation comes in, but let's not get ahead of ourselves. So how do we figure out how to get new stuff done? That is the task of AGI. Well, I'm going to throw this at you, and it's this: produce an understanding of this stuff. So unlike some well-known philosophers throughout the ages, and especially in the second half of last century, I don't consider understanding to be an irrelevant philosophical curiosity. But then, of course, I have to explain to you what does it mean to produce a state of understanding. So when you say you understand something, it has some implications. You should be able to explain how this works, this thing you say you understand. You should be able to assess your own ability to affect this phenomenon. You should be able to give an outline of the extent of your understanding of the phenomenon, and so on. There's other things. You should be able to identify misunderstandings about the phenomenon, or misunderstandings in others about the phenomenon. You should be able to improve your understanding or your knowledge of it, and deepen your knowledge, increase in breadth and depth. Because understanding essentially enables a few things. There's really four things. One of them is prediction, and a lot of people talk about prediction, and some have even claimed that the goal of science is to predict. Well, it's not. Let me tell you that. It's actually to explain. But prediction is a big part of that. Now, you can actually make predictions simply by knowing correlations, but you can't explain. And so you can predict without understanding. So that's not sufficient. But is explanation sufficient to, or sufficient evidence of understanding? Well, you can explain with partial and even faulty understanding. So, of course, your explanations will be partial, but then again, there's still explanations. And lastly, and this is very important, goal achievement. It's very impossible virtually to achieve goals with respect to some phenomenon unless you understand it, right? So unless it's through some sort of luck or educated guess. There's one more before we leave this slide, and that is recreation. So if I ask you, do you understand the solar system? And you say, yes, I know everything there's to know about it. I understand it completely from A to Z. And then I ask you, well, write me a simulation that predicts perfectly where the planets will be tomorrow. And if you can do that, well, your claim is absolutely correct. You really do understand the solar system, how it runs and its rules, right? But you actually need all of these to talk about understanding, because alone, any one of these could simply be regenerated or actually implemented in some other way. So only by combining these do you have a real evidence of understanding. And the best way to assess an agent's understanding of anything is essentially to do a thorough test with all these kinds of probes. You know, ask them to predict, ask them to explain the prediction, ask them to achieve a goal and explain how they couldn't have achieved it if someone had done something else, and so on. So it's really not an irrelevant curiosity of a concept. It really is important for AGI research. And I actually have a theory of understanding, which I will not go into now, but you can look it up if you're interested. And I really think that this is necessary. Certainly not sufficient, but necessary for AGI to progress. Okay, so back to the question. How is a state of understanding produced? I haven't actually answered that question. Well, to look at that, we need to ask this question, and actually the question was also in Robert's slides, which I find really funny. So what is learning? And this is like my 30 seconds of explaining this in a way that ties in with the rest of the terms in my title. So it is the systematic creation of knowledge from experience. And it has to be bootstrapped somehow using reasoning. And what is being modeled there, and so essentially all of these methods that we've discussed here today are about modeling. And it's about modeling of experience. Now, these models can be done in various ways. And that is the difference, for instance, between NARS, my own architecture era, and others, Drescher's approach. So, and the devil's in the details, but it's all about modeling. So here's how I see it. Okay, if you have some phenomena, the oval is the agent over time, and it has some knowledge. It has something that it sees as familiar, but you know, if it's young, it has a lot of, it encounters a lot of novelty. And the trick of learning is essentially to reduce the models of novel things over time and increase its models of the world, so that increasingly its knowledge, its head is filled with the models that essentially then turn the world into familiar territory. And there's one thing missing here, and that is, yeah, so this is figuring out new stuff. That's what this is, this picture. And then we come to this term, seed programming. And this actually has an important connection to novelty. So when a learner is born or is entered into a world, an autonomous learner, it needs to be able to do this process autonomously. Otherwise, it can't bootstrap its own learning or figuring out new stuff, right? So we mark here something called a seed, which the learner must be born with, because if there's nothing to bootstrap the learning as it's fresh out of the womb, digital womb maybe, then it can't bootstrap. So it has to have something to bootstrap. And this bootstrap code may actually get reduced over time, but the process is still the same. Learning is about reducing the amount of novelty encountered. So that is what seed programming is. It's really a way to talk about imbuing systems with autonomy. And seed programmed learning is basically just a special case of learning where the existing knowledge is very, very small. So seed programming is knowledge bootstrapping, and that is figuring out new stuff. So there we are, essentially. The ability to bootstrap using model creation from insufficient knowledge requires ampliated reasoning, all kinds of reasoning, and recursively use it to systematically test the knowledge and verify whether it matches how this regularity in the world works over time. And we achieve this through hypothesis testing, and that was another excellent discussion here just a bit earlier. So we need to be able to identify relevant relations, create models of these observed relations or hypothesized relations, essentially, compare subsets of our knowledge to the observed to see if it makes any sense in light of our current knowledge. And if it doesn't, come up with some ideas for how it might work. And this is actually achieved through explanation, and that's where explanation comes in. So this is connecting the dots, folks. So explanations are really good for getting stuff done because they allow you to keep track of your hypothesis generation and the results of your hypothesis testing. And this is all, this is not necessarily deliberate. I often talk to people, they think, oh, you think people are walking around, making hypotheses when they're learning, like 2-year-old kids, you think they're hypothesis testing, like miniature scientists? Well, actually, yes, but it's not very reflectively available to them at the time. It's just processes that are happening autonomously. And so again, explanations allow you to keep track of your progress in achieving goals and predicting outcomes and recreating phenomena. And in fact, it's also a way to learn to get better at explaining. So it does really have a recursion there. So now we come to the bottom line, which is this. Explanation is good for improving or proving understanding. If you cannot explain it, well, maybe there's a hole in your understanding. And in that sense, understanding is really about a model, a composite model of the phenomenon in question. And these are the sub-goals of explanation. When you explain something, it could be it's definitely meeting the top level goal, but it could be one of the others as well, maybe even more than one at a time. So this is the top level goal and sub goals of explanation. Now, to be consistent and reliable, explanations must rest on causal relations, which means that we need to have good models of causal relations before we can properly explain. And this ties it back to science, because if they can't be falsified, well, you can't really verify that there's any value in them. So at that point in time, until they have been tested repeatedly to be falsified, they really just stand as a hypothesis, like all ravens are black, except for the ones in my backyard, which I've never seen, but I know that they're multicolored. That's a hypothesis that, well, I can't test now, and not until I get back to Reykjavik can I test it, actually. So anyway, here's the conclusion. essentially, this is what forms the basis of cumulative learning, systematic hypothesis generation and testing through explanation and experimentation on the world, which bootstrap the process of learning or figuring out new things. And this allows us to get better at understanding new things and produces deeper understanding and forms the basis of general intelligence. So that's all, folks. Thanks to my sponsor.
Could you go back to your slide on the seed?
On this one?
The seed. Your seed.
Yeah.
So the seed program right there in the initial learner.
Yeah.
The I don't know what that Greek symbol is.
S.
Oh, S. Okay. Okay. So the seed program. So what do you envision that as? Do you envision it as a NARS program, or do you envision it as some other code that will eventually build the events, which are the phenomena or the aspects of the phenomena, and the novel aspects and everything else? What do you envision that seed?
The answer is yes. All of the above.
Oh, so it's all together.
This is just the point being made here is that you cannot really bootstrap your learning autonomously unless there are already existing some methods for bootstrapping. So in a human baby, I would say, take the example of, why is it that all they can do more or less is eat, sleep, cry, and, something, a few other things. Like, and the crying is basically anything, it means pretty much anything.
Right.
And so that seed assumes a caretaker. If there's no caretaker for human babies, they die because the bootstrap code is so primitive, right?
It also mean the innate capabilities that we have, like, for example, distinction between, like, whether whatever label we associate with it in any language, but we have like innate capability of this object is same as this, or this is bigger than that, this color is different from this color. Distinguishing color, sound, smells, all those different things, those are like innate, whether we understand language or labels or not.
Yeah, well, yes, you are, if you want to operate in the physical world, you have to have sensors that can measure the world around you, the physical world in that case. If you're a digital entity, running in a simulated world, it works differently, but you still have to get that input, and it's still assumed to be happening over time. With AGI, I think, AGI researchers cannot ignore the physical world. And unlike what maybe a mathematician might say, well, you can make mathematical worlds that are infinitely more different and more complex, et cetera, than the physical world. But my answer is basically this. If you can't do the physical world, if your AGI theory can't address the physical world, we have no deal, because that is a necessary component of a general intelligence. As we conceive of it, because most people that I've met and argued with for hours and at conferences, they ultimately agree that, well, I guess we will call what humans have general intelligence, because we don't have any examples of anything else. But essentially, of course, it's a multidimensional phenomenon.
I would call the seed the mechanisms of the intelligence, and then everything else coming in, the phenomena or the data or the events that are coming in, and then everything gets built up from those mechanisms.
Yeah, there's multiple ways of bootstrapping. You could, engineer it in with the biology or the mechanisms if it's a machine, pure machine. There's many ways to think about it. But in any case, these have to do with information. These have to do with measuring and affecting through the base mechanisms of your embodiment. And if your answer is, and I know yours isn't, but if someone says, well, but my AI doesn't have a body, I call bullshit, because somehow you have to measure the environment you're in. no entity is omniscient, or omnipotent. The assumption is that there's more in the world than there is in the knowledge of the agent. So this seed has to do with basically some sort of information processing. Okay. Yes.
In what you call a seed, do you make a difference between a need and a reflex? So let's say that both are innate and then part of the seed. Would you make a distinction between a need and a reflex?
There's no need to make that distinction here, because this is really just about the information that is needed and the program. It's a program, for sure, that's needed to bootstrap the learning. Okay. And learning, and I agree with your slides about learning, it matches this perfectly. Learning essentially about extracting, you could say, useful patterns to achieve whatever it is you want to achieve. And if it's a biological system, it's of course basically to survive and maybe procreate, otherwise the species disappears. For a machine, it's whatever the engineer essentially decided, I'm going to make a machine for this or for that. So if it's an AGI that was born in a research lab, it should have all sorts of features, open the hood, etc., explain itself, and so on. But that would be the top level reason for being, for that being.
Get started. Can you estimate absolutely minimum requirements for the seed part of this diagram?
Yes. It needs to be sufficient so as not to make the learner block its own ability to learn. Okay? Then it would be a non-learning agent, and then it's outside of the scope of our research. So it will have to be something that bootstraps it under the assumptions of what's available in the world. If you make the seed extremely general, then you might, so in sense, I don't know what world this agent is going to be born into, so let me try to make it really, really general. You'd still have to make it build on some assumption like there's going to be a caretaker, or there's going to be air to breathe, or whatever it is, however this system is able to continue to learn to bootstrap until it knows enough to avoid getting killed or getting disassembled or whatever it is, So these are very general concepts. Yes.
On the definition of understanding, it seems like the description is still from an external view of the understanding. Point of view of the internal, like the system itself.
Yes.
It seems like different type of the description of understanding can be unified as some kind of internal operations, like some checking point or something like that, and a measure of whether that operation is achieved. So.
Yes, for that you have to check my paper. Yes. All right, folks. Thank you. Thank you very much.
Interesting.
My understanding is very interesting. I mean, I struggle with it a lot, to be honest.
Just like
Yeah.